Okay, so welcome to the week 5 of problem solving session for the design and analysis of algorithms course. So last time we saw two kinds of problems. One was the shortest path problem, and the other was the minimum spanning tree. Okay, and for each of them we saw two algorithms. One was due to Dijkstra's shortest path, and then we had a Floyd-Warshall algorithm. And for MST we had a Kruskal's algorithm, and we had a Prim's algorithm. Okay, so last time we saw the algorithm and some properties about the algorithms, but what we did not do is the running time analysis of them. So this time we will look into the data structures that you can use. Um, so you can do a trivial or naive implementation, but that will uh, the running time of that is not very satisfactory. So what we do is we don't change the algorithm remains the same. Instead we make a clever choice of data structure that allows you to do certain operations efficiently. So for each of these, maybe not the Floyd Warshall, but yeah, for the rest of the three, we will see we will see what kind of data structures are good. Okay, so okay, okay. So recall the okay. I think all of you are familiar with Dijkstra's algorithm, right? Um, we don't need to do the example again, right? So this is a pseudocode of the Dijkstra's algorithm. So basically, what it does is, um, initially you have, let's say you have some, yeah, you have some graph like this, and say A is your source node. Then initially what we did was from yeah initially the distance of A from A was 0, the rest of them were infinity. And then what we did was we sort of took the smallest value from here, we removed it and updated the distances, the immediate distances of that. So this becomes 3, this becomes 1, and this remains infinity. And then among these two, do you recall which one we chose to explore next?
D.
Okay, anybody else? Okay, so what we did was we chose C because among the remaining vertices, you always look at the uh, minimum distance.
D is 1 kilometer away from A. I think
Oh,
wait.
Okay,
Uh,
sorry, I did a wrong labeling. Thanks. Okay, so this is B, D, C. Okay, so you choose to explore D, and then how do you update the rest of the distances? Okay, let me just add one more each. Okay, so I'll just add maybe one. So how do we update now? Now we are choosing to explore D. So
its parent is A,
okay, parent
and
is A. You will store that.
distance is 1. So we can say in bracket A comma 1. We can write.
Yeah. Okay, but how do you update the distance to B? So now B is reachable via this path, right?
So 2.
2, right? So we will update this to 2, and now C is discovered through this edge, so we will update this infinity to 9, and then we are going to store the parent. So in this case it is A, and then D is already
9
explored.
or 10?
Sorry, 10. Yeah, 1 plus 9, which is 10. Okay, and then what do we do? Which is the next vertex to explore?
B.
B, right, because B is smaller, so 2 is smaller than 10, and then you update the distances based on this. So uh, this becomes 10 again, which is same as what you had, so you don't need to update, and you will stop your exploration. So the shortest path that you get is that of 10. And how does it go? A to D, D to C. So yeah, you can trace it back like this. So this is the quick example of what we did, and this is a pseudocode for this. So what we essentially did was we initialized it here, and each time we're going to select a node which is least in the value in this array. So, and we will remove that node and update the distances. So if there are smaller distances that are discoverable from that vertex, we'll update that and keep on doing this until all the vertices are visited. So what is the running time of this algorithm? If you do a naive implementation, what would be the running time? Okay, so let us see what happens inside this loop. How much time does a particular iteration take? What we're doing is, when I choose a vertex here, I'm going to look at all the neighbors that it has, and we're going to update this minimum distance. So calculating the distance is just one step thing, but how many such edges can be there? In the worst case, how many edges can we update?
In the worst case,
In the worst case,
we can update any of the edge which has, like, if there
yeah,
are edges with same weights,
yeah,
so we can update any one from those edges.
yeah. But what we do here is, yeah, recall that what we do here is, let's say I'm visiting D right now, then I'm going to look at all the edges that go outside, and I'm going to have to check whether the new distance is smaller than the previous one. If it is,
Yes,
so I'm anyway going to have to calculate that. Updating or not is a different question, but I have to calculate. I have to spend my
yes.
time in calculating. So what are the maximum number of edges that can go out from
Degree of out,
degree?
degree
Huh.
of D.
So degree can be n minus 1 in the worst case. Um, right? So
Yes.
in the worst case, it can have all the neighbors. So then what we do is, uh, so this step is going to take like order and time. Um, okay, and how many times are we doing that? We're doing it, and we are visiting every vertex. So this is n times, and so overall this will take something like order n square. Okay, which looks like it's not bad. But if the graph is very large, then n square is also bad for us. So I don't want to do it in quadratic time. I want to do something smaller. I want to do, say, n log n or something like that. Okay, so I want to bring it down to, so this is the trivial implementation, and I want to bring it down to, let's say, order n log n. Okay, so how do we do that? So before answering that, let's understand why are we spending so much time. So where is the maximum amount of time going? It's going here. If I could somehow, um, if I could, like, okay, and there is one more step where we actually spend time. It is in the first line, where I'm finding what is the minimum vertex or the minimum distance in this array. So this time, for example, I chose 1, then the other time, the next time I chose 2, and so on. So every time what you're doing is you are looking at this array, finding the minimum element which has not yet been explored, and then you're carrying. So you actually have to find the minimum element. So this can take order and time. So how will you do this if you want to find the minimum element?
We can use any of the sorting.
Yeah, in fact, you don't need to sort the whole array, because you're just finding one element. So you just keep comparing. It's like bubble sort. So you take this element. Okay, this is already explored. Take this element, compare with its neighbor, keep the current minimum. Now compare the current minimum with the next one and so on. So you can just, in one scan, you can find the minimum element. So this much time is needed for minimum element, but it's not adding up to the, this is for finding minimum element. So um, yeah, so what are the kind of operations that we are doing? Can you so one operation that we are doing is, okay, one operation we are definitely doing is in finding minimum, or I'll just call it extract min. This is one operation that tells you within this array um, how much, you want to find the minimum element in that. And the second operation we are doing is delete. Okay, so what is delete min? What do I mean by that? So when I choose the minimum element, I'm actually going to remove. So we are marking this as visited so that we are never going to visit the same vertex again. So we are sort of removing that element from our data structure. So this is another operation that we are performing. And the third operation would be decrease. What do I mean by that? So what happens is, whenever you update this, so initially your distance was 3, now you discovered a smaller path which is from A to B, so you're going to update this. In that case, you're going to decrease, basically updating the new value of the distances. So that is also another operation that we need to do. So these are the three operations we have right now, and given the kind of implementation we do, it's taking like order n square time. Okay, but the reason we are identifying these operations is that if I could do all these operations, um, if I could do it efficiently, then the hope is that I would reduce the overall running time of the algorithm. So for example, let us identify how many times are we performing each of these operations. So how many times are we performing extract mean? N times, exactly. So this operation we are performing, um, here we are performing extract min n times. And what about this, how many times are we performing this decrease key operation? N plus n. So we said that we are looking at all the neighbors, right? So the degree could be in the first, yeah, okay. So um okay, so in fact I'll just call this delete min, because after this point you are basically going to remove that vertex. You are never going to deal with that vertex again, so you just think of it one step. Okay, so now what I want to do is, I want to find a data structure that can do all of this um, as easily, as quickly as possible. Okay, so okay. So first data structure is the trivial algorithm that we just now saw. So if I just use an array, um, then how much time does it take to do this delete min operation? So this is something that we said just now, right? So we said that if I want to find the minimum element, I'll look into the array, I'll make one scan, and I'll find the minimum element. So delete min will take something like order n time. And what about decrease key? Okay. Yeah. So you are correct about order n minus 1 thing. Okay. But okay, in fact, you don't really need that much time. No, you can just go. Let's say I want to update the value at D. I'll just go at, maybe I want to update at B. I'll just go at B and I'll update it here. So that's just one step thing. It's like constant time. Okay. But yeah, so this is something like constant time. And then the overall, what is the overall cost of this? You are doing this operations n time, so this is something like order n square. This is the trivial algorithm we saw. Now um, what I actually want to do is, I want to design a better structure that can fetch me these two answers as quickly as possible. Okay. So okay, so to do that, let me just um, yeah, let me just define a data structure. Okay, so imagine a tree. So like we said earlier, so tree is basically an acyclic connected graph. So imagine a tree like this, where I have written some values. Okay, and this particular tree has a property. So do you see, is there anything special about this tree? If you look at the values, does it satisfy some property?
The next generation weights are, higher than the.
Exactly. So if you look at any vertex, any node, and you look at its children, immediate children, the value of this parent is always smaller than both the children. If you take any vertex, so for example I take this vertex, the value of this is always smaller than the value of the children. So 11 is smaller than 15 and 20. Similarly, if I look at 5, the value of the children uh, is higher than that of parent. So such kind of structure is called a min heap. Okay, and similar to that, I can define a max heap. So what does that mean? Can you give me an example of a max heap maybe? Just tell me the values that I should write here. So it should satisfy the property that the value at parent is always high, greater than equal to the value of the children. Yeah, so can you give me some values? So for example, if I give you 10, 7, 9, 11, 8, 6, is this a max heap? Mm, how but does this satisfy the property of the max heap?
Ma'am, it should be 11 and 9, no, ma'am.
Yeah, so here the value of the parent is smaller than the value of the child, which is violating the property of max heap. So what should happen is, if even if I do this, even if I write 11 here and 9 here, this part is fine. Okay, this part is satisfied. Now the parent here is larger than the value of the child. But if I look at this pair now this is violated, right? So now 10 is smaller than 11, which should not happen. So what can we do to make it max heap?
And we can put 9 instead of 11.
Mm, where?
We can replace.
Okay, we can replace.
Hmm. We can take 9 in place of 11.
Okay, but then that pair will, if we swap these two, then that pair is um, violating the property, right? Okay, is this clear that we're talking about max heap here?
We can, swap the 10 and 11.
You can swap the 10 and 11. Okay, so let's do that. So I swap. 10 and 11, so you have 11, 10. Now this pair is fine, this pair is fine because parent is greater than child, parent is greater than child, but um, this pair is also fine.
Hmm.
But now here we have a problem. So what do we do?
Similarly, we can swap 8 and 7.
Let's say I swap 8 and 7. So this is not an algorithm that we are seeing. We are just arbitrarily just changing values so that it satisfies the property. Okay, we'll look at a procedure, an algorithm for doing this very soon. But right now, let's just focus on understanding the structure. Okay. So okay. So this is what we have. Okay, and now let's say I want to find the minimum element in the whole heap. I'm not looking at the max heap right now. Let's just focus on the min heap. Suppose I give you a tree like this and I want to find the minimum element in this heap. Then how much time will it take you to find it out? Okay, what are the two swaps that you are talking about? So the question is that I want to find the minimum element, or let's say a minimum element in the mean heap. So how much time does this take?
We go up one.
Exactly, order of 1. Why is that?
Ma'am, because the first element, that is the parent node, that is root node, is the
Yeah,
minimum one.
exactly. So good. So because of the property that we define, we said that the value at this root is always going to be smaller than the values of its children, or it is at least at most the values of its children. Now if you look at this as your tree, then the values here can only be larger, they cannot be smaller than that. So there is no point in looking at any element here because these values will definitely be larger than the root, or they cannot be smaller than the root. And same thing happens here, because this value is larger than the that of the root. What follows here can only be larger, it cannot be smaller. That means the minimum element of the heap is always going to be the root. Is this clear to everyone? So this takes order 1 time because the root is the minimum element. Is this fine with everyone?
Yes, it's fine.
Okay. Okay. And okay. So now okay. So now the problem is that if you compare this, if you compare this with what we wanted for Dijkstra's algorithm. So we wanted two operations. One was we wanted to delete the minimum one, and the other was we want to do some updations. Okay, so that means you can think of um, these values, right? These values that you keep updating throughout your Dijkstra's algorithm. You can think of these as your nodes of the tree. Okay, so these are the values that you have. Okay, and when I delete it, that means I'm visiting that particular vertex. So let's say I'm going to visit this now. So this vertex is going to be deleted from the heap. So that means uh, there is like a hole that is created. This is no longer a heap because there is nothing in the root. So what I need to do is I need to uh, move some values up and down so that the resultant structure is now again a heap. So although finding this minimum element is only taking me order one time, there is some time that I need to spend to make sure that after deleting the vertex, the remaining structure is still a heap. Okay, so we need to find a procedure for doing that. That process of doing that is what we call heapify. So okay, so any ideas about how do we do that? Let's say I remove the 3, now there is a hole that is created. So how do we do that? Okay, so let me ask you, um, where is the second minimum? So 3 was the minimum element of the whole um, heap. Okay, so where is the second minimum?
5.
Huh. So in general, if I give you the structure, where should the location be? So we said the
uh, i- in the first child there will be, one of the element will be minimum.
exactly, exactly. So we know that the minimum element is at the root. The second minimum has to be either the one of the two child. Is it clear why? Because if you look at the child, then everything below it can only be larger. It cannot be smaller than that. And similarly for the other child also, everything below it cannot be smaller than the value of that itself. So if there is a minimum, so the next minimum has to be one of these two children. Okay. So that you can find in one comparison. You just look at look at which child it is. So compare 10 with 5. Okay, in this case it so happens that the answer is 5, so we'll do this, okay, step by step. So let me get this diagram there. Okay, now okay, now we said that the minimum is 5. So what I'll do is I'll bring this 5 up here. So now 5 is here, and now I'll delete the value here. So there is a hole again. So now what should go here? If you use the same idea again, you should have the minimum of this heap. If you forget about this part and think of this as your heap with this as your root, again the same thing holds, right? What should happen? The next minimum should come up. So where is the next minimum? It is one of the two children. So then we will compare in one more step. We'll look at the two children, and then um, we will update this. So this becomes 6, and now this guy is deleted. Okay.
Yes, ma'am.
Okay, so all of this is just an intuition of how it should happen. Okay, but now the problem with this is that this structure here is not a heap. Why is that? Because whenever I define a heap, it should be a complete binary tree. What do I mean by that? So what is a binary tree? Let's break it step by step. So what is a binary tree? I have a root, it has two children. For every node there are two children like this. Okay, and something like this, something like this. Okay, all of this is a binary tree. But when I say a full binary tree, what it means is all the levels have to be full. Okay, that means I have my first root, I have my root here, then it has to have two children. Okay, then this has to have two children, 4 5 6 7. Okay, so it has to be, every level has to be full. You can't have a level where something is missing. So this, for example, is not a full binary tree because I have some levels here, some nodes here that are missing from this level. Ideally there should be 8. So this level has 1, 2, 4, 8 powers of 2. So there should be powers of 2 in every level. So if I do this, okay, if I do this, then this is a full binary tree. Okay, but what I'm interested in is a complete binary tree. And what does that mean? So complete binary tree is just a relaxation of full binary tree where every level is full except the last level. In the last level, I'm allowed to have some nodes deleted. For example, this. Okay. But you can't have, like, if you are deleting, you have to delete everything to the only to the right. You can't arbitrarily say delete these. This is not allowed. So if you start traversing, it should look like this. uh, okay, this is full, this is full, this is full, then there should be something here. The moment you stop, it has to be on the right. So is this making sense? So if at all there are vacancies in the last level, they have to be on the right and a contiguous set of vacancies. Okay, so okay, which is not what is happening here. Although it is satisfying the properties that we want, it's not in the form of a complete binary tree, because here there are nodes here that are missing from the previous level. Is this making sense? um, is the definition of complete binary tree fine with everyone?
Yes, ma'am.
Okay, so then how do we define a heap? Heap is basically, or let's say min heap. So min heap must be, first of all, it should be a complete binary tree. And second thing is that the value of the child, or the value at parent, is always smaller than that of children, or less than equal to. These are the two properties for the min heap. Okay, so now we come back to this problem where I want to find the minimum. I can find it. The moment I remove it, there is a vacancy, and now I need to perform this heapify operation in order to get my structure back to that of a heap. So do you have any other ideas? How do we go about it? Okay, so let's see how do we do that. Okay, right now there is a vacancy here. Okay, so let's see what do we do. We go to the last element in the, go to the last level and take the rightmost element that you have. In this case it is 13. So I'll just take it, I'll remove 13, and I'll put it at the root. Okay, but is this a heap now? Is this a min heap?
But मैंने सुना अनिल वाला
Hello, yeah, sorry, I couldn't hear you. Can you repeat?
No, I think.
Yeah, it is not, because the root here is larger than the value of the children, which is not what can happen. Okay, but then what do? We do the same idea that we applied earlier. We said that then where is the minimum? The minimum can only be one of the two children. Okay, we compare these two children. Now we know that 5 must be the min. So what we do is we swap them. So let me do the swap operation. And now okay, now what happened is that okay, now what happened is that this is smaller than its two children, and the whole subtree under this is also satisfying the property of min heap, because we did not change anything there, right? So this was already following the property of min heap. This is also satisfying. Okay, the only thing where it's violated is where you the side where you swapped it. Now you swapped it here and it has created more new conflicts. So this is not a min tree, because min heap, because the value of this parent is larger than its children. So then you do the same thing again. What will you do now? You'll find the minimum, next minimum. So where should it be? Is the question clear? Yeah, sorry, I couldn't hear you.
What is the question, ma'am?
The question is, where is the violation now? Where is the violation of min heap happening?
सेकंड पेज में क्या किया इन्होंने जस्ट वहां पर तो बाहर निकालने के लिए गवर्नमेंट ने ये किया कि ट्रेन जो बाहर जाने वाली ट्रेन
Okay.
आपको वाराणसी जाना है 100 किलोमीटर ट्रेन में आपको कोई फेयर नहीं है यहाँ से बाहर कोई आप टिकट वैसे किया एस 6
6 8, you mean 13 and 6, or 13
yes
and 8?
yes
Right. So then what do? We know that the next minimum has to be one of the two children. So we will compare 6 and 8. We will find out the minimum. So in this case it is 6. We will swap 13 and 6. So we know this is the next minimum. So we perform a swap here. Earlier we performed a swap here. So then what you get is, you get 5 here, 6 here, 13 here, 8 here, 10, 11, 12, 15, 20. So now, now there is nothing below this. So there is nothing further we need to do. And this is now in the form of a min heap. So is this fine with everyone? Just take a look at what we did and let me know if there are any questions. Is this fine with everyone? So maybe
Now-
I'll just give you, okay, good. I'll just give you one small example and then you tell me what are the steps you will do, okay? So let me just change the values here.
Ma'am, I have a small doubt now.
Yeah.
So before swapping, you need to take the highest value and then place it as the root node value, ma'am. And then you have
Before
to start.
swapping, you mean this step where
Yes, ma'am.
you take the, you take the last child in the whole tree. So you traverse in this direction, like left to right, left to right, left to right, and the last child that you see here, you're going to delete that and put the value here. I mean, just blindly replace it there.
So it should be the last, not
It should
the
be the
highest
last.
value.
No, because the reason we are doing that is because we want to maintain the heap structure. If you delete any other node, you are violating the complete binary tree property, because I cannot create holes in between. I only have to delete from here. So earlier what we were doing was, we were maintaining the parent child relation, but we were not maintaining the structure of the complete binary tree, and that's why the only node you can actually delete so that it still remains a full binary tree is this.
Yes, ma'am.
Okay,
Thank you.
good. So if that is clear, then let's say there are n elements. I have n elements in the heap. Then let's say I perform one heapify operation. So this is the heapify function. Then how much time does it take to make it into a heap? So what we are doing is there is a violation at the first level. We are swapping with one of the minimum. Then there is a violation that happens at the second level. Then we swap with the next level. Then there's a violation at the third level and so on. So how long can this series of violation be? It can be the height of the tree, right? Because every time we are percolating it down, the violation sort of bubbles down, 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 and so on. Finally, there is no violation. So what is the height of the tree?
Labels like
Levels. So if there
yes.
are n vertices, then what will be the number of levels?
Oh,
So let's take small
I mean to
n.
say generation. You can say like from root how far it is. Like how many generations are there?
Yeah, exactly. I
Hmm.
understand. So you are saying like this is your level 1. You are saying this is level 1, this is level 2, this is level 3, this is level 4. Okay.
Yes, yes.
Yeah. So in this case, you're going to take 3 or 4 um, many swaps. Okay. But in general, let's say in
Not swaps. That is the height of the tree.
yeah, the height of the tree. So my question is, if you have okay, let's say if the height of the tree is n. For now, let's assume the height of the tree is n. Then how many nodes can be there? What is the maximum number of nodes you can have in a tree whose height is n? At first level you will have 1, at second level you have 2, third level you have 2 square, and so on up to 2 to the
Yes. So we can find it some
yeah,
from geometric progression.
yeah. So in this case okay, maybe I'll do it like this. So you have 2 to the 0, 2 to the 1, 2 to the 2. Okay, so the total number of um, vertices you have is the sum of this. So this will be 2 to the n plus 1 minus 1. So in general, if the height of the tree is um, I'm basically trying to say there is a relation between the height of the tree and the total number of nodes that there can be. So if the height of the tree is n, then the number of nodes that you can have is something like log n, right? Is this fine? So if you have height as n plus 1, then the number of nodes were 2 to the n plus 1. And if the number of nodes is n, then what will be the number of nodes? That will be log of that number, right?
Maybe I didn't understand this. Like we find the sum of this series is equal to this one. Then after that, what are you saying?
Huh. I'm saying that if you have height n plus 1, then this is the maximum number of nodes you can have.
Okay.
So now I'm just writing this number as capital N. That is, I know that the total number of nodes is
Okay.
capital N. Then what is the height in terms of N?
In terms of capital
In
N.
terms of capital N.
What is the height?
It's something, it's log N, right? Around, I mean,
How?
yeah, I'm just not worrying right now about the constants, but something like log N, right?
Okay.
Okay, so that means how many operations are we taking? The height of this tree, if there are n many nodes, then the height of the tree is log n. So how much time are we taking to do the heapify operation?
Order of log n.
Exactly, we're taking something like log n time. So the heapify runs in. Okay, so what does that mean? That means I can perform this. So I can perform this delete min operation in order log n time. Okay, now the question is, I want to decrease decrease the value of some of the elements. Then how do we do that? So by decrease I mean, let's say somehow, so you are continuing your exploration and you find a smaller path. So initially, let's say there was a path from A to B that was of length 10, but now you explored this C which was at a distance of 3, and then you discover a smaller path like this. So this 10 needs to be updated to 7, right? So this 10 now becomes 7. Okay, is this fine with everyone? What do we mean by I mean, why 10 is changing to 7? Okay, maybe forget about the connection right now. Just think of this as an operation that you want to perform. Just we'll see the connection to the shortest path later. Let's say maybe instead of maybe instead of maybe 12 gets updated to 7. Then what will you do? Is this a heap now? Is this a min heap now? Is the question clear?
No, if it is 7, then no.
Exactly. If it is 7, then no, because now this parent is larger than the value at the child. So what do we do?
Yes.
Huh. So now what do we do? We'll do something similar to what we did earlier. We'll do like we'll do another heapify. So what you can do is you can compare this 7 with the parent. Um, okay, and then swap these two. So now 7 comes here and 10 comes here. So this part is fine. So the bottom part is now satisfying the property of min heap. But it can also happen that this value 7 is now smaller than the value here. So if, let's say, instead of 3 I had a larger value, or let's say maybe instead of 7 let me write 2, that is probably better. So I have 2 here instead of 12 now. So then what we do is we are going to swap it like earlier, because this is a violation, so we will swap 10 and 2. Now 2 comes here and 10 is here. So this bottom part satisfies the property of a min heap. But now there is another problem here which could happen. I mean, because the tree is like large, you could have problems up there. So then what do? You again do the same thing. You compare it with the parent. If it is smaller, then you swap again. So then 3 comes here and 2 comes here. So the previous operation that we did was like percolating down. You had created a violation here, then you started swapping with the bottom one, and you kept on percolating it down and down until the violation vanishes. In this case, when you decrease the value of the element, what you can do is you can keep on updating it by comparing with the parent each time. So you're percolating it sort of upward, you're bubbling it upward, and eventually you would have removed the violations. So again, how much time does this take? So how much time will it take? So maybe it started from here and you went upward all the way up to root. So how much distance is that? That is same as the height of the
Order
tree,
log n.
which is order log n. So again, if you do decrease key operation, then you're going to spend order log n time here, and this also takes order log n time. So this becomes order log n, and yeah, and that gives you, so that okay. Okay, so one thing that I probably, yeah, so one thing that I probably did not do in the previous calculation was, it was a very loose calculation, but um, yeah, but what you can actually say is that uh, every every edge is going to be visited at most once. It can happen that when A is visited, you looked at these two. When D is visited, you looked at all the other edges. So essentially, if you look at the whole run of the Dijkstra's algorithm, every edge is going to be visited exactly once or at most once. So that means the number of these comparisons you made, whether to update it or not, overall is bounded by m. So if we do this kind of calculation, what we're doing is you're doing n times a loose bound of n here, so which gives you n square. Okay, but what I'm saying is, instead of doing a loose analysis, I'll look at the whole run of the algorithm and see that actually none of the edges going to be visited twice. So that means every edge is visited once, hence this operation is done at most m times, m where m is the number of edges. Is this fine with everyone? So overall, in the overall run of algorithm, this operation happens m times, where m is the number of edges. Is this making sense? Is there any question about the comment about this observation?
Yes, ma'am.
Hmm. Uh, okay. So basically, what we're saying is, when we analyzed this earlier, we analyzed in a very loose, in a very trivial, I mean, very, very obvious way, that we looked at the number of runs and we upper bounded this, which was a bound of n minus 1, and then multiplied this, which became n square. But what we're now saying is, oh, look, you don't need to, like, you can actually do a better observation, a better, um, I mean, a better analysis by looking at how many times we are performing this operation throughout the run of the algorithm as a whole, and that, we said, can be at most the total number of edges, and that's why from n square we are bringing it down to m. So we are actually performing this m times. So m times decrease key will give you m log n, and n times we are deleting, because every vertex we are visiting, each time we are visiting a vertex, we are removing it, updating the values, taking the next minimum vertex. So this will happen n times. So this is the total runtime of the algorithm. So is this fine with everyone? How we got log n here and the whole runtime of the Dijkstra's algorithm if we implement it using heap sort. Using heap.
Yes.
Okay, good. So now the question is, does that mean कि if I do an implementation by heap, it is always going to be better than array? Will you always use heap? Just compare this versus order n square.
ये एक्चुअली उन्होंने क्या लेटर पे लिखा होता ना लीव
Uh,
and the login thing is much better, I guess.
okay, so you are saying that n log n is definitely better than n square, but now we are comparing m log n with n square. So what is the maximum value of m that is possible? What are the maximum number of edges in a graph?
If it is connected, then like n into n minus 1 divided by 2.
Exactly. So this is like order n square. M can be at most
Oh,
n into
yes.
n minus 1 by 2. And now we are comparing m log n versus n square, which is n square, order n square log n.
Yes, yes.
Yeah, versus order n square. So if m is very large, that means if the graph is very dense, there are so many edges in the graph, then actually this is worse. Then you
Hmm.
what you do is you just use the array and get done in quadratic time. But if m is small, if the graph is very sparse, so if graph is sparse, that is, let's say m is less than um, n square by log n. If it's smaller than that, then what will happen is m log n will always be smaller than n square. So then it's a better idea to use min heap. Then you are doing some saving. Okay. So is this
Oh.
is okay. So are there any questions about anything that we saw just now? Anything about the heap, the heapify, and delete process, um, and the analysis?
No, ma'am, it's clear.
Okay, good. So, uh, yeah. So actually, this is not the best that we know. Um, you can even do better. There's something called Fibonacci heap, which I'll not talk about. I'll just let you. If you are interested, you can take a look at Fibonacci heap. If you do that, I think this delete mean remains the same. It remains order log n, but you can bring this down to order 1, which is an amortized analysis. So then you can further improve this, but we'll not get into it. But if you are interested, then take a look at this. Okay. And yeah, and then the next thing I want to mention is that um, we talked about binary heap, where we said that you have a node, it will have two children. That's a binary heap. Every node has two children. Okay, but I can also talk about a ternary heap where every node has three children, and so on. And you can generalize the definition of a complete ternary tree. Yeah, you can generalize the definition of complete ternary tree, saying that every level should have a power of 3. So here you have 1, 3, 9, then 81, uh, and so on. And then you can also define complete ternary tree by just saying that if you are removing, you just remove from the bottom rightmost part, and there should be no holes in between. Okay, and you can define min heap property in the similar way. You can say that the value at parent should always be smaller than that of the children. So if I have a 3 here, you can have 9, 8, 11, and then for each of these subtrees you have the same property. The value of their children should be larger than that of the parent. You can generalize the whole thing. So we saw binary min heap. You can, in general, you can define a k-ary min heap, where instead of 2 you have k children. You'll have k children like that. And then you can try to see how do you perform the delete min operation, how do you perform heapify operation, and basically everything that we saw. You can see, are we doing better, and if we are doing better in terms of time, how much better are we doing. So this is something you can try. So take this as homework. So we define the structure, and then okay. So does the question make sense? Is this fine? This is fine, right?
Hmm. Yes, ma'am.
Okay, okay. So now the next question is, we did the whole thing, right? We did the analysis of Dijkstra's algorithm, and we saw how to perform these operations. But one thing that we did in the process is we assumed that we have a heap. So in the whole process, if you remember, I gave you a heap, and then we were performing these operations dynamically. So then if I want to delete something, how do I delete? If I want to decrease key, how do I delete? How do I decrease? But the question is, who gave you this heap, or how do I, in order to do all this, first thing is um, I need to create this heap, right? So in the whole process, we assumed that there was a heap. Is this fine?
Yes, ma'am.
Okay. So what we'll now do is we are going to see how do you create heap. Okay. And yeah, before that we're going to let's look at some interesting properties about the heap. Okay. So first one question is, how do I represent heap? So let's say I don't want to do all this pointer business. You can create like pointers, and yeah, you can define a tree like that, and then keep on traversing and so on. But I want to use an easy data structure. So what you can do is you can implement a heap simply using an array. Okay, so what I'll do is I'm simply going to represent it using an array. So if I tell you, maybe let's say I take the same heap, let's say this one, maybe I'll just copy this. Okay, and maybe I'll just clean up. This is 3, 3, 10, 12. This is the heap that I have, and I want to represent it in an array such that I can always find its children easily. I want to be able to do it quickly. So how do you do that? So I just want to store these numbers in an array. Any thoughts? Okay, so one obvious thing is, note that whenever we read the values of the heap of this tree, we read it like this. We read from left to right, go to the next level, read from left to right, go to the next level, read from left to right, and so on. So then what I'll do is, I'll just follow the same steps. So let me write it here. So 3, what are the next values if you read it in that fashion?
10,
10,
5,
5,
11,
11,
12,
12,
6,
6,
8,
8,
15,
15,
20,
20,
13.
13. Okay, so we just read the whole thing from left to right and then we got an array. Now the question is, I give you I'll give you one note. Let's say I give you 5 and I want to find its children, which are 6 and 8. Can I locate it quickly in this array? Let's say I'm at 5. Where are the children?
Not easy to get by array.
Okay, but if you observe something, these are not arbitrary positions, okay? There is something happening here with respect to the numbers. So if this is I, if this location is I, then the value of its children is something special.
Greater than I.
Uh, First we are writing first generation, second generation. Yes, there is some rule.
Yeah. So maybe look at some examples and try to figure out within this, try to see some.
Yes, ma'am. We can say like first number is three. Then there will be two children. Then, then next two will be the children of first parent of second generation.
Yeah. Yeah. So let's look at some examples. If I look at 3, whose index is uh, whose index is 1, then where are its children located? So if I look at index 1, the children are located at index 2 and 3. Okay, if I look at 3 for example, the children are located at location 6 and 7. Then maybe let's say I look at 4. Where are its children located? Where are the children of 11?
8, 9.
8 and 9. So do you now see some property what's happening between these values and these values? Okay, between these two you agree that if this is j, then this has to be j plus 1 because you are writing consecutive.
Ma'am.
Let's say two times.
Exactly. So if the parent is at location I, it is at index I, then the left child is at index 2i and the right child is at index 2i plus 1. Okay, so this is one nice thing if you about using arrays, that you definitely know that where its children will lie. And now if you look at this, maybe you will be able to appreciate why we defined it like this. Why did I define it like a full binary tree or a complete binary tree? Because I don't want to keep gaps here. If I do that, then my array positions will be disturbed. That's why I always wanted the previous levels to be full so that I can access it like this, using this observation about 2i and 2i plus 1. So one thing is you can formally try to, so right now what we did is we just looked at some examples and then we said, oh look, this is like 2i, there is some pattern that we observed. We said left child is at 2i, the right child is always at 2i plus 1. But how do I prove this formally? We in this course, you might have seen at various points that whenever we say something we actually have to prove it. So this is something you can try out. This is an easy exercise to prove why this happens in a heap. So take this as another homework and try to prove this by writing uh, by doing all the calculations. Okay, so so now the whole idea of representation is clear. There is another very beautiful um, thing that happens um, about this heap. Okay, let's say I give you a sorted array. So it's clear that from a heap, from a tree like this, I can convert to an array. From the array, can you get back to the tree? How will you do that? So you know that this is always the root, right? So you will write 3 here. Then you know its children are 10 and 5. So you write 10 here, 5 here. Then the next children are going to be that of 10. So basically you are just writing it from left to right at every level. Is this clear how you go back from array to tree? Okay, good. So now let's see a very nice example. Let's say the array that I give you is like this. It is 2, 4, 7, 10, 13, 14, 18. Okay, so this is the array that I have given to you, which is what is special about this array? Is this any arbitrary array, or is there something nice about it, about the values, the way they are arranged? Um,
Is it in ascending order?
exactly. Good. So this is a sorted array. I've given you a sorted array, and now what you will do is you tell me what is the heap, what is the tree associated with it. So 2 is going to be the first, the root, then
4 will be left child,
4 will be left child,
7 will be right
7,
child,
okay,
um, 10 will be left child of
yeah,
4, 13 will be right child of 4,
13,
14 will be left child of 7,
14,
and 18
18.
will be right child of 7.
Good. So basically what we are doing is we are reading this from left to right, starting to fill it like this. Okay. So now what is interesting about this heap? Does it satisfy some nice property that you have already seen?
It is a min heap.
Exactly. This is a mean heap. So what that means is you can again try to prove this formally. You can intuitively see why this is happening. It's happening because the minimum element is always coming at the top. The next two minimum are coming here, and therefore their children will always have values larger than, or at least as large as the parent. So this is an intuitive reason. You can also try to prove that if I give you a sorted array, then the heap corresponding to the array is a min heap. And suppose let's say I would have given you this array in the descending order of sorting. Then if you convert it into a heap, what I mean, what will be special about it?
Last element will be the root node.
No, you just follow the same steps. Okay, I mean, just follow this. So whatever is written here, let's say there's a very large number here, maybe
Yes, ma'am.
let's say it is like 18, 14, 13, 10, 7, 4, 2. Then you get 18, 14, 13, 10, 7, 4, 2. What is special about this heap?
It is a max heap.
It is a max heap. So if I give you in the descending order of sorting, you will get a max heap. Okay, so you can try to prove this again. So now the nice question here is, you have seen several sorting algorithms, right? We give you input to use an array where elements are arranged in random order, and you have to sort it. So then you saw several sorting algorithms. So you saw something like you saw selection sort, you saw insertion sort, bubble sort. What is the running time of all this? What are the running times of all these algorithms? Okay, maybe I'll just think about it. I'll just get my charger. Okay, so what did you come up with? What are the answers?
For selection sort, is it big O of n square?
Yeah, that is actually correct. So for the first three, for the first three algorithms, it takes n square time, and for the other two, it takes
N log n.
n log n. So let me write that. So for these three, it takes order n square time. For the remaining two, it takes order n log n time. Now, one thing that is one thing that's a like drawback for merge sort is that of space. So I mean, clearly in terms of running time, n log n is better than n square. So we are only looking at these two algorithms. There is one drawback or the other with respect to both the algorithms. So the drawback of merge sort is that you need space for merging. So you need an extra, you need an auxiliary.
Extra required.
Yeah, exactly. You need extra space. In terms of for quicksort, you don't need order and space. Basically, you don't need any space. But the drawback is that it's a randomized algorithm, and it only I mean, in the worst case, it can do something like order n square time. If every time the pivot that you are choosing is like the smallest one for the remaining array, then you can end up doing as bad as n square. But if you do a randomized analysis of this, then you get then you get something like an n log n average running time. Okay, so one thing that you can do with these heaps is sorting of arrays. So I'll just give you a random array and you're going to sort it using heaps. This is called heap sort, and this is a very nice algorithm because it does not use any extra space and it runs in time order log n. And this is not a randomized analysis. It's a very deterministic algorithm and a very simple analysis of why it does this in n log n time. So maybe I'll just spend some 10 minutes describing this, then maybe we'll move on to the other algorithms. Okay, so I just want to give you an idea of how this works because the operations that it uses are something that we have already seen in the previous discussion. So let's see how to do that. So maybe let's take the same maybe just take some example and um, okay, okay, maybe I'll just give you a brief idea of what happens here. If there's more time, maybe we can get into the details. So what you'll do is you have an array like this that is given to you which is not sorted, and then we are going to build the heap. Okay, so how do we do that? First you take the first element that you have, which need not be the minimum, you make it your root. Think of it. So I mean, we'll visualize this algorithm in terms of the heap, then you will see in the code how do you implement it using arrays, which is just a translation from the node to their children and so on, which you anyway know how to do in constant time. Okay, so yeah, so additionally what you want, your sorted if the array is sorted, one additional thing that you want your min heap to satisfy is that the left child should be smaller than the right child. So in this case, if I write 5 and 10 here, then you read it left to right, you read it as 3, 5, 10, which is already sorted. But if you write it like 10 and 5, which is perfectly valid for a min heap, then if you read it from left to right, it's not sorted because this left child is larger than that of small child. So there's just one additional thing that you need to make sure when you are when you are like making it, I mean when you want to sort the array, you always want to make sure that the left child is smaller than or equal to the right child. So how you will do it is you will do it iteratively. So first you only think, first there is nothing, initially there is nothing, you take the first element, make it your root, then you take the second element and you'll make it a child of this because between 3 and 10 3 is smaller. Then you take the third element and now the question is between, so initially you have this 3 and 10, now you have 5. So between 3 and 5 is larger, so it's clear that 5 should be a child. The question is which child should it be? Should it be the left child or the right child? This is one more query that you do. You know 5 is smaller, so then you're going to swap it. Make 5 and 10 your 2 children. Then you look at the next element, which is 11, and and then you're going to find the correct place for 11. So each time you're going to add it. Maybe I'll do it here. Okay, I'll maybe create some space here. Okay, so now 11 goes here. Okay, then you read the next element, which is 12, and 12 goes here, and then you look at 6, but 6 can't be here because this violates the property of min heap. Then what you do is you use your heapify function. What does heapify say? It says that there is a violation here, you're going to go all the way up, and make it clear. So how does it proceed? You're going to check this with its parent, there is a violation, you swap. So then this becomes 6, and this becomes 10. 6 and sorry, what was the value here? 10, right? 10. Okay, now this, if you read this, at every point whenever I'm adding, it is always sorted. So now you have 3, 5, 6. Okay, maybe not at this stage, you'll have to do some more cleanup for that. So right now what happened is 10 is on this side, which does not um which violates the definition. So then you can you can do something like you can delete this 10 and put it maybe put it at the top and then percolate all the way down. So I'll not get into the details right now, but but I just want to give you the idea that there's something, a structure like an algorithm like this exists. You can read it out and try to see why this works in n log n time. So if there is time at the end of this tutorial, then maybe we'll get into it. But I just want to cover a few more things before before we get there. Okay, there are lots of applications of using heaps. I've listed at least 5 of them. If there's time, maybe we'll get into it, but let me just state the questions for you and you can try this out. It should not be very difficult to come up with the algorithms. So what is the dynamic median? I'll just spend like 2-3 minutes in explaining the question. We'll not solve it right now, but yeah, please think about it offline. So what is a dynamic median finding algorithm? So what is a median? If I give you like maybe I'll just write some random numbers: 7, 3, 2, 4, 5, 8, 9. If I give you some random some list of numbers, then what is the median of this? So how do you find the median? You're going to write it in the sorted form. So what is the sorted form? 2, 3, 4, 5, 7, 8, 9. Now in the sorted form, find the middle position, which is in this case this. There are exactly half same number of elements, so the left and right. And what is the value at the middle position? It's 5. So 5 is the median. Okay, but
Yes.
good. So let's say there are in this case there are odd number of elements, so we know there is a median, which is 5. But let's say I delete this, so now this is your array. So now how do we define the median for even number of elements? Okay, so there are different definitions that people work with. One way is that you fix, either you fix the smaller one or the larger one. So in this case you can either return 4 or 5, but fix it. Or you can also define it to be the average of the two. So you can define it to be 4 plus 5 by 2, which is 4.5. So any of these definitions is fine. Okay, so the question is, I want to find, let's say I give you maybe for simplicity, let's say I give you an array and you want to find a median. So how will you do that?
Sort the array and then find the middle value.
Exactly, you can sort it and you can spend order n log n time to sort it, and you can find the median. So sort and look at the middle position and return and find median. So this is what you can do. Okay, In fact, you can do better because you don't need the rest of the elements to be sorted. So there are, if you're interested, you can look into, maybe Corman has some nice examples of doing better algorithm than n log n for finding medians. You can take a look at it if you are interested, for median finding. Okay, but the point I want to make here right now is, let's say that the array is dynamic. So what do I mean by dynamic? I don't give you all the values at once. Okay, I'll keep on adding. So maybe I'll add in one more element, say 10. Now you have to tell me in this array, what is the median. Then once you do that, I'm adding one more element. So elements keep coming. So this is not a fixed array. Every time the element comes, you have to be ready with the median. So it's dynamic in that sense. So then what will you do? What is your strategy?
I'm sorry, but could you please repeat the question?
Yeah, sure. So what I'm saying is, if I give you the elements beforehand, these were the elements, then you know how to find the median. You said you will sort them and find the middle position and return the entry at that. But
Yes, ma'am.
now the array is dynamic, meaning each time I keep on adding elements. So then now I add 10 and you have to tell me in this array what is the median. Then I'll add 12 and then you have to tell me in this array what is the median, and I keep on doing that. So each time I'm keeping on adding something new to the array, and you have to keep telling me what is the new median with respect to the new array. So it's dynamic in that sense. So then what will be your strategy? What is the most obvious thing you can do? Each time I add the new element, you can sort again.
Yes, ma'am.
So how much time will that take? If I add n elements, each time I'm giving you n elements, you are spending n log n time in sorting that. Is this okay? So I add one element, one new element, and now your idea is you will sort it and return median. This will take order n log n time. If I do this k times, how much time I'll be spending in total?
K into n log n.
K into n log n. Order k into n log n. In particular, if k is n, then you are doing order n square log n.
Square log n.
Okay, so question is, can I do better? I don't want to spend so much time because there is already some work that I've done, right? There is already some part which is sorted. Now I'm just adding one new element to it. So can I do something better rather than having to sort the whole array again? You have seen something similar to this in one of the sorting algorithms.
Ma'am, can we use insertion sort now?
Exactly. You can use insertion sort. So then you will do in order in time. You are just going to find what is the correct position of this and keep, I mean, push it there and then push all the remaining values to the right. So you can do insertion idea. So using insertion idea, you can get it to order n.
Order.
So then what is the better bound that you get here? You will improve this to order n square, because you are doing k times, so you are doing order k times n, and if k is n, then you are doing order n square. Okay, now now the question is, I want to do it using heaps. So imagine that, just convert your arrays into heaps, and I want to do a median finding algorithm. Then you can actually do this in order n. The dynamic median finding you can do in order n log n using heaps. So okay, maybe I'll not it's a very interesting algorithm, but Yeah, maybe think about it first. If I have to give you a hint, then maybe I'll say that you have to maintain two heaps. You have to maintain two heaps which need not be of the same kind. Both need not be min heap or both need not be max heap. But think of how you can use these to come up with a median. Okay, so that's the hint. I'll leave it, but do try this out. This is a very interesting example, and if you can solve this, that means you have actually understood the whole um, concept nicely. So hint is that maintain two heaps. And if you want to arrive at this, one thing you can do is play around with some examples. So just take one sorted array and see how you can maintain the heap, and using that, where do you see your solution? So just take some toy examples, play around with it, and hopefully you'll see what is the intuition behind this. So just try this out. uh, the other thing you can try out is I give you two min heaps and you have to merge them into a single heap. So this is like a merge algorithm that happens in merge sort. Two sorted arrays and you have to merge them. So similarly, you have two heaps and you have to merge them. So think about this. And if you're familiar with stacks and queues as data structures, you can also implement those using heaps. So just try all of them. All of them are interesting examples. But I want to discuss in the remaining 20 minutes we have another data structure. So we saw one data structure which is heap, um, and the other data structure that I want to discuss is union find data structure. So before that, let's do the same thing that we did earlier um, for the um, for the Dijkstra's algorithm. What we did was, you did a very whenever you come across an algorithm, first thing you do is you find the worst time analysis for it using trivial data structures that you can. Then the next question is, can I do better? Can I do better? These are the next questions you ask. So remember the Kruskal's algorithm. Kruskal's algorithm is that, maybe let me just take a tree here. So let me just take a graph, and just to remind you quickly what Kruskal's algorithm was, what we did was, you take the first minimum edge. In this case it is 1. Then you form this CF edge. You take the next minimum edge, so which is here 2 and 2. You can take either of them. Then let's say I take this and I add it to my tree. So this is now removed. The next minimum is again 2, and the next minimum is 3. Again there are two choices, one is this, one is this. Let me say I take this. Then the next minimum is again 3, but I cannot take it because if I take this, then it forms a cycle which violates the definition of tree. And again I can't do this because this forms a tree, can't do this because this forms a tree. So if any of you is not familiar with this, we discussed the same example last time in the previous tutorial. So if you want to take a look at it, you can do that, but I won't go slowly into it because that will take a lot of time. So next minimum that you can take is 7, and again I can't take 8 because that will form a cycle which I don't want. So then I'll take I'll take G, and I get my minimum spanning tree. So this is how Kruskal's work. It takes the minimum edge as long as it does not form a cycle. Now the question we did not answer last time was, how much time does this algorithm take? So let's look at, so how much time does this take if you want to, I mean, you know the algorithm now. So how much time do you think it will take? Any guess, like any wild guess?
Maybe n square. I'm not sure.
Okay, so let's yeah, so let's see how it works. What are the operations that we do? One thing is, you can assume that we have sorted all the edges, because anyway we are finding minimum edge each time. So you sort the edges. How much time does sorting take? If there are m edges, it will take m log m time. Okay, now once the edges are sorted, what I'm doing is I'm picking up the minimum like we did. Then you keep on picking minimum as long as it does not create the cycle. If it creates a cycle, I need to discard it. So I need to check whether it creates a cycle. So how do you check in a graph whether the given edges create a cycle? We've done this question in, I think, previous to previous week, when we looked at graphs. So what you saw, two algorithms, BFS, DFS. You can use either of them. So checking for cycle. So this will take something like order n time. So yeah. So this is something you can do with a BFS or DFS algorithm. Okay. So the question is, this sorting is a one-time thing. Sorting I've already done. But this process of checking for cycle is a repeating process, right? Every time I'm adding an edge, I have to check whether it forms a cycle. If it does, then I have to discard it and look for the next minimum edge. If it does not, then I'm going to add it to my cycle. So how many times are we checking this? So so notice that in the worst case, it can so happen that I have to go through all the edges. That every minimum edge that I'm picking is creating a cycle with the current tree I have. So in the worst case, maybe I have to look at all the edges and see whether it forms a cycle or not. So if I do a very loose analysis, this will be something like order m log m, which is for sorting, plus m times n, because I'm checking for cycle every time I take a new edge. There are m edges, for each of them order n time. So this is like loose analysis of what we for the Kruskal's algorithm. So the question is, can I do better? And the answer is yes. And how do we do that is again the same set of steps that we saw earlier. So for doing that, first you need to identify what are the operations that your algorithm performs. Once you know the operations that it performs, the question is, how do I design my data structure so that these particular operations can be done efficiently? It's possible that maybe there is some other operation which is difficult to do in the new data structure, but I don't use that operation for my algorithm. So it doesn't matter whether the rest of the operations are going to take more time. I just care about these particular operations. So let's define what are the operations we are doing. Sorting is something we are not looking into right now. You just use your merge sort or some or heap sort algorithm for that matter and find the sorting. Once the edges are sorted, what we're doing is we are essentially checking whether, so you can think of these as components, right? So initially, let's say at this stage, maybe let's say we are at this stage where I have added CF, AB and AE to my tree. So then this is a tree by itself. This is a connected component. You can go from E to B, A to, and so on. This is a connected component and this is a connected component. But I can't go from C to B or something like that. So I have two components right now. Okay. And when I do this, when I add the next stage, which is 3, what happens is these two components are going to merge and they're going to become a single component. So this is the new edge. Okay, so this is the new edge that I added, and now this is a single component, right? This is a connected component. And now if I look at the next minimum edge, which is this, then what happens here is both the endpoints of the new edge are actually within the same component, and hence it's creating a cycle. Whereas what happened in the previous case was you had one component here, the other component here, and the new edge that you added was connecting one vertex of one component to the other vertex of the other component, and that's why it's not creating a cycle. So these two are equivalent definitions, saying that if you add one edge within a component, you will end up creating a cycle. So this is also some exercise that we have done, I think 2 or 3 tutorials earlier. So this follows from the definition of tree and connectivity. So one observation we made is that I'm going to maintain some connected components. Okay, and if the new edge um, has both endpoints within the same component, then it creates a cycle, and otherwise if the endpoints are in two different components, then it reduces the number of components by how much? If I add one edge, and let's say there were k components earlier, now I add an edge, then how many components do I have now?
K minus 1.
Exactly, good. K minus 1. And at the end of the algorithm, how many components do I want? Will it have? So the output of this algorithm is a minimum spanning tree, and tree is just one single component, right? It's a whole connected structure. So yeah, so initially you think of each of the vertex is your own component. So initially you have something like this: A is a component, B is a component, and you have how many vertices here? G, all the way up to G. You have, in this case, you have 7 components.
Components. So all the 7 will become a tree. They'll all be components of a tree.
Exactly. That's what's going to happen. So what are the two operations that we need? One operation is to check whether they are in the same component, right?
Yes.
So yeah, so this is what we call find. Find tells you whether both endpoints
Are in the same component.
are in the same component. And now there is one more operation we do, which is when I add the edge, I'm actually combining two components. So this is what we call union. This combines two components. So now these are the two operations I have. One is find, which checks whether given two vertices whether they are in the same component. Union, what union does is it combines two components. So find and union are the two operations that I want to perform efficiently. And let's again ask the same question that we asked earlier. So how many find operations will this algorithm perform? So what is the line just before this? We are going through all the edges. So in the worst case, for every edge, I'm going to check whether the two endpoints are in the same component. So let's say it takes like m many find operations. Okay, not exactly m, it's actually 2m, because for every edge there are, sorry, let me just admit somebody in the call. Okay, so that for every edge I'm checking I'm using the find operation on u as well as v. So there are two operations per edge. There are m many edges, so there are 2m find operations. And how many union operations do we perform? So recall, what does union do? Union takes two components, merges them by adding one more edge. So how many union operations do we perform? Okay, so the answer is n. You need n many union operation. Why is that? Because every time I perform a union operation, what I'm doing is I'm adding one edge. When I do union, I'm adding one edge. In a tree of in a tree with n vertices, how many edges can you have? Okay, so this is also something that we have done in previous week. So if you have a tree, you can also see in this particular example there are 7 vertices and there are 6 edges. You can prove this. If in case you don't know, try to prove this again, that if you have a tree with n vertices, then the number of edges m is exactly equal to n minus 1. So this is something you can try proving if you are not aware of this, or you can check out one of the previous lectures, tutorial or lecture. So in a tree there are n minus 1 edges, so every time I perform a union operation, I'm adding an edge. So how many union operations can I perform? I can perform n minus 1. So okay, so this is going to be the runtime of this. So the runtime of this is going to be the time needed for doing a find operation into 2m plus the time needed for doing the union operation into n, and then we will add this up. So let's see whether we can do better than this. And also additionally, I'm already spending m log n time in sorting. That is something we will again add up. So this sum is the total amount of time that will be the runtime of your Kruskal's algorithm. So now let's see how do we do this find and union operation. Okay, so okay, so okay, so maybe let's start with a very natural thing. So initially what I'm doing is, initially the graph that is given to you, all of them are a component of itself. Initially nothing is merged because the tree does not have any edge added. So now you have 7, okay, in this case I have more vertices. This is some other graph. So I have one component corresponding to each vertex. So how many components these are these? There are some 10 components.
10 components.
Right. So now when I say I do a union, what I mean by that is there is a parent associated with every vertex. Initially A is a parent of itself, B is a parent of itself, C is a parent of itself, and so on. Now when I do a union of AB, I'm going to update the parent of B to parent of A. So what will that look like? A is a parent of itself, but B is now a child of A. So now this is one component, and you will see in a moment why we are doing this. So let's say I do BC now. Let's say I'm doing a union of BC. Okay, then what we will do? Can someone tell what to do? What is the most natural thing?
C will become the
Child
child
of
of B.
B. So C will become the child of B. Okay, now if I want to check whether A and C are in the same component, then what will I do? Let's say I want to do find of A is equal to find of C. Then what will I do? How do we see whether it's in the same component? So notice that if they are in the same component, then their root will be the same, because if I'll trace back the like the ancestor of C. So firstly, the parent of C is B, then parent of B is A, and parent of A is A. So find of C will return A. And what is find of A? What is the parent of A?
A is the root node, no, ma'am.
Yeah. So A's parent is A itself. That's how we defined it.
Yes, ma'am.
So this is equal, and therefore we know that they are the same component. So basically what find does is it traces down your parent's parent, parent's parent, parent's parent until you finally reach a root node. How do you know it's a root node? Because it itself be its own parent. That is when you stop the algorithm. So basically what find of x will do is um, it will find parent of it will keep on finding the parent of x. So let me denote by pi of x the parent of x. So this is a recursive algorithm until x is itself the pi of x. In that case you return x. So this is a recursive algorithm that keeps on calling parents parent parents parent parents parent until it itself is its parent and returns that thing. So let's do one more, maybe let's do one more operation. Let's say I want to merge D and D. So I'm doing union of D and D. What does that look like?
E is the child of D.
A is the child of D. Now let's say I want to merge B and D.
So I'll apply find operation.
We will apply exactly. So we will apply find operation, and find of B is
A,
A, and find of D is
D
D
itself.
itself, which are different. So that means you need to merge
Must.
them. So how do
Yeah.
we merge? D becomes the child of B.
Okay, ma'am.
Okay, so now
Ma'am, so, for which two vertices you're finding that find, for those only are merging if they're not the same. Like they're
exactly,
not same component.
exactly. So
Yeah.
then uh, now if you look at this becomes a whole connected component, and any node in this connected component has the same root, which is A, because if you trace back you will eventually get to A only. So that is how you know that they belong to the same connected component, because their root will be the same. Okay, so this is very obvious way of implementing find and union. But what is the runtime of this? In the worst case, how much time am I going to spend? Has it got something to do with the height, like it was the case in the previous algorithms? Because let's say I want to find, I'm applying this find operation on E. Then how much time will it take? How many operations are we doing? We are tracing E's parent D, D's parent B, B's parent A, and A's parent A. So the length of this tree,
Wait, the tree.
the height of this tree, is the amount of time that you are spending on the find operation. But the way we are doing this find right now, we are just doing it blindly. So whenever they tell you, there is a union operation, we are just attaching um, attaching this with the node that is given. So it can happen that this height of the tree becomes very bad. It can become something like n, and that would say that find operation takes order and time, and so does the union. Um, so this is not what we want, right? That will be bad for our algorithm. Um, I want to spend less time. So can I do something clever instead of just blindly attaching the parent to, the child to the parent? Can I do something better so that the height of the tree is minimized? Every time I do this union operation, I don't want to increase the height of the tree by too much. So where can I attach this? Instead of, let's say, adding this edge here, I want to add it to some other node so that the height does not increase by too much, but the ancestor, the the root remains the same. just try out some examples. Maybe which node do you see where I can attach, so that the height of the tree does not blow up by much. So what will happen if I attach it to the root itself? So I have a tree like this. Let's say for now I have a tree like this. Okay, now if I attach my D here, I'm only increasing the size. I'm only increasing the height. If I attach it here, I'm decreasing the height by 1. If I attach it here, I'm decreasing it by 2. That means I want to attach it as up as possible, so that it does not blow up the height. So basically what I want to do is I want to directly attach it to the root only. Is this okay?
Yes, ma'am.
Okay. So now the question is, how much are we saving by doing this? Okay. Another question is, if let's say I have at some point I have two trees that are going to be merged. So let's say I have one tree that looks like this. Okay, the question is not how we came up with this. Let's say I have this. Let's assume these are the two trees I have. G H I. So now I want to perform a union operation of these two. So the question is, who should go to, I mean, which one thing we know is either you should attach this root to the root of this, or you should attach the root of the first tree to the root of the second tree. The question is, which would you do? Although
Root
it's
the second tree to the first tree, ma'am.
exactly, so you always take the shorter tree and attach it to the longer tree, because if I do this, if let's say I do this, then what is the height of this tree? I'm increasing the height by 1, right?
4.
In this case, so initially the height is 4, but when I do this, the height becomes 5, right?
Yes, ma'am.
So I'm saving by 1 if I always take the smaller one, and so always take the smaller tree or shorter tree, and attach it to the longer tree. So it can so happen that both the trees are the same height. In that case, you can do either. You can attach whichever to whichever. It is fine. Now the question is, how do I keep track of the height? Because I don't want to every time go and calculate it. So what you do is, you keep one more, use some extra memory, and every time you keep the height of the tree stored in it. So initially, let's say this is at level 0, this is at 1, this is at level 1, 2, 3, 4, or okay, maybe I think you should do the other way around. Sorry, you should write 0, 0, 1, 2, 2, 3, 0, 0, 1, so that when you look at the roots, you know which is the smaller tree. In this case, this is 1, this is 3, so you know that this is the smaller tree, and therefore you should attach this to this. And yeah, the moment you do that, it's going to change some of the values. So now this is no longer 1, this is 2, and these are 1, 1. So so you are going to update it like that. So one thing that we are doing is additionally keep, or let's say store, the heights of each node. So this is to keep track of whether the tree is shorter or longer. So this will take some time. That will also add up in the total running time. Okay, but um yeah, maybe just I mean, if what we are doing is clear right now. So initially what we did was we blindly made one node the parent of the other. That was bad because it blew up the height by too much. Now we are doing something careful. Now we are keeping track of the height of the tree and choosing then to do what. So just to make sure that we all are on the same page, maybe take this example and run it one after other, and let's see how does this work. Sorry. Okay, so let's do this one by one. So now if you do union of AB, what do you get?
B is the child of A.
B is the child of A. Then you do CD.
D is the child of C.
D is the child of C. EF.
F is the child of E.
GH.
H is the child of G.
IG. Okay, now is the interesting part. So let's say you do a union of J and G. So we said, how do? We said we will only merge the roots. Either G becomes a um, child of I, or I becomes a child of. Because what are we doing? We are using the find operation. Remember, whenever I say G and J, you're going to find the parent. I mean, the root of G, which is G itself, and the root of J, which is I, which are both different. So we are going to do a union operation. So either I becomes a child of G, or G becomes a child of I. So which one do we do?
No, we can do either of
You can do
them.
either. So maybe let's say I do this. Okay, so now the height of the tree has increased by 1. And next thing, so we did this G and J. Now let's say we do H and F. So H is in a different component, H is here and F is here. So what do we do now? The height of this tree, what is the height of this tree?
2,
2, and the height of this tree is 1.
1.
So
So
the
we map the smaller tree to the bigger
to the
one.
bigger one. So this is how we change it. So we did H and F. Now let's say we do A and C. So A is in this component, C is in this component. Both are of the same height. So let's say I do, or let's say I do the other way around. So let's say I do this. So AC is done. Now I want to do DE.
Take A, B, C, D and then combine to the bigger tree.
Take A, B, C, D and okay. So whenever we are combining the root. I mean, root of D. So root of D is C, and root of D is, sorry, D and D, right? Root of D is C and root of E is G. So we have to combine C and C versus, I mean, C and G together. So both are of the same height. So it does not matter, right?
Yes, ma'am.
So let's say I do this. Okay. Now if you notice, um, everything is already one component. Every node's root is G only. There's no other root that is remaining. So for the rest of the operation, so let's say G and B, if you want to perform, G's root is already G, and B's root is B goes to A goes to C, C goes to G, so and G goes to G. Both of their roots are G only, so there's nothing to there's no need to do a union operation. Same with I and J. I's root is G, and J's root is also G. So there's nothing to do here further, and we already have one connected component, which is what we wanted at the end of the story. So now the question is, how much time does this take? Okay, so what does union do? Union uses two find operations. And then once you know the find, you are just adding one edge. Adding one edge is not taking time. Only time you are spending is in finding the root, and merging is just one adding one pointer. So if you do a careful analysis of this, you'll see that by doing this, you're always ensuring that after doing n operations, the height of this tree is going to be bounded by order log n. So the height of this tree cannot be more than n if you are doing n many operations. So just in this example, what is the height of the, how many components we had? We had 8, no, we had 10 components. But finally, what is the height of this tree? The height of this tree is, okay, maybe this is a very small example, so you can't maybe relate, but the height of this tree is finally 3, which is much smaller than 10. So there is a proof for this. You can prove that if you do this, if you do it this way, then your find operation is going to take order log n amount of time. And therefore, what is the time of union? How much time will union take? Recall, what does union do? It just finds um, the roots of both the nodes and then just adds an edge. So you are basically just calling find 2 times. So it's still going to be order log n. So if I plug this now, okay, this is a proof that you can check this proof in, you can find this in Dasgupta, or even I think Katie should have it. So okay, so just check this. If you're interested, check this. It's not too hard to see, but right now I just want to show you that we are doing better in terms of time. So let's go back to our algorithm and let's plug and place our values here. So find is taking order log n time, and union is also taking order log n time. So what is the total running time here? Can someone quickly tell me? We're doing m log n plus okay, sorry, n is m for us here because the number of um, I mean, okay, no, this is fine, sorry to confuse. Okay, this is n, this is still n. So how much time did we end up spending? This is just m log m, right? Is this fine with everyone?
Yes, ma'am.
Okay, and you can even write this as m log, m can be order n square in the worst case. So this is order m log n again. And so if you use this find union, this data structure is called union find data structure, the one that we saw just now. So if you do this union find implementation, you are doing in time order m log n. And if you do the trivial algorithm that we saw, then we said it was something like order m log n plus n square. Okay, so again we have the same question. Is union find better?
Yes, ma'am. Union find is better than trivial.
Okay, that, yeah, that is correct. So another thing is that you can actually do even better. So the union find that we saw just now was just doing a balancing in some sense. You were doing a height balancing of the tree. Actually, there is something called path compression, where what you do is additionally, just to give you an idea, let's say we were here, right, in this stage, we said C's parent is, okay, maybe this is not the it's not a good example, yeah. So maybe something like this, you can have something like this in this algorithm, but there what you do is you even break this down further. You even take its children and directly connect it to A, so that the height of the tree is as small as possible. So there what you will end up doing at certain places is you will remove this, directly make D the child of A, now you see you have cut down the height by a lot. So you keep on doing something like this. It's called path compression. And yeah, if you do that, you can do amortized cost of this would be constant. So you can do much better by using path compression, which is something I'll not get into. You can again read out the details in the reference that I mentioned. You can check the Dasgupta book. And the other thing that I want you to try out is this example. So in this example, at every stage of the algorithm, write how does your so similar to what we did here, right? We had this union operations and so on. You see, step by step, try to see how your union operation will how does your data structure change every time you do a union operation. So try to draw those arrows. So initially you will have something like this, all are different components. Then here CF becomes one component here, so you do union of C and F. Then you do a union of A and B. Then you do union of A and D. So basically I'm trying to say that have these self loop vertices, and each time you perform this operation by adding an edge, update, see how your union find data structure changes. So yeah, so do try this out um, to ensure that you have understood it clearly. I think I'll stop with that. And next we will meet on Friday next week, same time, 6 p.m. to 8 p.m. And yeah, so how was this, how was the difficulty level of this um, tutorial? Was it okay? What we will discuss on next Friday will be the content of the next week, which is greedy algorithms. So we have already seen a few greedy algorithms, but next week we'll see how do we actually prove that it works, how do we know it is optimal. And there are some other very interesting examples um, in the greedy strategy. Yeah, it will be about greedy paradigm. um, okay, so was this moderately difficult or easy or difficult to follow? Okay, maybe I'll stop the recording, then you can let me know. 1 second, okay. Okay. Okay, so yeah, hello everyone. Welcome to the week 6 of problem solving session for the design and analysis course. So what will last time we saw this MST and union find data structure and how you can implement it efficiently by making a clever choice of data structure. So in the upcoming weeks, I guess there are only 3 more weeks for the exam. So the theme of this week is going to be one paradigm of algorithm, which you've already seen. It's called greedy algorithms. And the other paradigm that you have seen in previous algorithms, the shortest path algorithms and the minimum spanning tree algorithm, the other thing was dynamic programming. So this is another paradigm, and this week we'll only look into the greedy algorithms, and this is something we'll do in the in the week 7. And just to give you an idea about how we are going to conclude the course, so what we'll finally see is that so what we'll finally do is, so far in the course you have seen some problems and how do we design algorithms for them, what is a correct algorithm and so on, and how to do the time analysis and so on. Finally, what we'll see is that there are problems for which we don't know if there is an efficient solution. We don't know if there exists one. And we'll look into those kind of hard problems, and there is a neat classification that we have done. So given a problem, where do you put it? Do you put it in the class of efficiently solvable algorithms, or do you know they are hard and you know how to prove them, or you don't know any of this? So easy versus hardness of problems, and we will properly define what we mean by them. So this is called intractability, and this will be the final theme of the this is the final theme of the course. And finally on um, Monday, which is 17th, I think exam is on 18th. So on Monday the 17th, we'll have a final summary or short summary session. If you have any questions, you can you can participate in the final session. Okay, so let's start with the theme of the greedy algorithms. So um, do you recall any greedy algorithms that you have seen um, earlier?
Dijkstra,
Dijkstra. Dijkstra is one. Good.
Kruskals,
Kruskal's.
Prims,
Prim. Yeah. Okay. Good. So so these are the uh, three greedy algorithms that you saw, and we did not formally prove the correctness of any of them. We never argued why it always gives you the correct answer. So that's something we didn't do. But if you are interested in knowing, then good resources, again the three textbooks that I've been mentioning throughout the course. One is CLRS, then the other is Kleinberg Tardush, and the other is, if you want more problems to practice on, then um, then Das Gupta is a good reference. So Das Gupta, Papa Dimitriou, and Wazirani. So this is just one book, DPB you can call it. So you can look into the three for correctness and so on, and for more practice problems also. So we'll do for the data structure parts. There are two things that are relevant. So data structures that we'll look into is one is what is called the binary search tree. The other is what is called an AVL tree. So before we get into the data structures, we'll quickly talk about the greedy theme. So greedy algorithms, and what we'll look into today is just the Huffman encoding. Okay, so let me start with that. Okay. Okay, so the problem is very simple. So you have this huge files, mp3. It could be any file, it need not be just a text file, it could be an audio file, it could be a video file, or it could just be as simple as a text file. And let's say the file is very large, so it's something like maybe maybe it's like 256 GB or something, let's say. So it's very maybe like 25 GB, and it's very large. So if you want to send it from your computer to your friend's computer, then that amount of data has to be transferred from your machine to the other machine. So naturally, one thing is you are losing lot of resource would be computation, could be time, it could be your data itself, storage, and so on. So that's something you don't want to do. You don't want to send large files just like that. So then what do? You do something that's called a compression, which is something you use in your day-to-day life, right? So what you need to do is you somehow need to compress this data, this large amount of data, into let's say reasonably smaller file. So maybe if I can bring it down to few MBs or something, then I can then if I can some way send it to your friend's machine, it's the same file. And then if there is some uh, um, decrypting decryption algorithm which will take that compressed file and get back the original data, then your friend can now enjoy the same music. So now you can get back the uh, yeah, you can get back the whole file, send the file that way. So what we need to understand is how do we do this compression, okay, and how do we do the decryption efficiently. So these are the two things that come up. So um, one of the most natural things that you would do is, let's say, um, yeah, so maybe I have some data, I'll just write random. Okay, so I've so okay, so let's say you have some part of data which looks like this, and of course there may be so many other characters. Yeah, there could be a lot of characters, but right now I'm not writing, just for the sake of ease. And you want to send it as a binary encoding. So what you could do is, one way to do, so how many characters are there? There is B, C, D, E, um, F and G. These are the five. These are the six letters that you have. So, if you can observe this, you know that um, every alphabet or every character has an ASCII value associated with it. That means you have, say, all these possible um, yeah, you have all these possible letters, and then there is an 8-bit string that is associated with it. So for example, 00, I want to write A like this, then B could be something like this. So there is a standard encoding which converts your alphabets in English into a binary string for the computer, and each of them is guaranteed to be 8-bit string. So what will happen is, you'll use the ASCII encoding for B, that is itself 8 bits, and then you'll use the ASCII encoding for C, which is again 8 bits, and so on. So then you will eventually get this as a binary string of zeros and ones. So what will be the length of this encoding? So if this is the message that I have, or this is the file that I have, so how many characters are there? There are 12, right? Okay, so by that we mean that so the length of this message would be the number of characters into it, which is 12 in this case. So for each of the 12 characters, you are using 8 bits. So totally how much is the length of the encoding? Is this okay? Is this okay with everyone? So so basically what we just said is that for each of the letters you're going to replace it with a binary string of 8 bits, and therefore the total length of your encoding would be 8 times the length of the message, which is really bad for us. Why is that? Because yeah, which is really bad for us because um, if you notice in this particular message, there are some alphabets that are not even going to be used, and I'm still using so many bits to represent them. So this is the problem. So if I could instead create my own mapping where I map B to let's say 000, C is 001, D is 010, E is 011, F is, let's say, 100 and G is 101. Okay, if I create a mapping like this, and now if I do the encoding, then how much bits will it take? So for every alphabet here, I'm going to replace it with a string of length 3. So this becomes, let's say, 000. This becomes 001, 010, and so on. So what is the length going to be? Yeah, exactly. So it's going to be 12 into 3, which is 36. Okay, so just by using this fact that I'm not really using everything in the alphabet set, I'm just using a few of them, I can actually bring down the length of the encoding from 96 all the way down to 36. So this is the main idea behind compression. You're going to remove the redundant information and use only what is needed. So you can create your own mappings like this, so that the this compression happens as you can compress it as much as possible. So one such idea is by Huffman. So we'll see how to what it does. So far what we did is just a very naive um, just a very naive way of doing. Okay, there is one comment in the chat. Alphabets are 6 and the string. Okay, yeah, that is correct. Okay, okay, okay. So let's just look at one simple example again. So let's say I have a string like this. Okay, and in this case I only have maybe I'll write a few more. Okay, now in this case I have some 4 5 letters in my alphabets in my string, A B C D and E. Okay, and now what you can do something like earlier. You can say that maybe A is 000, B is 001, and so on. You can do something like that. So it will take 3 bits per character. Okay, but notice that there are some alphabets that occur more often than other. So what I would want to do is, for the ones that occur so many times, if I could somehow just reserve this bit 0. So whenever I write 0, I just mean, let's say, A. Then what will happen is, how many times does A occur? So frequency of A is the number of times A occurs in the string, so which is in this case 6, right? There are 6 occurrences of A. So if I encode A as 000, then I'm totally spending 3 into 6, which is 18 bits for encoding A in the whole string. Okay, but now that I know that A occurs so frequently, if I could somehow, let's say, encode A as just 0, then I'm actually using only 1 bit per occurrence, so which is 1 into 6, which is 6 bits. So instead of 18, I'm bringing it down all the way to 6. Okay, so this is like the idea of Huffman encoding. It says that don't just blindly encode your alphabets with same number of bits each time, which is what we did earlier. We did 3 bits per alphabet, but rather you notice the frequency of, maybe like do one scan of the entire message and find out how frequently a particular alphabet occurs. So can you tell me the frequency of the other alphabets here? So what is the frequency of B? B is 3. Yes. C, D and D are all 1. Yeah. Good. Okay. So so what that means is, so for example, if I encode C, if I end up encoding C um, as maybe 111, okay, that is okay for me. I'm still paying a large price for C, but that's okay because I'm only paying it once here. It only, anyway, it occurs once. So I'm okay with spending few more bits there. Similarly for TNE, because it's just a one-time cost. It doesn't occur a lot of times. So with that in mind, how much if you do this encoding, so let's say I encode A as 0, B as 1 1, C is encoded as 1 0, and D is encoded as 1 1 0, and let's say E is encoded as um, okay, maybe I'll do this. Okay, just give me a minute. Okay, let's say I do this kind of encoding. So A is mapped to 0, B is mapped as 101, 100, C is mapped as 101, and so on. So if this is the encoding you follow, that is, you replace every occurrence of A with a 0, every occurrence of B with a 100, then what is the total length of this message if we follow this encoding map? So what is the total length? Okay, so Ayuti says 24. Let's check that. So there are 6 occurrences of A. For each of them, we are spending 1 bit, so that is 6. For B, um, we are using 3 bits, so that is 9. For C, we are using 3 bits, so that is 3, and for E again we are using 3 bits. So what is the sum of this? This is 18 plus 6, which is 24. So 24 is what you will end up using. Whereas if we would have, if I mean, just contrast it with the previous method where each of them had a 3-bit string associated with them. So if we do that 3-bit encoding, then how much would the length have been? There's a raised hand. Krishna, do you have a question or is it- okay? So there are 12. The length of this message is 12. For each of them, we are using, if we use 3 bits, then the total, yeah, the total length of this would be 36 bits. Okay, so this is just to contrast. So if you just blindly do a 3-bit encoding, you would have used 36, but if we do something clever, which is look at the frequency, then we are saving on the number of bits that we used. So this is the main idea of the Huffman encoding, and what it tells you is how to come up with the best map, with a map as best as possible. So this is something that we just tried out. I mean, we just tried some values and we came up with this, but is maybe there is a possibility that we can do something better. Maybe there's some better map than this which will even bring this 24 down further. So that is what Huffman does. So what it says is, now we'll look at the idea of Huffman encoding. So what it says is, whenever you get a message, first thing that you do is you scan through it and write down the frequencies of each of the alphabet. And now we have these values 63111. Then what you do is you write them in the sorted order, in ascending order. So what is the sorted order for this? That would be 11136. This corresponds to maybe A, B, C, D, E, doesn't matter. So then what you do is, now that you have written them in the sorted order, you're going to pick the minimum two smallest values. So which are they? What are the two smallest values here? Yeah, so C and D. Yeah, you can take any of the two out of this. So C and D. Let me take C and D. And then what I'll do is I'll combine them together and form a node. So this comes from the idea of trees that we saw earlier. So I'll just combine these two and I'll form a node, and I'll write a value at it. So what will be the value at this? It will be the value of the frequency of C plus the frequency of D, which is in this case 1 plus 1. So I'll write a 2. Okay. Now what you do is you think of these and this new value as your set, and now you pick the smallest two again. So these are out of the question because we already dealt with them. The boxes are out of the question. Look at the remaining values and find the next two minimum. So which is that? Okay, this is also in the set. So you are looking at 2136. One and two, exactly. So now we will do the same thing, combine 1 and 2 and form a node. And what is the value that we will write there? We'll write the sum of the two values that we just combined, which is 3 in this case. 2 plus 1, 3. Now this is also done. So what? Okay, so now look at the next two minimum, which is amongst these three. So what are the next two minimum? 3 and 3. Good. So then we now combine 3 and 3 together and we get a tree like this. And finally we only have two elements remaining now, which is 6 and 6. So there is no choice, we are going to combine 6 and 6 together and we get a value of 12. Okay, so now what it says is you're going to write 0 on the left. So each node has exactly one left left edge and exactly one right edge. So we'll write 0 1 for 6 also. On the left side you write a 0, on the right side you write a 1. So 0. So 0 1. Again do the same thing, left is 0, right is 1, left is 0, right is 1. Okay, now what we are saying is we have actually encoded all these letters by using this tree. So what is the encoding for A? We want to find the encoding for A. I'll start with the root, which is 12 in this case. Start from 12 and reach all the way up to A. So what did I read? I only read 1. So the encoding for A is just going to be 1. But let's say I want to encode B now. So how do I go from 12 to B? What is the path? I'll go like this. So what is the encoding? It is the value that you read on along the path, which is 0 followed by a 1. So encoding for B will be 0 1. Now similarly, what is the encoding for C? Exactly, it is going to be 4 zeros, because if I want to reach from 12 to C, then I'll take a 0 0 0 0, and then you want to go from let's say quickly maybe encoding for D and encoding for E. So it's 0 0 0 1 and 0 0 1. Okay, so okay, good. So you can now using these as your encoding. So instead of having this map, if I give you this map, you can try to find out what is the compression length of this message if I use this. Okay, but we'll do such examples. But the point that I want to convey is that um, the um, the Huffman algorithm basically what it does is it writes the frequency in the ascending order, and each time it looks at the new the unassigned values that you have, finds the minimum two, and creates a node and updates the value of the node until you have basically made all of them the leaves. So yeah, and then we use the property of the tree here to find out this encoding, because in a tree, if you look at any leaf, there's going to be exactly one path. There's a unique path from the root to the leaf. You can't have two paths from root to leaf. Do you see why? What will it contradict otherwise? Exactly, good. Otherwise you end up getting a cycle. So if you have uh, two paths like that, then you will end up creating a cycle. That's why, so this is the property that we are using to make sure that we have an encoding function. That is, you cannot have one character and have two possible encodings for it. So this is the simple algorithms. Now what we'll do is we will see some examples on based on these. Okay, before that, are there any questions regarding the algorithm? Okay, good. So
Hello, ma'am.
yes.
Ma'am, I have a doubt in binary heaps, ma'am.
Okay, so can I take it up after we
Ah,
finish?
okay, ma'am. Okay,
Okay,
ma'am.
okay, sure. So yeah, so just take this example. So the symbols that you have are A, B, C, D, E, and these are the frequencies. So frequency of A is half, frequency of B is 1/4, and so on. And now we are going to use the Huffman encoding technique, and it will tell you how to encode A, B, C, and so on. So just apply the algorithm and let me know what are the encodings that you get. So I'll wait for a couple of minutes in case you are trying. Okay, so those who are trying, you can if you come up with answers, you can write in the chat. I'll take a look at it. So let me start solving. Okay, so the frequencies that are given to you are precisely these, and the first step that we know is first step would be that you sort them. So what is the order? Um, okay, so the order would be 1 over 16, 1 over 16, 1 over 8, 1 over 4, and 1 over 2. Okay, so this is the ascending order. Now what do? We take the first two minimum, which are these two, and combine them together as a node. And what is the value that we will write? What is the value of this node? So just recall what we did earlier. So we looked at the frequencies here and we simply added them. So what will we do? We'll just take the sum of these two. So what do we get? Okay, so we get 1 over 8. And now what are the next two minimum? Okay, is the algorithm clear to everyone? So okay, maybe if it's not, then maybe we'll run this example again. If there are any questions after that, then please let me know. So then we look at the next two minimum among this set, which is 1 by 8 and 1 by 8. So we combine them, and what is the value that you write? It will be the sum of 1 over 8 and 1 over 8, the nodes that we combine, which is 1 by 4. Then you look at the next two minimum, which is 1 4 and 1 over 4 here. Then again we combine them together. So what is the value that we get here? It's the sum of these two, which is 1 by 2. And finally, what are the two minimum nodes that are remaining? It's half and half. So we combine them together, and yeah, and we write this. Okay, so now we follow the same steps. We just write 0 1 0 1 0 1 0 1. It doesn't matter where you write 0 and where you write 1. It should just be that one of the branches is 0, the other branch is 1. It can be in any order, but they should both be distinct. Okay, good. So I think Ramnathan has correctly answered this. So you have A, B, C, D, E, and the encoding for A is going to be 1, encoding for B is going to be 0 1. Then you have 0 0 1 for C, 0 0 0 1 for D, and 0 0 0 all zeros for E. Okay, so good. So now can you try the part B? So what it says is you have a large file. It has 10,000 characters. There are 10,000 characters in it, out of which half of them are going to be A. That means this is 1 million, right? So yeah. So half of these are going to be A's, 1/4 of these are going to be B's, and so on. So if you have such a file, what is the total length of the encoded file when you apply this scheme here? It's okay if you don't calculate. If you just tell me the expression, that would be enough.
Hello, ma'am.
Yes.
I think we should multiply with 1 by 2 with 1 million plus For B, we have 1 by 4 into 1 million plus 1 by 8 into 1 million plus 1 by 16 into 1 million plus 1 by 16 into 1 million.
Yes, that is almost correct, except that one thing that we did not count here is the bits that we are using to encode each of them. So for B, for example, you're using 2 bits, so you should also multiply it by 2.
Yes, ma'am. Yes, ma'am.
Yeah, good. So for A, the length is just 1, so it doesn't matter. So for A, you're going to take 10 to the 6 into 1 by 2 into 1 bits. For B, you're going to take 10 to the 6 into 1 by 4, because 1/4 of them are B's. For each B, you are using 2 bits to encode. So this is what you'll get. For C, you have 10 to the 6 times 1/8 of them are C's. So these many C's you have. For each of them, you are using 3 bits to encode. So this is what you get. For D, you will get sorry, I think sorry,
For
both
E,
are
4,
4.
4.
Yeah, both are 4. Yeah, thanks. So this is 4, and if you add them together, you will get your final answer. So just sum up all these values, and that will be your final answer. So are there any questions? Are there any questions regarding? Um, okay, okay, good. So okay, so maybe in the interest of time, I'll not do this question, but try this out. It's similar to what we did. You just have to convert them into frequencies and then apply the same algorithm. So we'll not do this. Maybe I'll move on to the next question. So okay, just 2 of them. So maybe we'll do this one. So what the question says is you have 3 alphabets only. It's ABC, and their frequencies are FA, FB, and FC. Okay, and now we're going to apply the Huffman encoding on them. So if you, let's say, apply the algorithm, and the code that it gives you is 0, 10, and 11. That means one of these gets 0, the other gets 1, 0, and the other gets 1, 1. We don't know which one gets what, but the question is it possible that such an encoding can happen? If yes, then you have to come up with some values for FA, FB, and FC, such that if you apply the Huffman algorithm, you'll get this code. Otherwise, if it's not possible, then come up with a reasoning why it is not possible. So yeah, so just take some time, think about it, and then share your ideas. So for part A, do you think it is possible to get such an encoding, such a code? How many think it's possible? Can you yeah, maybe use a reaction or use the chat? Okay, so okay, so let's see the answers. Sorry. Okay, so the answer for this is yes, it is indeed possible. So we'll um, just come up with some examples. So let's say FA is 2, FB is, let's say, 4, and FC is, let's say, 7. So then apply the Huffman algorithm on these frequencies. So what do you have? You have this sorted form 2, 4, 7. You choose the first two smallest values, which are 2 and 4. Then you combine them and you get 6 here, and then you combine the next two remaining values and you get a 13 here. And now if you do the same labeling, 0 1, or maybe I'll do 1 0 1 0, then okay, it doesn't matter which is A, which is B, which is C, I'll just do randomly. Then one of these gets encoding of 0, which is what we have here, the other gets a 1 0, which is what we have here, and the other gets a 1 1, which is what we have here. So I have given you some frequencies for which if you apply the algorithm you'll get these encodings. And yeah, like we remarked earlier, there is no strict rule on which side is 0, which side is 1. You can fix a convention for yourself, but yeah, you just have to ensure that the two branches should get opposite values. That's it. So is this clear? Is the part clear? Okay, if yes, then can you try B and come up with frequencies, or come up with an argument if it's not possible? Yeah, frequencies can be anything. You come up with frequencies such that if you apply the algorithm you get this code. It could be anything. So did anyone come up with some frequencies? Feel free to share if you have any partial thoughts or any ideas. Okay. Okay, so does anyone think it is not possible? Maybe yes or no answer. Do you think it's possible or not possible? Exactly, yeah. B is not possible. So do you have any, I mean, just random guess or anything for why it cannot be possible?
I took A1,
Okay.
B2, and C3.
Okay. Yeah, so for these values you can't get, but sorry, so for these values you can't get, that is correct. But the question is it possible that I can come up with some other values such that for those values I get this encoding? So for this one I agree we don't. Okay, so the question is, if you want to say no, then you have to say that no matter what FA, FP, FC you write, it can't happen. And if you want to say yes, then you just have to come up with some FFP, which is what we did here. I just want to say yes, then here is one example. If I want to say no, that means for no values, that's what we are saying here, no matter what frequencies you put, you can't come up with this encoding. Okay, so so how do we show something like that? So the idea is that if let's say such an encoding is possible in the Huffman, then what will the tree look like? The tree will look something like this. It has some root node. From there you have a 0, you have a 1, there is some leaf here, and you have some leaf here at 0, and then further you have a 0 and you have some leaf here. So I think you might have guessed by now that all the leaves that you have are only, all the characters you have are only at the leaf level. You cannot have a leaf somewhere in the middle like this. So these squares are somewhere that's already at the bottom. These are your characters, and these are just internal nodes that are never being used. So So intuitively what's happening is it's saying that this is also a leaf, this is also a character, and this is also a character, which if you apply the Huffman algorithm you'll never get, because what it does is it already starts with these three leaves at the bottom, and it's going to combine in some order. And there is a reason why this cannot happen, so this is just something you can conclude from the algorithm, but the reason why it cannot happen is because of sanity checks. So for example, um, if I give you a code, maybe let me take the first example, and I'll give you a random uh, binary string. Okay, I'm just writing some random values. mm, okay, if I give you this string, this binary string, and let's say that a is 0, b is 1 0, and c is 1 1, and from this string you want to extract the abc data. Okay, so this is the decryption part which we mentioned earlier. So this is the compression part where we use the Huffman encoding. Now your friend has this file and they want back the file that you sent, so they're going to do some kind of decompression. Okay, so how do we do that? What we'll do is you look at the first bit and you know that 0 is definitely an a, so you write an a here. Next you look at 1, there is no there's no I mean string, there's no character here which has just 1. Then you read the next two, which is 1 0, so then you write a b. Then you read the next one, there's nothing for 1, so you read the next two, which is 1 1, you replace it with c. Can you complete this quickly? Like, can you just tell me what is the data here? Okay, so for 0 you have a, for 1 0 you have b, for 0 you have a, 1 1 you have c, for 0 you have a. Okay, this one is not even possible, sorry, this shouldn't even be there. So notice that there is, yeah, good. So notice that there is one nice thing about this string, which is that no matter how you read it, there is only one possible interpretation from it. You cannot get two possible interpretations from this code. And but if you look at this example, and if I give you something like this, maybe, then if you read the first 0, then you can interpret it as a. But if you read read it as a block of two zeros, yeah, exactly, yeah. So if you read it as a block of two codes, then it could even be, maybe there's no a here, but it's just a c. So that's also possible. So you cannot, ideally your a good code should not have two interpretations. And like Ramanathan has correctly pointed out, you if you generalize the property, you don't want one code to be a prefix of the other code. That is exactly the property that we want. So maybe I'll just write it. So the property that we want is no code should be a prefix of the other. Okay, so we don't want that, otherwise there is no unique interpretation that is possible. So okay, so this is what is happening in this example. And Huffman coding makes sure that it is in fact a coding which has this property. This is something you can see from the algorithm itself. And because this does not have the property, this is not a Huffman code, so you can never get this. So is this clear? Okay, so okay, there is a question. What if we had 1 at the end of that string which is not present? Do you mean this string or this string? This string, right? The second one. First one. Okay, then it's not a valid encoding itself. So not every binary string is a valid encoding, only some of them will be valid. Is it okay? Okay, good. So what about third one? If you observe, it does not have the property that we just now observed, right? There is no string here which is a prefix of the other. So then is this a Huffman code? No. Good. So why is that? Okay. None string are getting mapped with respect to property. You mean this property of prefix free? Okay, so this property is satisfied because there is no, if you look at any two encodings here, none of them is a prefix of the other. So when I say prefix, the whole thing should appear before, I mean this entire code word should be there before some other code word. So the entire thing is a prefix of the other, only then you say it's a prefix. Okay, in other words, if it's prefix free, which it is in this case, if you look at any random binary string, let's say this, there will be a unique encoding for it, because what you will do is all three of them are blocks of 2. So you basically break it into blocks of 2, check if it is 1001 or 00, and then map it accordingly. So there is a unique decoding for this that is possible, but the problem with this is that, so answer for C is no, it is not a Huffman encoding. So why is that? Because you have three characters, right? A, B, C in some order, doesn't matter, and they have some frequencies, and these are in the ascending order. So let's say like this. Then what it will do is, I don't know what the values are, it will take the two minimum. So let's say these are the two minimum, it will combine them like this, and then there is no other choice, it just has to take this and combine them together. This is the only way it will work. Okay, by the definition of, by the algorithm. So then you do some any kind of assignment, you will see that there is always one alphabet which only gets a encoding of length 1. Okay, this will always happen because of the way the algorithm runs. And then there will be two which have 2-bit encoding, and what this does is, it actually gives a 2-bit encoding to all of them, which you cannot get if you run the Huffman encoding, and which is good for us because this is taking more bits to store, right? Something that I could just do using 1 bit, I'm actually spending more bits for that. So Huffman kind of ensures that you spend as minimum as possible. So there's a proof for why Huffman would give you like a compressed, a good encoding. There's a proof of correctness for this, but we'll not get into the correctness proof for now, but it is, if you want, if you can look it up in one of the books that I mentioned. Okay, and okay, so are there any questions regarding what we did right now? Okay, good. So okay, so maybe this is a quick question, so we'll end up the discussion of Huffman with that, and yeah, we'll move on to the data structure part. Before that, just quickly try to answer this. So you have n symbols, n alphabets, and these are the frequencies f1 to fn. The question is, what is the longest code word that you can possibly have. So there could be lots of different trees possible based on the values of f1 to f2. What is the longest such path you can find? And if you can find, can you come up with an explicit values of fi's, um, which would satisfy the claim? Okay, good. Yeah, so I think if you meant n minus 1, yes, then the answer is correct. So what could happen in the worst cases? You have these frequencies arranged in the ascending order. You take the minimum and you combine them together. Okay, then it's possible that this one and this one are still the next minimum. Then you combine them together. Then maybe this one and the next one are the next minimum, and you keep on doing this. Finally, you will end up combining the previous one and this. So, what is the longest path in this? The longest path is this that reaches to f1. So, what is the maximum height of this? This can be n minus 1 if you count it. So this is 1, then you have 2, then you have 3, and so on. So for f1 you have n minus 1. So the longest path you can have would be n minus 1. And if you want, you can come up with a simple example, which is you write a 1, 2, 4, 8. Basically write the powers of 2, and you will always see that if you add 1 plus 2 you get a 3. So the next smallest is 3 and 4. If you add them you get a 7. So the next smallest is again 7 and 8. So you combine them, and it keeps on happening like that. And the longest path here will be of n minus 1. So this is an explicit example of when we can produce these frequencies. So if you want to see why this is maximum and why can there not be any other tree which has you can think about it and try to prove the correctness of why this is the maximum you can get. Yeah, but if there are any questions about the Huffman encoding in general, then this is a good time to ask. Then we'll switch to the data structure part. Okay, so if you want more examples to practice, you can take a look at the Tartosh book, and there's a chapter called Greedy Algorithms, and you can find some nice solved as well as unsolved examples in it. So before we move to the data structure part, I think there was a question about heaps. I can address that now. So what was the question? I think Ramanath.
Ma'am,
Yes.
ma'am, what is the time required to update a value in heap, ma'am?
Okay. So you are saying you already have a heap and you want to update some node in it.
Yes, ma'am.
Okay. So the standard operations that you have is insert and delete, right? So you can think of update as two operations. One is that you delete the node that you want to update, and then you insert the new value that you want. So the time for update would be the sum of the two, which is log n.
Okay, ma'am. I thought first we need to locate that element, then we need to change the value. So I thought it's n log n, ma'am.
Oh,
So
okay,
in
okay.
previous lecture, you have discussed about decrease key procedure, ma'am. So in that I have a doubt.
Oh, okay, okay.
Thank you.
Okay, sure. Okay, good. So yeah, so let's move to the data structure part. Okay, So I'll just quickly start by defining what is a binary search tree. It's also called a BST, and it's basically a binary tree where each node satisfies a certain property. So let's say I look at this particular node, and what are the two children? This is the left child of this root, and this is the right child. Similarly, if I think of this as if I forget about the whole tree, and if I just look at maybe this subtree and I forget about the rest of the part, if I think of this as my node, and this is the left child, this is the right child. And what a binary search tree basically says is that if I look at the value at the node, the value of its left child can be at most the value of the right child, and so on. So for example, if I write if I write 10 here, then 7 and I write a 7 here and a 13 here, then it satisfies the property. Similarly, if I write a 3 here, 6 here, it satisfies the property that the value at node is larger than or at most the value of the immediate left child and that of the right child, and this property recursively holds for every node. So if I look at this node, the value here should be at most 13, the value here should be at least 13. Same thing happens, sorry, this is not 6, I can have 8 here. Okay, but can I have maybe something like, sorry, can I have something like 13 here, because 13 is larger than 7? Is that okay?
No, ma'am.
No, why is that?
Because 13 is greater than 10, ma'am.
Exactly. So the property is satisfied for 7, but the property is violated for 10. So yeah, so it cannot be everything to the left of this should be smaller than 10, and everything to the right of this should be larger than 10. So this is not correct. Okay, so if that is clear, just quickly just take a look at the 4 examples and tell which of them are BST and which are not.
A is not a BST, ma'am.
Okay, why is that? Which is the
12 cannot be the 12
12.
cannot be as a left
12
subtree.
cannot be, yeah, so this is the problem. 12 is larger than 10. What about B?
It is also not a BST, ma'am.
Okay,
9
why?
cannot be at the right side of 10, ma'am.
9 cannot be, so this node is the problem is at this node, here the problem is at this node. What about C?
It is a BST, ma'am.
It is a BST, but
That or machine.
D cannot be a BST, ma'am.
okay, why?
7 cannot be a left side, ma'am.
Yeah,
To a
so
1 root 1.
exactly, so this is again the culprit node. Okay, so this is the only BST that you have. Okay, so I'll just quickly recall what in order, pre-order and post-order traversal is. So this is not something specific to a BST, it's something that's there for any tree. So what does it say? Maybe I'll just quickly define what is in order traversal. So okay, maybe let's do pre-order. This is something that you have seen when we did DFS and BFS algorithms, but I'll just quickly recall in order traversal. So what it does is it says visit, then go to the left, then go to the right. What does that mean? I start my exploration from the root node, which is 10, and I'm going to visit that node. That means I'll print the value 10. Then then what I'll do is I'll go to then it says go to the left, then you go to the left and repeat the same algorithm. Now think of this as your tree, and repeat the same algorithm. So then what does it say? It says visit, go to the left, go to the right. So visit would mean that we print 7. Now we've done a visit for this. Now we need to go to the left. Left of this is 6. So for 6 again you use the same rule. We visit left, right. So visit would mean that I print 6. Left would mean I go to the left, so there's nothing, I come back. Then I go to the right, there's nothing, I come back. Now at this point for this node we have completed our visit, we have completed our left. Now we go to the right and apply the same process for this subtree. So what do you get now?
Ma'am, hello, ma'am.
Yes, yes, yes.
Ma'am, I think that the tree is not a BST, ma'am.
This is not a BST. So we are saying that this
Okay, ma'am, okay, ma'am,
holds,
okay, ma'am.
this holds for any tree. Okay, so what do we write next? We continue the exploration. So we were here, we did our visit, we did our left, now we are doing right. So on the right we have this subtree, so we do a VLR on this. Okay, so we are at this part and we are going to do VLR. So V means visit, visit would mean that print 12. Now you're done with V part. Now we're going to do left. So we go to the left of 12, which is 20. Now think of 20 as your tree and do a VLR for 20. So VLR for 20 means visit it first. So we visit it. Then you go to the left. There's nothing to the left of 20, so you come back. Then you go to the right of 20. There's nothing to the right. You go back. Now we are done with the VLR for 20. So we come back. So when we come back, we are at 12. At 12, we already did our visit. We already did our left. Now we are going to go to the right. So go to the right, but there is nothing. So you come back. You come back at 12. Now we are done with our VLR for 12. So you go back. You go back to 7. At 7 also we have done visit, left, right. All of that is done. So go back to 10. At 10 we have VLR. We'd already visited. We did the left part, which was this. This is already explored. So you go to the right. So now what do we do now?
We will first visit 14,
Visit
then
14,
13,
go to the
then
left,
13.
then visit it, 13. Then there's nothing here, nothing here, go back, nothing here, go back, and you're done with the VLR for this. So go back. So everything is done. Okay, so similarly you can think of in order traversal, where you go to the left first. After you have completed the exploration at left, you visit it. Once you have visited it, then go to the right and explore the whole tree. And there's something called post order, where you do LRP. Okay, so what we did here is, this is exactly the pre-order. Now you have to identify which of these, which one is the in order and which is the post order among the options that are given.
I think C is in order, ma'am.
Okay, C is in order, but that would mean if you try to do in order, so we are just trying to get, no, I'll just draw the whole thing again, maybe 10, 7. Okay, so if you do in order, that means you are doing left, visit, right. So you are doing left, visit, right. So that means you are at this node, you're going to go to the left. When you are at this tree, then you do left, visit right. What it says is go to the left. So you go to the left, and then you get 6. You get LVR for this, and uh, at 6 you go to the left, but there is nothing, so you come back. Then you visit it. At this point only you visit it. Print 6. Then you go to the right. There's nothing, come back, so right is done. Now go back. At 7 what you've done is you've completed the exploration for the left part. Then you print 7, then you visit 7, then 7 comes, and then you visit the right part of it. So if you start with 10, that can only happen if you visit it in the first step only. So is this okay?
I said C is the in order.
Exactly. So if you complete, yeah, good. So C is the in order, and yeah, and yeah, I think none of the answers that are there in the options corresponds to a post order traversal. So you can try to come up with it. It's an interesting exercise to understand how recursion works also. So try this out and come up with a sequence for the post order traversal, and then you can also ask, okay, why not define something like, you have this right, you always said that first you go do left, then you do right. Every time left comes before right. You can even do the other way around. You can also define something like VRL. You can even do RVL. You can even do RLV. So this is also valid. There are different names for this. I think these are called reverse in order and reverse post order and so on. But will not. These are not generally. These are the ones that are very well studied, and so we'll just stick to this. So just try this out as an exercise. So now the interesting question that I want to ask is, what will happen if I give you a BST? If I give you BST, is there anything special about one of these three traversals? So okay, my claim is that
The in
yes,
order traversal will be in ascending order, ma'am.
exactly. If you do an in-order traversal, you will get the sorted values. So the property of BST is that in-order traversal gives sorted values, and the reason for that um, is very intuitive. It comes from the definition of a BST, which is when you do you have this node, you have a left tree, you have a right tree. When you do LVR, what that means is, before I visit the route here, I would have traveled all the nodes before it. So there will be some nodes that are red, then I visit this route, and then I visit all the other nodes in some order. So everything to the left of this is always going to be smaller, and everything to the right of this can only be larger, because of the property of the BST, which says that if you have a node, everything to the left should be smaller, or at most that value. Everything to the right should be at least that value. So this property recursively holds for every node. So similarly, when you come here, same thing will happen within this set. Before you visit this node, everything you visit before it will be smaller than it. Everything you visit after it will be larger than it. Same property like recursively holds, and therefore this entire array will be sorted. So this is an interesting exercise. You can try to convince yourself if it's not clear. Okay. So the other question is, when I gave you a BST, there is a unique um, in-order traversal. There is a unique pre-order traversal. There cannot be two in-order traversals or any of these traversals. That there's one unique um, sequence that you get. The question is the other way around true? If I, let's say, just give you this in order, sorry, this was the in order traversal, then can you come up with this tree? Can you construct this tree back?
No, ma'am.
No. So there are multiple possible ways in which you can interpret it, right? So same thing happens for the rest of the traversals, but there are two of these that you can choose. Of course, if I give you three, you can always, so you can try this out. If I give you all the three, there is a unique tree that you can come up with, but I'm saying even two are sufficient. So which two are sufficient? Any guess? Like some some I mean, two of these are sufficient to construct the tree uniquely.
I think we can use both pre-order or post-order, ma'am.
Okay, so
For BST,
okay, okay. So the answer is you can use in order plus pre-order. If you use these two, you will uniquely get a tree. You can even do in order plus post order. This will give you unique tree. But if you do pre and post, this is the only case where you don't get, and there is a reason why. So I'll just try to hint you towards it, but I'll not prove it right now. But I think if you take some examples, you'll see what is happening. So let me just think of these two. I have pre-order and in order with me, and pre-order means I'm first going to visit, and then I'm going to the left, and then I'm going to the right. That means I know my route from this step only. So that means 10 is going to be the route. That is something I know from the pre-order. But now I can't tell which of these are to the left and which of these are to the right. So then I take help from the in order traversal. So 10 is somewhere here, right? So we are going to locate our 10 here, and in order you do LVR. So this part is the left and this part is the right. So that is how I know what is to the left and what is to the right. So then you go back to the pre-order sequence and see that 7 is the node that is visited next. So if you follow that sequence in pre-order, once you visit it, you go to the left. When you go to the left, you're going to visit it. So then you know that the next node is 7. So basically you do one step, use one information from pre-order, use it back to get into in order, and just keep moving back and forth between the two, and you will be able to construct the whole sequence using either these two or the other two. But the problem that happens with pre-order and post-order is that um, okay, you can actually come up with so there is no, it does not have this nice property. This in order sort of tells you what is to the left, the whole array that is to the left, and the whole values that are to the right, and that makes your job easier. But if you have pre and post only, you can't have such a nice distinction what should be on the left and what should be on the right. So that can lead to ambiguity. You can even come up with examples where you have pre-order and post-order for it, but there are two different trees that you can construct out of it. So just take it as maybe a homework, and so come up with.
ma'am. What I mean is, if they give pre-order alone means we can construct in order from the pre-order, ma'am. Then we can draw the tree, ma'am. We can sort it in ascending order means it will give the in
So
order traversal.
so yeah, so my question is, yeah, that if it's a BST then it's correct, but if I don't necessarily give you a BST, so it's just for any general tree. Let's say for any tree I want to do,
Then it is not possible, ma'am.
then it's not possible, right? So yeah, so that's the only thing I've yeah, good. Okay, so yeah. Hmm. So now we'll just look at, we know what a BST is. Then some standard operations on that would be, um, you want to insert some elements into BST, you want to delete some elements out of it, you want to search for some element, and so on. So standard operations that you've seen on arrays. And yeah, so we'll just see how these operations are done. Okay, so okay, so let's start with the first operation, which says insert 13. So when I say insert 13, I'll create a node like this, and That's the operation. Then you do the next operation, which is insert it. So where should we insert it?
Left.
To the left of 13. So 8 comes to the left of 13. Then we want to insert 20
Right of 13.
to the right of 13, because 20 is larger than 13. Then I want to insert 6
Left of 8.
to the left of it, because you start at the root. So 6 is smaller, so you go to the left, you go to 8, and 6 is even smaller than 8, so you insert here. Then I want to insert 10
To the right of 8.
to the right of it. So again, same thing, you start at 13, it's smaller, so it should be on the left. Compare with 8, it's larger than it, so it should be on the right. So 10 comes here, and I want to do 42
Right of 20.
to the right of 20. So larger than 13 and larger than 20, so to the right of 20 we have 42, and I want to do 16
Left of 20, ma'am.
to the left of 20. So again, larger than 13, so go to the right, but smaller than 20, so go to the left. So 16 is done. Now I want to insert 30
To the left of 42, ma'am.
to the left of 42, and 45
To the right of 42.
to the right of 42. Good. So now comes the interesting part. All this time we were just inserting the elements by deciding whether to go to the left or right based on the value of the parent. So now I want to perform deletion. So before even going there, if I want to delete 6, then what I'll do is, I'll start at 13. The value I want to delete is smaller than 13, so I go to the left. Then I check with 8, again it's smaller than 8, so I go here, and now I found the node that I want to delete. So I'll just safely delete this node. I'll just remove this node out of the picture, and the resultant tree is still a BST, it's still a binary tree. This is okay. But let's say I want to delete 20. So where is 20? You will do the comparisons and find the node, and I want to delete it. So the problem is that we can't just remove the node, because then it will have these two hanging components which do not form a tree. So yeah, so then how do we delete? What is the natural way? So maybe I'll just remove these edges, because 20 is deleted. So what do we do?
We can replace 20 with the maximum value in the left subtree or minimum value in the right subtree.
Exactly. So you have now two components, and you know that the value of, maybe I'll look at the right component. The value of these are all going to be larger than 13. That is something we know for sure because of the property of. So then this can be a right child. 42 can be a right child of 13. There is no, I mean, you just add it to the parent, to the right child of the parent, and that would be fine. But then now we have the 16. So what is the correct place of 16 um, in this tree? Where should 16 be?
Can be a parent of 42.
But I've already fixed this. Okay, I mean, um, I've already made 13 a parent of 42, so I don't want to change that. And the reason I don't want to do that is that there can be a lot of things out hanging here. So this is in this case it's not, but sorry. In this case it's not, but it can have its own left subtree and right subtree. So if I add 16 here, again we run into the same problem. It already has its children, and then we now make it a parent of 42, so there are more pointers. That's why I don't want to add it here. I want to add it somewhere else. And then what is the correct position?
Left of 30.
Left of 30. Exactly. So now I add one more edge like this, and now this is your final PST. So if I draw it neatly, it is going to be 16, and whatever is to the left and whatever is to the right. So generally the algorithm for delete would be that whenever you delete a node that has children, look at its parent and make the right child, attach the right child directly to the parent, to the right of the parent, and take the whole left side, and from this node you keep going, keep going left 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 all the way, and then attach this. And why is left the correct position? Because of the property of BST, that this all these values are going to be smaller than, I mean, these values are always going to be smaller than any value here. So therefore it should be on the smallest, I mean, the leftmost child of this 42. So that's the general algorithm. It just follows from, from the properties. The question is, how much time does this take? So maybe just look at insert. How much time does it take?
Insert operation, ma'am.
Hmm.
In worst case, it can take up to linear time.
Exactly. In the worst case, it can go all the way linear. So if you have like a very nice BST which is balanced, where if you have a balanced BST where um, something like this maybe. Okay. So okay, then the height of this tree is going to be logarithmic in terms of the number of nodes. This is an exercise that we have done many times. So height of this tree is log n, and so in this case if you do an insert operation, then you are only traversing along a path, so you will, in the best case you go into log n, but the worst case that could happen is we never guaranteed that this would be balanced if we perform insertion like this. In the worst case it could so happen that yeah in the worst case it could so happen that the elements that came to you for insert came in this order. So it came 1 2 4 6 13 15 20. Then what happens is you inserted 1, 2 goes to the right, 4 goes to the right, 6 goes to the right, 13 15 and so on. So the height of this tree is basically the number of nodes that you have. So in the worst case the height can be order n, and therefore if you try to insert something you will always have to travel the whole length and then insert. So worst case insertion complexity is order n, and same thing happens for delete. I think you can see by now that for delete also we have the same problem. So although BST um, has a nice structure that if it's balanced can help us do all these operations in logarithmic time, um, the problem is that it's not balanced, so the height can become very skewed. So what we want to do is we want to ensure that it's balanced. So yeah, so that is where this AVL tree comes into picture. I'll discuss about it. Before that there are just a few questions you can practice on BSTs. We don't have time to get into it right now, but yeah, I'll just upload this whole PDF on the drive, and do take time to solve this. So one question is you want to find the kth smallest element. So one thing is, where does the smallest element lie in the BST?
Hello,
Yes.
ma'am. I have a small doubt, ma'am. Like I am pursuing my BTech second year, so can I apply for an internship in the summer? Like in the summer, I will complete my BTech second year. Can I apply for that?
Okay, so directly
Means
there.
I have already got a top 1% in the IoT course like last semester of
Hmm.
NPTEL.
Okay, so directly, I think for second years, we at least IITM doesn't have um, programs for directly, um, I mean, direct applications. But I think if you are keen on doing and you have strong interest in research, I think you can personally mail the professors, maybe send them your CV and stuff. But directly there is no program for second years, but for third years there is a summer internship um, program. And sorry, and the criteria, I'm not sure if NPTEL toppers or if there's a criteria like that, but generally it will CGPA criteria would be there and from your institute. And yeah, I mean, a strong motivation and a strong CV would be preferable. So
Okay, ma'am.
okay, good. So okay, so getting back to the question, so I'll just pass through it. Will not do it right now because I want to discuss the AVL. um yeah, so just okay, so if you get time, do attempt those questions. Some of them maybe we already discussed. Okay, so these are also called height balanced BSTs. Okay, and okay, so okay, so what we are going to do is, the idea is very intuitive. The problem that was happening when we did, let's maybe take the same example. We inserted 2, we inserted 4. Okay, so the problem that was happening was that this chain kept growing like that. Okay, so for that, what we'll define is, we'll define a notion of balancedness. When do I say a tree is balanced and when is it not balanced? So for example, if I have this node and there is a left subtree and a right subtree, if the height of this is 3 and 3 both are the same, then it's a balanced tree for me, because um, yeah, because both of them have exactly the same height. If it's something like 3 and 4, then sometimes it's unavoidable, because maybe it can happen that my tree is full like this, and now there comes a node for insertion, so I'll have to insert it like this. That can make its height 4 and this height 3 and so on. This kind of imbalance can happen. So the error of one, or the difference of one in the heights of the two children, the two subtrees, is something that we will tolerate. So if it's 3 3 4 3 or 3 4, we will say it is still balanced. So when do I say a node is balanced? Is that the height of left subtree minus the height of right subtree is at most 1. Is at most 1. And yeah, so if maybe this becomes 5 at some point, then the tree is not balanced for us. So we'll say the tree is balanced if this property holds at every node, not just at the root. Then you look at the subtree, recursively the property holds for this node and within each of the subtrees, then you say it is balanced. Otherwise, if the property is violated for some node, then the tree is not balanced for us. That means we need to do something to make it balanced. So we say that a tree is balanced if this balanced condition holds for every node. So yeah, that observation is correct. That means if I don't look at the absolute values, I just look at the difference, it can be -1, 0 or 1. Okay, so okay, so then what I need to do is, I need to so maybe let's take the same example, and I inserted 1, I inserted 2. So what is the balanced factor at this point? What is the height of left subtree? That is 0. And what is the height of the right subtree? That is 1. It has a depth of 1. So if you look at the difference, here you have 0, here you have 1. The difference is mine. This node maybe, let's say, does not exist right now. Okay, so the difference is just -1, so this is still balanced. But now the problem is when I add this node 4, then what is the height of the left subtree and what is the height of the right subtree?
0 and 2.
0 and 2, and the difference is more than 1, so this is not balanced. So then what I'll do is I'll perform what is called a rotation. Okay, so yeah, so what we'll do is we'll rotate along this point and we'll make 2, or maybe that's not the, okay, that's not the visual way of saying it, but what I'll do is I'll bring this down and I'll bring this up. So 2 becomes the root, 1 becomes the left child, 4 becomes the right child, and it still satisfies the BST property when we rotate it this way. So now if we look at the height of the left subtree and the right subtree, it is now balanced and we are still maintaining the BST property. So throughout the insertions that we do, there are several kinds of reasons why a tree suddenly becomes imbalanced. So yeah, so what we need to do is we need to each of the time we need to do some adjustments, some rotations, so that the tree finally becomes balanced according to the definition that we have. So yeah, so maybe let's take a look at what all kind of um, um, yeah, what sorts of imbalances can happen. So one is something that we just now saw, which is 1 to 4. So the imbalance was to the right and right. So in this case the kind of rotation that we performed is called an RR rotation, what we did just now. It can also happen that you have 4, 2, 1. This is also a BST, and it also has violated the property of the height balance condition. But in this case the fault is on the left and left. So in this case we perform what is called the LL rotation, and idea is similar. You bring this down, rotate it on this side and rotate it upward, so you get 2, 1 and 4. But just forget about, okay, so this is what you get, and this is still a BST. And in fact you might have noticed that this and this is kind of a symmetric case. LL and RR are kind of mirror images of each other, so these are very similar cases. The other kind of imbalance can happen when you have 1, then you inserted 4, and then you inserted 2. So in this case again the height difference is evident, and what happened is you have 1 on the right and then on the left. So this is what is called RL. This is an RL type of imbalance, so you perform what is called an RL type of rotation. So any idea what kind of rotation can we do in this case to make it
First, we can make 2 as the right child of 1 ma'am. Then 4 should be right child of 2 ma'am. Then we can perform RR rotation.
RL, yeah. So yeah, so what you can do is you can bring this here, so that means 2, 4, and then you can do this, so 1 comes here. You can do in any order. I think there are 2 orders that are possible, one, but yeah. So this is what you do, and a very symmetric case would be when you have 4 here, 1 here and 2 here. So same thing happens. This is left of right, so LR rotation. You can do something similar and make it balanced. So these are the 4 types of imbalances that can happen. But now the complexity comes up when these also have children. So for example, this has children, this has a subtree, this has a subtree, this also has a subtree, let's say. Then what do we do? So maybe I'll call this T1, T2, T3 and T4. So so this is something we did, right? We did these kinds of rotations and we got this. Okay, but then what happens to these? So any idea where should T1, maybe let's see, where should T4 be in this case? Where should T4 be? Oh, sorry, T2 be?
To the right of T4, ma'am.
To the right of 4. Yeah. So
At first rotation.
yeah, so T4 is to the right of 4 because um, we're still maintaining the BST property. So everything here, sorry, I meant T2. Sorry. Um, yeah, sorry if I say T4 at some point. Okay, yeah, so we are looking at this subtree and we know that all these values are larger than 4. So if there's something that is larger than 4, it will come to the right. So this tree remains intact on this side. Similarly, let's think about T1. So T1 has all the values that are smaller than 1, so it should come to the left of 1. So this remains intact, so this is retained just like it was. So this part nothing has changed, and this part also nothing has changed, but it is 2 whose left child was removed and we attached T1 to the left child, and its right child was removed and we attached 4 to the right child, 4 as its right child. So now there are these 2 trees that are hanging and we have not attached them anywhere. So the question is, what is the correct position for T3? So look at the values in T3. Those are larger than those are larger than 1 because they are on the right of 1, and they are smaller than 2 because they are on the left of 2. So that means we should go to the left of 2 and to the right of 1 because it's smaller than 2 but larger than 1. So this is the correct place for T3. So similarly, where should T4 go?
Left of 4.
Left of 4 because T4 is larger than, sorry, it's smaller than 4. It's on the left of 4, but it's larger than 2. So it's larger than 2, so go to the right, but smaller than 4, so go to the left. So this is T4. And similarly, the um, yeah, same questions arise when maybe we did RR rotation, LL rotation. It can maybe let's do this example. This is T1, T2, T3 and T4. So when I did the rotation, where should the T1, T2, T3, T4 go? So let's say T1, where should T1 be? Maybe I'll just draw it again. So what we did was we did 2, 1, 4. So where is T1? T1 is smaller than 1, so it's to the left of 1, so it should be to the left of 1. So T1 is intact. Then we look at T2. So T2 is larger than 1 but it's smaller than 2, so it's smaller than 2, so it should come to the left, but it's larger than 1, so it should come to the right of 1. So this is T2. Then similarly look at T3. T3 is larger than 2 but smaller than 4, so larger than 2 but smaller than 4, so the left child of 4, that would be T3. And finally similarly T4, it's larger than 4, so it should come to the right of 4. So yeah, so this is how we take care of um, all the subtrees that could be rooted at it. And I hope it's clear how performing the rotation makes the tree balanced at every step. So whenever we perform an insertion, if it so happens that the tree suddenly becomes imbalanced, then we're going to perform this rotation at every step. So that is the whole idea of the AVL tree. And yeah, and the question that we now want to ask is if it's okay. So the good thing about this is that it's height balanced. That's why if I want to, that's why the tree is always going to be logarithmic in order of log n, where n is the total number of nodes in the tree. So the nice thing about this is if I want to perform any kind of operations, say be it search or delete or insert, I can always do it in log n time. Okay, so okay, so so the question is, how do I detect that? Sorry, how do I detect that there is an imbalance? So maybe my tree is very large. I've already performed some 100 insert, delete, and so on operations, and I have a very large tree. Now I'm adding one node somewhere based on the BST property and so on. So how do I detect that there is an imbalance suddenly? I need to maintain some extra memory to know that there is an imbalance. So so what are the options? What can we do? Any ideas? What kind of information can we maintain at every node to check whether this balanced condition that we described earlier, this balanced condition is satisfied at every node, even after performing all these insert delete operations?
I think the key we can say with height.
Sorry, can you repeat? The voice was not coming through. I mean, there was some break.
Hello, ma'am.
Yes.
Hello.
Yes, I can hear you
I
now.
think
Yeah.
we can save the height along with its key value as an element in node.
Yeah, so you can store the height along with the key value. That is something you can do, but um yeah, but um think just one issue with that could be that now you have stored the height, and okay, maybe that's not such a bad idea to do. You can do that. So whenever you update something, if it changes the height of that tree, then you are going to trace along the path. If it increases the height, you will increase the height of its parent and keep on doing that. So you'll have to keep on maintaining it, and every time if you want to check whether there is an imbalance, you look at the height on the left tree, look at the height on the right tree, subtract and check if there is an imbalance. Okay, but yeah but the but the one problem that happens here with storing the heights explicitly is if I want to check if there is a if there is an imbalance, I'll always have to keep on subtracting. Whenever there is a change, I'll always have to keep on checking the node, look at its two children, keep subtracting and check whether, I mean, there is some way in which you can do this, but if I want to detect it very quickly, one thing you can do is just use this idea of this minus 101 that we maybe this idea of minus 101. So minus 1 if the height of the left tree is just smaller than that of right by 1, and so on. So you're not storing the whole height per se, you're just storing the balance factor of minus 101. So for example, um, so for example, in this case, if I look at this particular example, or maybe I look at this particular example, I look at this node, and the height of the left subtree is 1, the height of the right subtree is 1, the difference is 0, so I write a 0 here. This case, same thing happens, I write a 0, but let's say there was one more node of 3 here. Then what is the balance factor of 4?
My one.
If we're doing
One.
left minus
One.
right, then it's 1, and for 3 it's 0. So um so right now everything is in the range, so we are good. Okay, but now let's say I add one more element, and maybe maybe I do 6 first and then I do 8. Let's see for now. So yeah, so what will happen is when I do 6, the height of this becomes 0. Okay, I should update everything maybe. Okay, I'll just quickly do this. Okay, so when I add 3, the height of 4, yeah, that of 4 remains 1. But if I look at 2 now, if I keep on tracing back the parents, then the height of this has now become 0 minus 1, which is minus 1. So we are just doing this minus this. Okay, so now it becomes minus 1, and that is still okay because we are still in the range. Then if you do an addition of 6, then this is 0, go to its parent. Now both of them are balanced because both are 0 0, so the parent is also balanced. So update this to 0. So update this to 0 and look at its parent now. So we are always going back to the parent and update the height changes if any. So this is 0, this is okay, it's not exactly that, but okay, maybe we need to do some extra bookkeeping to to make sure of this 1 minus 1 factors. So here you have 1, here you have 2, so maybe like keep whenever you are iterating back, keep a like a, what do you say, like a flag. So flag tells you whether the height increased at all or not. If it increased, then only we're going to have to make these changes. So this becomes, so this remains minus 1 because because when I added 6, I did not change the height of 4. The height of 4 is still 1. It was 1 even before 6 was added. So nothing changed for 4. The height of 4 did not increase. So you don't need to trace back any of the parents. The height of the parents will remain the same. So there is some, this is some what do you say, like case sort of thing you need to do to make sure when you have to go back to the parents to update and when not. So this is just one flag which tells you if it increases the height, then you have to trace back and change. If it doesn't, then we don't need to change. Okay, so so we keep on doing this, and eventually, let's say when I add 8, then we are going to update the values. So 8 is balanced. 6, this increases the height of the tree. Note that in this case the flag becomes 1. Go back to the parent, and left tree height is 0, right tree is okay, and there was an increase, so we are going to increase this by 1 and go back to the parent. There was an increase on the right side, so change this to 1 and go back to the parent, and there was an increase on the right side. So sorry, this is -1 -1. There was an increase on the right side, so this becomes -2. So at this point so at this point we know that there is an imbalance. So basically what we're saying is that if the tree is very huge and I want to detect that there has been an increase in the, I mean an imbalance, then these values are going to help us to detect, and I think you can also possibly implement it using heights. I think it should be, I think same kind of idea should work for heights also. I don't see a catch with it, but so this is some extra kind of bookkeeping that we need to do, and based on the kind of imbalance, then we're going to appropriately apply one of these 4 rotations. So maybe I'll add some more questions on AVL trees. There are few that are already there, but but we are out of time, so so I'll skip this for now, but I'll upload the PDF so you can try this out. If there are any questions, you can reach out to me. And next for the week 7, we'll meet on the upcoming Friday, which is 7th March, 6 p.m. to 8 p.m. So I think that's it for today. So thank you for attending. I'll stop the recording. Okay. 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 So yeah. So welcome to the week 7 of the problem solving session for the design and analysis of algorithms course. So last time what we saw is this paradigm called greedy algorithms, and yeah, and we saw how to use this strategy for say Huffman coding and so on. And although we didn't get time to look into the correctness of the algorithms, if you would like to look into, I think yeah, with I mean the standard references, which is Coleman or Tartush and so on, you can look into it. So this week what we'll do is we'll look into this paradigm of dynamic programming. So okay, so both the strategies have something in common, but there's something that is different with them. So for example, in both of them, what we're going to do is we're going to solve some sub problems and use the solutions optimal solution to the sub problem to build an optimal solution for the original problem. So one property is that we can use the optimal solution for sub problems to build optimal solution for the original problem. Okay, so what do we mean by that? For example, we saw one such algorithm which was APSP, all pair shortest path, which is due to Floyd-Warshall. And what we saw here was that we want to find shortest path. So the notion of optimality here is we want to minimize the length of the path from any node, from any source to from given source to given target. So what we instead do is, if I want to find so there's some graph that is given to us, and yeah, so let's say there's some graph that is given to us, and what I want to do is I want to find shortest paths from any node to any node. Let's say I'm looking at SNT, the given SNT for now. Then what you do is you actually think of think of these as being labeled from 1 to n, 1 2 3 4 5 6 7 8 9 10. So then what you do is you think of this shortest path as going from node S to some node T, to some node P, and from P to some node T, where you want to minimize the distance from S to P and the distance from P to T. Or it may so happen that it does not even take the node P, and there is some other path that is shortest. So we are used the kind of sub problem that we identified here was the shortest path to some other node. Okay, so how do we get this into account? So okay, maybe for the sake of simplicity, maybe just let me call this 10 and this one is 5. So I want to find the shortest path from S to T, which is from 1 to 10. Then what I'm going to do is I'm gonna say that first let me find the shortest path from this S to from 1 to 10, which uses the node 2, or it may not use the node 2. So I'll just I'll just say that shortest path from okay, I'll just erase this for the sake of okay, I'll just add one more parameter here. So when I say ijk, I mean that it's a path from I to j which has only used at most k many, at most k nodes. By k nodes we mean it can use these 1 2 and so on up to k, but using other nodes is not allowed. So how do we do that? So this path can either be a shortest path, so we are saying the shortest path can either be shortest path from I to k and then a shortest path from k to j, or it can simply be a path from I to j which does not use k. So it's the minimum of shortest path from I to k plus shortest path from k to j, or it's just simply the path from I to j. Sorry, let me write this. I to k using nodes up to k plus shortest path from k to j using nodes up to k, or it's simply the shortest path from I to j by using up to k minus 1 nodes, because it does not use the k node. So this is something we did earlier, so I'm not gonna get into it, but it's just a quick recap of what we did earlier. So what we're doing is you are sort of solving for the smaller and smaller subproblems and using it to build the solution. So what we'll do today is some other examples of this. Okay, because this is something we did earlier, so let me just get started with the first example. So okay, so let's say you have been given, this is called the maximum subarray sum problem. Okay, so the input to you is an array whose entries are integers. So let me just give an example. So let's say you have -2 3 5 -6 1 okay, then you have, let's say, 7 -3 5 6 -2. Let's say this is the array that is given to you, and what you want to find is so what is a subarray here? A subarray is a contiguous block, a small array sitting inside it, but it has to be contiguous. So it cannot be, for example, 3 5 and then 7. This is not a subarray. A subarray would look like this or this, something like that. It's a contiguous block of a chunk of array sitting inside. What you want to output is, so if I look at this particular subarray, then the sum of this subarray is the sum of simply the sum of the entries or values that are in there. So this would be 3 plus 5 minus 6 plus 1, so which is 3. So the sum of this subarray is 3. If I look at this subarray, then the sum is 4. So the question is, what is the maximum sum that you can get inside the array that is given to you? So find a subarray and find the sum, and it should be the maximum of all the sums of subarrays that are there. So so maybe just for this example, what is the maximum sum of the maximum subarray sum that you can find? If you just, trivially try out, right now we are not asking for a dynamic programming solution or anything. If you just try out, what do you get? Is the question clear? Is the question clear? Can if there are any questions, then please ask right now. Okay, so the answer for this is 16, which maybe we'll figure out how to find this with the DP solution. But I hope the question is clear at least. If not, then ask me at any point. Okay, so let's see what is a okay, so what is like a trivial, what is a very trivial solution, even before we get into the dynamic programming algorithm and all. What is the yeah, what is a trivial solution for this? Anusha, Pujita, and Varshinu, I think. Sorry if I'm pronouncing it incorrectly. So, if you have any thoughts, then please interact. That would help me present better. Okay, so let's see, even without getting into the dynamic program and stuff, let's see what is a very trivial algorithm for this. So, what is a trivial algorithm? It is that you look for, it says that you find a subarray, find its sum, and then check for which is the maximum. So then what is a trivial solution, a trivial algorithm? Trivial algorithm would be that yeah, go through each subarray and find the sum of the subarray, and maintain a current maximum max sum, and if the current sum is larger than the maximum, then you are going to update the maximum to equal to the current sum, and then you simply repeat this until no subarray is remaining, right? So this is the trivial algorithm. That is, you're going to check every subarray. That is, you're going to check through this, you're going to check through this, then and so on, these kinds of blocks. Then there are blocks of 2s like this, then there are blocks of 3s like this. So how many such subarrays would there be, like roughly asymptotically, if you want to bound, how many subarrays would be there? I mean, any random guess? Would it be n square or n cube? Okay, so maybe let's find this out. So how many subarrays are there? So if you look at, I want to understand the time complexity of this. So then what I'll do is I'll find what are the total number of subarrays that are possible. So let's look at this array of size n. You have 1, 2, and so on up to n. Then my subarray could be of size 1. So it could just be this, it could just be this, and so on. So how many subarrays are there? Subarray size and number of subarrays of that size. So if I take my size to be 1, then there are exactly n many subarrays, because this is precisely what the answer is. But if I take my subarray size to be 2, then how many subarrays can there be? Well, 1 comma 2 is one possibility, 1 2 is one possibility, 2 3 is another possibility, 3 4 is another possibility, and so on up to n minus 1 comma n. This is the final possibility. So how many of these are there? These are n minus 1. So I'll write n minus 1 here. Similarly, if I take subarray of size 3, then what is the total number of subarrays that you can have? If you, I mean, you can use the chat if you have any answers, or you can even unmute and speak.
Ma'am, NC3.
NC3. Okay, but we are looking at continuous subarrays, no? So, for example, this is one, sorry, I'll just use another pen. So this is one subarray which is 1 2 3. Then 2 3 4 is another subarray, so I'll just write this down. 1 2 3 2 3 4. You can start at 3 3 4 5 4 5 6, and like that what will the final
n minus 2.
n minus 2. Good. Yeah, so this is n minus 2. In general, if I take a subarray of size k, then what will be the number of subarrays? So it will be n minus k plus 1. Why is that? Why is this happening? Because my subarray of size k, if it starts at 1, it will be a block of size k. That is the only subarray that we can have which starts at 1. If I start at 2, then it will be a block like this, just one block ahead. It's just shifting one block ahead, and so on. If I start at 3, it will be like this. So for example, I cannot start at n and get a block of size k starting from here, because there is nothing behind, and there's nothing after it. Similarly, if I start at n minus 1, I can't get a larger chunk. So what is the last position where? So just count k blocks starting from n, start counting k blocks to the left and find that index. So this will be n minus k plus 1. And if you go at n minus k plus 2, which is here, you can't find a block of k because the array ends there. So there is one subarray starting at 1, there is another subarray starting at 2, and yeah, and finally there is one subarray starting at n minus k plus 1. And that's why finally when you get to n, there will be exactly one subarray of size 1, which is what is given to you. So yeah, so that is the, yeah, that is the count. And so if we sum them up, what is this? Okay, so is everyone with me? Is everybody clear with, or does everybody agree that this is precisely the number of subarrays of that particular size? Okay, if you would want me to repeat anything, then please feel free to ask, don't hesitate. Okay, so then I know that the number of subarray of size 1 is n, size 2 is n minus 1, and so on. So I just have to sum them up. So total number of subarrays is simply 1 plus 2 plus 3 and so on up to n, which is nothing but n into n minus 1 by 2, which is order n square. So this is something you know from the previous, I think some week 3 or 4, I think sometime we did this. So anyway, this is an identity. So you get like a quadratic number of subarrays. So what you do is you have order n square many subarrays here. Finding the sum, how much time does it take? So if I give you a subarray and I tell you to find the sum, it will take at most linear time, right? Yeah, and then what we're going to do is, once you find the current sum, if it's greater than the current maximum that you're maintaining, then you'll just update it and keep on doing this. So this will roughly be like order n cube or even order n square if you do a good analysis. So this is a trivial order n square time algorithm, which is very easy, like very very obvious thing to do, right? You just go through all subarrays, find which is the maximum. So there's nothing clever happening here. Okay, so now what we want to do is we want to use our dynamic programming approach to solve this. That means I want to build some sub problems. I want to use small sub problems, solve them, use their solution to find the solution for the whole um, for the entire subarray. Okay, so yeah, so can you think of some strategy? Okay, so okay, so let me first describe one strategy which is not optimal, which will also take order and square time. After that, we will see how to improve it to linear. We will bring it down all the way to linear. So let's just quickly see how to just think of a very obvious way of doing a dynamic programming approach. So I want to use dynamic programming, and what I'll do is I'm going to maintain a table, which is what you must have seen in the examples that you saw in the lectures, which is say edit distance or the grids or anything. So you maintain some sort of a table, and in this case the table could be maybe I'm storing my end index and a start index. So what do I mean by that? So let me write that 1 2 3 4 5 1 2 3 4 5 6. Okay, so what that means is let's say I have an array here of size 6. So 1 2 3 4 5 6, and minus 2 3 7 minus 1 3 minus 4. So let's say this is an array of size 6, and what does this table represent? This table represents, if I look at a row and a column, what that means is I'm looking at subarray starting at 1 and ending at 3, which is this in this case. And what will I store here? I'll store the sum of that subarray. So if I say 1 to 1, that is this subarray. What is the value stored at that? The value is minus 2. Similarly, if I look at 1 comma 2, then what is the subarray? It is the subarray which starts at 1 and ends at 2. So what will be the value? The value will be the sum of these two, which is 1. Now can you quickly like tell me what are the values in this row? What should be 1 comma 3? Okay, so 1 comma 3 is basically the sum of these, but what I'm going to do is I'm not going to now find minus 2 plus 3 plus 7. I'll not do that, because I already know the sum of 1 to 2, which is 1. So I already know this sum, this is 1. Now I'll just add 7 to it and write an 8. Similarly, if I want to find a solution for 1 to 4, I'll not start adding minus 2 plus 3 plus 7 plus minus 1. Why? Because I've already found this solution. What is that? The sum is 8. So if I sum all the way up to this, it will be 8 minus 1, which is 7. And similarly, now if I want to do the sum of 1 to 5, I'll not count all of them. I'll just look at the previous sum and I'll add it to the current value, that is 10. And similarly for 6, it will be 10 minus 4, which is 6. So I'll write this 8 7 10 6. Now notice that the left diagonal here is useless. So this part of the matrix is useless, because it does not mean anything to say that the array starts here and ends at 1, or it starts at 5 and ends at, because we always go from left to right. So all these values are anyway redundant, so you can assume that these are zeros. I'll just cross off this part. I'm only going to look at this part of the table. Only these are the values that matter. So can you now tell me what is the value at 2 comma 2?
3.
3. Exactly. And now if I want to, good. So now if I want to find the value at 2, 3, then how do I find that?
10.
10. So how did we find? You just looked at the previous sum and just added the element 7 to it. So you get a 10 here. And now if I want to find for this, we'll just add 10 with minus 1. So what are the entries?
9, 12,
9,
8.
sorry, yeah, sorry, what was it? Yeah, 9, 12, 8. Good. Similarly, can you tell me the remaining values now quickly? 7,
6, 9, 5.
9, 5. Good. Then minus 1.
Minus
Hmm.
2, minus 2.
Minus 2.
3, minus 1.
3 minus 1. And
Minus
finally
4.
minus 4. Okay. So now what is the maximum number that is there in the whole um, triangle?
12, man.
12. And so what is the subarray corresponding to it? I look at the row, I look at the column. It says 2 to 5. So 2 to 5, this is the subarray which has the maximum sum. So if you do this method, it's even if you just look at, if you just look at the values, there is a way to trace back what is the subarray. So the question only asks you to find the maximum sum. It does not ask you to tell the subarray, but the way you are designing the algorithm, there is a natural way to extend it to get uh, to the subarray also. This similar thing you have seen in the shortest path algorithm also. I'm just uh, I'm just recalling in case you can make the connection. If not, it's okay. So what we did in the shortest path algorithm was we sort of started writing these values one after the other, and we were looking for the shortest path by just taking shortest edge which satisfies certain constraints, and then we had a way to just use that value to trace back the entire path. So we didn't do anything special in the whole thing to get the path, but the way we designed the algorithm gave us a way to extract the shortest path. This is something similar is happening here. So yeah, so good. So what is the running time of this algorithm? So although I'm doing some sort of a saving, I'm not like adding over and over again. Still I'm doing some sort of non-trivial operations. So what is the running time of this? Okay, so let's find out. So what I'm doing at every step is um, I'm looking at this value, I'm just adding one element to it and writing this. I'm just adding one element to this, adding this. So basically what we're doing is at every step we are just doing a sum of two numbers. The sum of two numbers is something you can assume you can do in constant time. So for writing every entry it took you constant time. Okay, so now how many entries are there in the matrix? If it's of size 1 to n, it's an n cross n matrix, then how many non-zero entries are there in terms of n? You can just tell me like in terms of order. It's you don't need to tell me exact number, you can even tell in terms of order. So is it linear or is it quadratic, is it cubic, or okay, so
Order of n square.
it's order of n square, exactly. So this is order of n square, and that means you are not really doing saving in terms of time. Maybe there is some constant factor we are saving, but we are not doing much of a saving by doing this algorithm. Um, what I want is like order n time algorithm. Okay, so this is a very okay. So just to reiterate, so this is a very obvious thing to do, and it also gives you the correct answer always, and it's a dynamic programming strategy, which is yeah, which is clear. But what I'm not happy about is the running time of the algorithm, and that's why we want to do something better. So, do you see some kind of redundant calculation that we are doing, or something that we could have avoided and saved on time? Okay, so let's see how to do this. So let me just take the previous. So let me just take the example first. After that, we will write the algorithm. So I'll just take this example from here. So okay, so I'll just erase. Okay, okay. So now what we'll do is yeah. So now what we'll do is we'll make the following observation. Okay, if there is a subarray, the subarray has to end either at 1 or at 2 or at 3 or at 4, or basically it can end at any of these points. So this is something very common. I mean, it's very obvious, but we will see how we are going to use this very obvious fact to save on time. So the observation is very simple to make. Observation is that the subarray ends at an index I in n, at some index I in n. So what I'm going to do is I'm going to the sub problem that I'm going to solve is that I will find out what is the maximum sum of subarray that ends at I. Okay, so it could start anywhere. So let's say my I is 5. It could start at 1, it could start anywhere here. I don't care where it started. I'm just going to maintain what is the maximum sum that ends at 5. It may be starting from 2, it may be starting from 1. We don't care about that. Why are we doing this? Because notice that we'll make another small observation. We'll see why these observations are useful. This is also a very simple observation. 2 is also very simple. So let's look at my first element. Okay, what is the value? The value is -2. So when I make a subarray which has a maximum sum, should I include 1 or should I exclude? Should I include this or should I just start my exploration from here? So can it ever be that a maximum subarray started at 1 and ended somewhere else? For this particular example. So how many of you think it's possible? You can use thumbs up or emojis or whatever, or use the chat. I just want to understand whether you are with me. So can it happen that it starts at 1? Anybody who thinks no? Okay, so let's see. So you cannot start at 1. So in this particular case I'm saying You cannot start at index 1 because the value is -2. So if there is a subarray like this here, if there is some subarray here, let's say which has a sum of 10, okay, and let me just write it. Maybe this is the maximum subarray, it has a sum of, I'm not, okay, what is the exact sum here? 8, 9, this is 3, okay, maybe let me take this whole thing. 3 plus 7, this is 10, okay. Then I should definitely not include 1 here. If I include this index also, then the sum becomes 8. So having a negative number here is only going to decrease the value of my the sum of my subarray. It's never going to increase. So if there is a subarray with some sum, I should just avoid the negative one in the beginning. I'm saying, not anywhere in the middle. It cannot happen anywhere in the middle. Just in the beginning, you cannot take a -2. Okay, so these are the two simple observations that we are going to use to build our entire solution. So how do we do that? Notice that if I start at if I start at 1, then what is the maximum sum I'm getting at this point? What is the maximum sum of any subarray that ends at 1? What is that? It is -2, okay. And then let me look at 1 comma 2. So what is the maximum sum of any subarray that ends at 2? So what are the subarrays that end at 2? It is either 1 comma 2 or it is simply 2. If it's 1 comma 2, then what is the sum? The sum is 1, right? And if it is simply just the subarray of 2, then the sum is 3. So we are looking at maximum of the subarray 1, 2 and simply the subarray 2. Let me say sum of this. So sum of 1, 2 is 1, sum of 2 is just 3. So which is the maximum one? It is 3. So I'll write 3 here. Okay. Similarly, I'll do the same for the subarray 1, 2, 3. So what is the maximum sum of a subarray that ends at 3? Here is where we are going to use our observation, which is if there is a subarray that ends at 3, then I look at the maximum sum that I had up to point 2. I'll not really look at all the values earlier. I'll just look at the maximum sum that I had up to index 2. If adding that with 5 increases my sum, then I'll keep it. Otherwise, I'll simply start at 3. So in this case, what happens is, what is the maximum sum up to 2? It is 3. So if I add 3 and 5, then so maximum sum up to this point is that of 3. 3 plus 5 or 5. I'm going to take the maximum of this. So this is 8 and this is 5. So maximum is 8. So I'll take it. Okay. Now similarly, what about 4? What about 4? So what is the maximum subarray sum that ends at 4? You look at the maximum you had until 3, which is 8. Now I'll add -6 to it. That will make the sum 2. So 8 minus 6 comma -6, which is the maximum of this 2. The maximum is 6. So this is 2. So can you tell me the remaining values? Okay, so yeah, so let us write the remaining values quickly.
3 it will be.
Okay, good. So 2 plus 1 is 3. Then you get 10. Then you get 7. Yeah, can you tell the remaining?
12, 17.
12, 18,
Yeah, sorry, 18.
18, and then 16.
Uh,
Yeah, so what is the maximum value here? The maximum is 18, right? So the maximum is 18, and what does it tell you? It ends at 9. So yeah, so this value ends at 9. And what is the subarray? The subarray is, I think, this one, which starts at 5 and ends at 9. So if you sum the numbers from 5 to 9, then yeah, then this will turn out to be 18. And so where did we use these two observations? Notice that okay, sorry, maybe I think I did I make a mistake? Yeah, sorry, you do from 2 to 9. Yeah, yeah, you do from 2 to 9, then you get 18. Okay, so where did we use the fact that uh, yeah, I mean, the first and the second observation? The second observation we used when what happens is, if at some point, which it did not happen in this case, but if at some point this sum becomes negative, let's say this becomes -6, then what I'll do is I would rather not take it, and I'll start by taking my new element itself. So yeah, I think it happened at this point, or some point, I think. Okay, maybe I'm not sure if it happened in this example, but this is precisely what we're using. So if the consecutive sum until some point is negative, then there's no point in taking that subarray. I'd rather start by starting a new subarray search. And where did we use this? We use this to avoid solving this all the way everywhere. We just used, okay, what was the previous maximum, then I should add the new element, whether that gives me the new maximum, or should I just simply start where I am. So how much time does this take? What are the operations that we did? We just wrote this sum. That is all we did. So what are the operations we used? What is the time that it took? You can just tell me in terms of order. You need not tell me exact expression. So at every point, what are the kind of checks that we are doing? We are checking, let's say I want to find at 4. I'm just looking at the value at 3 and adding it to the value at 4 in the given array, finding the sum, checking whether the sum is, finding the maximum between the sum and the element's value itself. So this is just an order one operation. You are just adding two elements and checking for the maximum. This is something you can do in order one time per entry. Okay, and how many entries are there? There are n entries, because they are arrays of sizes. So this we are doing n times. So hence the total time that the algorithm takes is order n time. And why is this dynamic programming? Because I'm actually using my small subproblems to build a solution for the bigger subproblems. And I can use optimal solutions for these subproblems to build an optimal solution for my bigger problem. Now you can also, in this case, the value, it just tells you the value here, right? That the maximum sum is 18. You can actually do some kind of a backtracking here. You can, if you use some extra memory like order and memory or something extra, then you can actually find out what the subarray is. You can even find out the starting and end index of that, and so on. So it's not very difficult to do that. It's something similar to what you did in the shortest path algorithm. So I'll not, I mean, the idea is similar, so we'll not get into it, because we want to focus on the strategy right now. I mean, practicing the strategy and understanding it clearly. So we'll not get into it, but you can even try doing that. So you can take it as a homework. So are there any questions about about this particular problem that we discussed, the maximum subarray sum problem? sorry. Okay, so if yeah, so if there are no questions, we'll look into another problem. So it's called knapsack problem. Let me write the problem. So this is called knapsack problem. And what does the problem say? So you basically have some n objects. Okay, so you have item 1, and maybe I'll say item 1, 2, 3, 4, all the way up to n, and there is some value that is associated with the object. So that means maybe object number 1 is some diamond and it has a lot of value. So let's say the value is 100 for me. Maybe item number 2 is some stone which may be not that valuable, so the value is 5, and so on. So there are some arbitrary n items and there is some value. Let's assume it's positive. Okay, positive. Let's not assume it's negative right now. Okay, so let's say you have some values that are associated with each of them. Okay, and there is also some weight. So they also have some weight. So for example, the diamond that you have here, okay, it has a value of 100 but it's also heavy. So it could be that this weighs some 30 units, and let's say this item 2 is not that valuable, but maybe it's not very heavy, so let's say its weight is 1, and so on. So it's not necessary that valuable item has less weight. There's no correlation. I'm just arbitrarily writing any numbers, 2, 15, and so on, let's say. So what we know is there are some n items that are given to us. They have some value and they have some weight. Let's now assume that none of them are negative. And what you have is a sack. So you have some sack here, and it has, you want to pick this item. So you're going to pick this item 1, put it here. Pick item 4, let's say you like it, you put it here. So there is one catch though. Your sack has a capacity. It can't hold more than some amount of weight. So let's say it can only hold weight up to W. I can't do more than that. So now there is some kind of a constraint. I can't just arbitrarily take any item and keep on putting. What I want to do is I want to maximize the value that I can have. That is the most natural thing to do. So there is some constraint on weight, but I want to respect that weight constraint and still achieve maximum value as possible. So let me just write this in terms of input output form. Input to you is an array of n items. They have some weights, they have some values, and there is a maximum capacity of W. And what you want to output is the maximum value that we can attain by picking some n items such that their total weight is still at most W. And let's say for now, let me just assume that there is an infinite supply of these elements. So I'm not saying that this item you can only pick once. You can pick it as many times as you want. Okay, there's no limit on the supply of them. They're unlimited, but you can't pick all of them, of course, because there is a weight capacity. So this kind of a constraint is called unbounded. This is unbounded version. So I'll just write it here. Okay, what do I mean by that? You can pick items, as many items of the same kind as you want. Okay, So is the problem clear? um, okay, so yeah, so just to summarize, you have these items, you have weights and values, and you have a capacity. You want to respect the weight, you can't take more than, you can't take the, make the total weight more than W, but you still want to maximize the value based on these constraints. So what is a natural strategy that you can have to solve this?
Ma'am, we can sort the array according to their value and then fit it until it gets full.
Okay, so if you sort them according to the value, then okay, so then yeah, let's say you sort them and let's say the capacity is let's say 60 for me, and then the values are like this, 100, 30, but then if I do 15, then I can make 75, and if I do um, yeah, maybe I'll just say, you're saying sorting on values or sorting on weights? Sorting on values, right?
Yes, ma'am.
So let's say this is one example that I have. Then if you sort on values, what will happen is you will pick this item 1, and the current value you have is 100, the current weight you have is 30. Now I still have a capacity of 30 more that I can take. So again, because it's sorted and you're allowed to make multiple, you're allowed to take multiple times, you will again end up taking 100 and a weight of 30. So eventually you have gotten total value of 200 within the weight of 60. But let's say I don't do that. What is the maximum I can do by using this? If I just pay 3 units of weight, I can get a value of 75. So I'll get 75 into 20, which is 1500, which is a value of 1500 if I don't use this, if I just use this. So um, yeah, so this is a counter example, right? Because what's happening here is, although its value is not as large as the largest as the other one, I'm still paying a very small price. The weight is very small, but it's adding a lot of value with respect to it. So I'll just take these kinds of um, yeah, these items, and then that will beat the greedy type approach. Is that clear? Is it clear why it will not work?
Yes, ma'am.
Okay, good. So then what can we do? Any other ideas? Or can you try identifying a sub problem here to solve the bigger problem? Okay. So greedy approach about using value over weight. So okay, so let's do this. What Ramanathan is suggesting is that you'll be greedy. So, and what you'll do is you'll find value over weight of an item. So let's say value was 100, 30, and you had 75, and what was this? This was 3. Then you had, let's say, 20, and maybe let's say 10, 4, and 2. So then what we'll do is we will find out this value over item. So what is this? This is it's a 10 by 3, 3.33, something like this. This is 25. Yeah, 25. This is 2 and this is 2. Okay, so what is suggesting is that you find the value over weight of this. So that means what is the item for which I can get maximum value by paying as sorry, this is not item, sorry, by paying as small um, weight or as small cost as possible. So in this case that is 25. So then what he's saying is you just keep taking these 25 of yeah, of these, and then you'll end up getting the maximum. Okay, but okay, so let me come up with the counter example. So okay, so maybe this is maybe not a very good example, but let me try to come up with one example like that. So okay, so basically the problem can happen when the weight that you have is not divisible by this number. So let's say the weight is something like 76, and let's say that, yeah, let's say I have 3 here, let's say 3 here, 9 here. So okay, this is still okay. I don't know if this is the exact counter example, but okay, I'm trying to say that the problem will arise when, let's say you take 25 and you're going to take 2 items of these, and that will make a weight of 50, and yeah, let's say this does not exist for now. Yeah, and then you this makes a weight of 50 and you have a value of 150. Okay, and now you have some 16 of these, yeah, sorry, some 26 weight that is remaining with you. Okay, so you'll actually take, sorry, you'll take 3 of these. Well, just do 74. If you take 2 of these now, then you have a weight of 50, the value is 150, and you have a capacity of 24 that is left with you. And this you cannot satisfy using yeah, using these, but yeah, but you can use this to fill up the rest of them. So this is not a counter example yet, but what I'm trying to say is, if the number is such that by taking these values, you'll eventually end up with some number which is remaining, which you can't satisfy using these weights because it's very large, but you also don't have the remaining items to fill that weight. Okay, which can happen if, for example, this is larger than maybe you have some 23 remaining here and this is some 24, then you can't even use this. So there is a whole lot of capacity that is going wasted because you made a greedy choice here. But if you would have taken this smaller and smaller items, maybe some combination of these, such that their combination adds up to the value, the exact value of the weight, and therefore even though you are losing on the values of these items by small some factor here and there, you're losing something by not taking the largest one, but because I'm able to fill the whole gap, there's nothing in the sack that is going wasted. Maybe the total capacity of the total value of these elements now is the total value is still larger, it surpasses than this. So I mean, am I at least intuitively conveying the problem with this? Although I don't have a counter example ready, does this convey what is wrong? Ramanathan. Okay, so I'll just try to explain it one more time. Although I don't, it would have been nice if I had a counter example ready, but let me try now. So let's say you have some capacity of, let's say 75 again. Sorry, what was that? 74. Okay, let's say there is some capacity of 73, and you have some items of this weight, this value over item of 25, and yeah, so what you did was you took those items, you packed those heavily. So what I mean by this is you are occupying this much of weight, and you kept on doing as much as possible, and now there is some gap in the sack, there is still some capacity that is remaining. Okay, but I can't use this big item because I don't have that much space. But the problem also is that I can't use the remaining smaller items because they are also not large enough to um, I mean, sorry, they're also not small enough to be covered here, because the gap that is left is so small that now none of the items can occupy it. So there is some space here that is going wasted. Okay, so there is some greedy thing you did to try to optimize. So there is some value you got here. Okay, but then there is some space wastage happening. Okay, so this is just intuitive because I don't have an example ready with me right now. But I'm saying what you could do is, maybe I'm not being greedy. I'm actually looking at some items for which I'm actually paying more weight, more weight for the value. It's possible maybe it's not this, it's not optimizing, but what is happening by doing that is, if I look at the sums of these weights, maybe they are like optimizing the space so much that maybe some combination of items here, they're optimizing the space so much that there is only limited wastage that is happening. So do you understand what I mean by, I mean, you understand, right, what I mean by this, at the wastage part? Okay, good. So now I'm saying that it is now possible that if you sum up these values, although I agree that these are not as value worthy with respect to the weights as these, but what happened is I managed to pack up a lot of those items now, and therefore as a collective sum, maybe the sum of this total sum is now actually greater than this value v1 that you had here, because there is very minimum um, space wastage that happened. So I managed to pack it very fully, and therefore now if I add the values, I can actually get more. So this is not always possible, but you can come up with examples like that. So now is this okay? Okay, good. So do try to come up with this, but this is actually a very nice strategy of doing this. So can you come up with a scenario where this will work? So can you just modify one constraint in this whole example? You just have to relax one constraint so that this greedy approach works. So there is something here that's not allowing me to do this, right? So this wastage that is happening is not allowing me to do that. So how do I relax that? Why is this happening? Limited item, you have unlimited items, but the problem is that you are allowing me to only take integral number of them. So I take an item, I take whole of it, I can't take half of it. If I allow you to take fractional item, then what you could do is maybe like this weight, this is maybe yeah, maybe this is like 10, and the weight of my most valuable item was 15. So earlier I could not do, but now I'm saying something like you take 2/3 of that item. So then if you do 2/3 of 15, you will actually fill this whole thing. So you're not taking the whole item, but you're taking 2/3 of the item, and therefore you are able to now fully use the sack because I'm allowing you to take fractional values. So this is called fractional knapsack, where you can actually take any fraction of item. So it need not be integral, you can take fractional many items, which right now does not make sense if you think of these as discrete item, but there are scenarios where it makes sense. So this is indeed a valid greedy, I mean this is a correct solution for a for a fractional knapsack problem, which is a greedy strategy. So but it will not work in the case when I'm imposing integral constraints, that an item will either be taken or not be taken. You can't do like taken half or something like that. So is this clear? Okay, good. So now we know that this does not work, or although we don't have an example, I couldn't give one yet, but if I come up with something, I'll add it into these notes before I before I post it on the drive. Okay, but yeah, believe me on that for now. And can you think of some DP, some dynamic programming sort of, or like a sub problem that you can use to solve the bigger problem? Okay, so let me just define the variable, maybe that will help you to identify the subproblem. Okay, so let me say that m of w denotes the maximum value that we can get when the knapsack has capacity of W remaining, or let's say remaining capacity of W. Okay, so that means I have a capacity of W that is remaining with me, and I want to find the maximum value that I can get for that particular knapsack. Okay, so how do we do that? So this is going to be maximum of yeah, so let's say my items are I1, I2 up to In, their values are V1, V2 up to Vn, and their weights are W1, W2 up to Wn. Okay, so if I take the first item, then I'm already getting a value of V1 with it, right? So the total value will have this plus, now it's same as solving the problem for weight W minus W1, because in the whole knapsack that I had, I've taken this item 1 and I'm already occupying the weight of W1 from it. So the remaining weight I have is now W minus W1. So it's same as optimizing, finding maximum value that I can get for this particular part of knapsack, and the value that I get for this, if I add it with the value of first item, I'll get the value of the whole thing. So this is just saying that find the maximum value for the smaller subproblem and add it with V1. That will be the value of your whole knapsack. Similarly, I don't know which item to take, right? It could so happen that maybe taking the second item actually gives me better. Maybe taking first item is not good for me. Maybe second item is better. So V2 plus M of W minus W2, and so on. Same thing happens for V3 and all the way up to Vn plus M of W minus Wn. So then to solve this, we are recursively going to use the same formulation. So M of W minus W1 will be max of, you do the same thing again and again. So is this formulation okay? Is this relation making sense? what we wrote here. Do you want me to repeat it? Okay, so if it is clear, then can someone tell me what is the value that I want to find? What is the final answer? What is the value that I should write here, which will give me the solution for the problem that I asked? Okay, so what does M of capital W denote? By our definition, it means what is the maximum value we can obtain for the knapsack whose capacity is capital W. And this is exactly the problem that we asked, right? You have this knapsack with capacity of W and you want to maximize the value. So M of W is precisely denoting what I want to find out. So then what it will do is basically it will take this M of W and it's going to find M of W1. So V1 plus M of W1, V2 plus M of W2, sorry, and so on, Vn plus M of W minus Wn, and then I want to find a maximum value for this, right? So then you are going to explore this again. So this will be V1 plus M of W minus 2W1. This will be V1 plus V2 plus M of W minus W1 minus W2, and so on. So when will this terminate? If this weight eventually becomes negative, that means I can't add that item. Then you will just simply write a 0. That means you can't take that item. So yeah, so then you will terminate. So this is how the recursion tree will look like. Okay, so is this clear? Okay, so you can even you can do both implementations of it. You can do a memoization version of it, you can even do an inductive version of it. So if you write it like this, it, yeah, I mean, this is the recurrence relation you have, and then the base case would be that M of yeah, so M of W1 would be would be V1, and so on. M of W2 would be V2, and so on. And M of some weight W where W is less than 0 is 0. This is just to make sure that the weight cannot go negative. If it goes negative, then you just write 0 and start terminating from that branch. So yeah, so if that is clear, then try the same example but with but now I don't allow you to repeat the objects. So if you take an object, you're going to take it at most once. You cannot take it multiple times. So this is the bounded knapsack version. Where an item I can be taken at most once. So then what is the strategy? How does it change? Any ideas how we can modify the previous answer? Okay, so let me just give a hint and then you think about it. Let me know if you have any ideas that come up. Okay, so okay, so earlier what we did was we denoted m of w by the maximum knapsack weight, I mean value you can obtain, value that can be obtained by with weight, with capacity at most w. Okay, and now why this does not work? Okay, first of all, is it clear that the same thing does not work, right? Because in the previous one you could have optimized by taking the same item again and again, which is not allowed in this case clearly. So then what you do is we're going to modify our variable by saying that m of iw is the maximum knapsack value that can be obtained by choosing items up to I. That means I have labeled my items with the numbers 1 to n, and I'm only allowing you to choose from items whose label, whose number is at most I. So when I say that I is 3, that means you can only choose from items 1 to 3. So this is what the I represents, and the capacity of the knapsack is at most W. Okay, so now using this, so you might have noticed by now that this extra I that we introduced is something similar to what we did for the all pair shortest path. So just to show you, so this extra k that we had introduced there is to tell you that you are allowed to use the nodes whose label is up to k, and then you go from k to k minus 1, and yeah, sorry, this should have been k minus 1, that, yeah. So that's how you keep on reducing this sub problems from k minus 1, k minus 2, and so on. So this is the same idea that we used here. So I'm just introducing one more variable to tell uh, which items are allowed to be taken. So then if the meaning of this is clear, can you tell what is it that we want to find? So the quantity we want to find in terms of the new variable, what is it? M of so W is just the capital W. It is the capacity that is given to you for the knapsack. But what is I here? What are all the items that I'm allowed to use? I'm allowed to use any of the n items, right? So initially I'm allowed to use any of the n items. So this is simply m of n comma w that I want to calculate. Now how will I do that using my DP approach? So DP approach says that m of I comma w is the maximum of either I take the ith item or I don't take the ith item. It's possible that taking ith item gives me the maximum. So these are all the items you have. Maybe taking this is going to give me the maximum. In that case, let's say I take the item. Then what is the value that I get? The value I get for that is Vi plus, then I want to maximize the remaining weight. So this is m of I minus 1. And what is the W? So what is the weight that I now have to maximize? So this is similar to what we did earlier just now. So W is the total weight I have, and I've already picked the item I. So the weight for that is WI. I'm already paying a weight of WI for that. So what is the remaining weight I have? I have W minus WI. So this is W minus WI. Or it can so happen maybe I get the maximum by not taking this ith item. In that case, I'll not take it and look for the new maximum by looking only at the previous items, and then the weight does not change because I did not take that item. So is this clear, or are there any questions about this? So compare this with the previous relation we had and see how it is different from this one. So just let me know if you need further explanation on this. Okay, so let me just repeat this one more time, although yeah, just for the sake of making sure that everyone has understood. So what we did was we let this m of iw denote maximum weight you can value that you can get in the knapsack, whose capacity is at most w, but you are only allowed to take items which are labeled from 1 to n, 1 to I. Anything that's greater than I will not take. So what is our problem? Our problem is I want to maximize the total value where the weight that is given to me, the capacity is bounded by capital W, and I'm allowed to choose any items from 1 to n, but I can't take them multiple number of times. I can either take them or leave them. That's it. So then what you do is you look at so this is what the quantity that we defined earlier, which I want to maximize. So when will I get the maximum value in my knapsack? It is either that I choose the ith item. In that case, the remaining weight that I have here is W minus WI, and this I want to maximize. So that is nothing but m of W minus WI. And what are the items I'm allowed to use? I've already used the ith item, right? So then if I'm allowed to use only from items 1 to I, which is what we said here, it comes from there, and I've already used the ith item, then I'm anyway only using from 1 to I minus 1. Therefore I write I minus 1 here, and by adding this ith item I've already paid a value of Vi. I'm already getting a value of Vi. Therefore we are adding the value of Vi to the maximum value you can get for this subproblem. Or it can also happen that I don't have to take the ith item. I have to leave it in order to maximize. In that case, what will the knapsack look like? It will look like the same. I still have to make a total weight of, still have that capacity, but still I'm not going to choose I because I took a decision of not taking it. Therefore you have an I minus 1 here, but the weight remains the same because I did not take that item, hence I did not lose any weight, nor did I get any value. So there's no addition of Vi, there's no subtraction of Wi. Okay, so is this clear? Then we can have base cases based on whenever I minus 1 becomes 0, you just make the value of the whole thing 0, and whenever it's 1, then it's simply the value of W1, and so on. So you can so you can have the appropriate base cases. That's not very difficult to do, but the main idea here is to understand how do we get this recurrence relation. Once we have this relation, you can do both versions. Okay, so yeah, so if there are any questions about anything that we discussed so far, yeah, feel free to ask. Okay, so if there are no questions, we will do one quick application of knapsack. So this is one quick application of what we saw just now. So I'd say this is the coin collection problem. Okay, what does that mean? I have some denomination, so I have some coins with me. Let's say I have rupee 1, rupee 3, and something like that. So I have some. So I mean, just don't worry about whether they exist or not. Just I'm just writing some random numbers here. I have some denomination, some coins here. Okay, and I want to make a total of 100 rupees with it. So how can I do that? Either I can take all 1 rupee notes. If I just use 1 rupee coins, all rupee 1 coins, if I use, how many do I need? I need 100 of them. But if I use rupees 10 coins only, then I only need 10 of them. Now 100 is a nice number where you can divide with all these, but let's say if I had something like 96 here or something like that, then there are so many combinations that you need to consider. So the question is, I want to make a total of some value. So I have to make a total of some rupees r, and I have to use these denominations. I can use them as many times as I want. So this is, you can think of this as an unbounded version of knapsack, where you are allowed to take the item as many times as possible. But what I want to do is, I want to minimize the total number of coins that are used. Okay, so in this case it's very obvious that if I use all rupee 10 coins, then I'm going to make a total of 100 by just using 10 coins. So in general, if I just give you some rupee r, I want to, and these are not the exact denominations that are given to you, this could be any numbers, any non-zero numbers. Then let me say x1, x2, or let's say p1, p2, p. So the denominations you have are of values v1, v2 up to vn. These are the n coins you have with different values v1 to vn. You can use them as many times as you want, and the total you want to make is total sum that you want is that of rupees r. And what you want to do is, you want to minimize the number of coins used. So how will we do, how can we use dynamic programming to solve this? Or you can do freshly, you can solve this with a fresh perspective, or you can use what we did earlier. So this is similar to knapsack, but you have to think of this problem or formulate it in terms of the knapsack problem, and then you can just simply lift the solution for the knapsack problem to solve this problem. So either is okay. So just take some time, maybe think about it for a couple of minutes, and let me know what you think. So then I'll just wait for some time. So any ideas, if you have, feel free to write or unmute and let me know. It's not necessary that it's on the correct lines. Any idea is a good idea. Okay, so one thing you can do is, of course, you can try to make your own variable and define a new definition for it, and define the relation, recurrence relation, and so on for it. That is something you can do. But what I want to do is, I want to think of this problem as an application of um, okay, as an application of the knapsack problem that we had. So then what I want to do is, if I want a knapsack problem, then I can think of this as a sack that I have, whose capacity is r, because r is what I want to make. So the capacity, or the w that I had, the capacity w, so I'll write this as knapsack formulation. And the capacity w corresponds to the value of r here, because r is the total number of amount that I want to make. And the values v1, v2 up to vn, these are the same as the amount the denomination has. If the coin is of rupee 1, then v1 corresponds to 1, and so on. So it's basically the value that the coin has, that's written on the coin. And what are the weights of the coin, because this is something we had in the knapsack. So um, so notice that the weights correspond to the fact that we want to minimize the total number of coins here. So earlier, um, so can you think of something? Can you think of what should I assign to w1, w2, and so on? Because with the coins, I don't have weights associated with it. They are all equal for me, but I want to minimize the number of coins that I use. So um, if I think of these as weight 1 coins, if I think of them all having weight 1, that means I want to use as few coins as possible. So is this okay? So this is basically same as the knapsack problem. Also, the question is whether it's unbounded version or the bounded version. So in the bounded version, you are only allowed to take it or leave it, but in the unbounded version, you can take it as many times as you want. So in this case, we said you have infinite supply of coins. You can take, if you want 10 rupee coin, you can take 10 rupee coin. There is no limit on the fact that you can take it only once. Therefore, this is the unbounded version. So this is also something that we identified. Therefore, what you have now is an instance of a coin collection problem, and we have converted it to an instance of unbounded knapsack problem. And whenever we say knapsack, we mean integral knapsack. If I want to say fractional, then we will specify that it's fractional knapsack problem. Okay, so this is something that we did, and now we will simply use our solution to the bounded knapsack problem, which is this, and then we'll use this dp solution to to solve the problem. So just if you get the idea, then can you roughly find out what is the running time of this? What are the parameters that it will depend on? Roughly what is the running time? Okay, so so let us see. In the previous case where we saw this subarray problem, it was something like order n, it was linear. But here you have something interesting happening. So notice that here you have a weight which is coming into play. The weight capital W, m of capital W, which you want to find out. So if W is very large, so for example, if W is like say 10 million here, and the denominations, let's say the coin problem, W is 10 million, so I want to make 10 million rupee amount, but let's say I only have the maximum coin that I have is of value 10 rupee 10. So what will this formulation do? It will just subtract rupee 10 from the 10 million, then from the remaining amount I'm again going to subtract 10 rupee, and so on. So this will happen like how many times? This will happen 10 to the 7, this is the amount I had, divided by the largest denomination I have, which is 10. So this will happen like a million times. So 1 million times you are going to keep on having to subtract 10 rupee 10 rupee 10 each time. That means the running time of the problem depends on how large the weight is. If the weight was very small, if I just have to make 20 rupee, I would just do 10 rupee, I'll just take my 10 rupee coin, then I have a remaining weight of 20 minus 10, and which is 10. I'll take another 10 rupee coin and I'll be done. This just stops in 2 steps. But if the value is very large, I have to keep on doing this again and again. So this kind of algorithm, so if you analyze this, actually the running time of this turns out to be order n times w, where n is the number of items, w is the weight that you have. So generally all the algorithms that you have seen so far only depend on the length of the array, or let's say yeah, basically the size of the input. But this is the first instance I think you might have seen where it also depends on the value of some other parameter. So these kinds of algorithms are called pseudo deterministic algorithms. Why is that? Because they are deterministic, pseudo polynomial time algorithms. So why is that? Because they are the rest of the factors are polynomial. If you ignore this w, the rest of the time is polynomial in terms of n, but there's this extra factor which is the value of it, because of which you call it pseudo polynomial, which means if that value is very small, then you are actually running in polynomial time, but if the value is large, then you are actually doing worse. So yeah, you can actually write this write an algorithm for this with all the base cases and actually see that the running time turns out to be this. And there are again several applications of knapsack problems. So there are lots of problems that can be converted into a knapsack instance, and then you can just simply use the solution to knapsack to solve them. So few resources, few nice again same references where that I've been pointing out I think throughout each week. So same references, you can use this Papadimitriou, Dasgupta, Papadimitriou book. This is called Algorithms. Then you can again Kleinberg Tardosh also has and CLRS, of course. So all the three books are a very good resource for studying dynamic programming, and they also have lot of examples to practice. So if you want to practice more, then these are some good resources. And just one more thing I want to mention before ending the session is that you know by now that greedy algorithms are good, but they don't work all the time. They may work sometimes, but they don't work all the time. Sometimes you're doing really bad by just being greedy. And same thing happens with dynamic programming also. Not every algorithm has not every problem has a dynamic programming approach. Sometimes it may work, sometimes it may not work. It can also happen that DP and greedy, both of them work together for the same problem. Maybe different sub problems are being used, but they are still good. They can both solve the problem. It can sometimes happen that greedy works but DP doesn't work, or other way around. But there are also problems where none of them work. Then you have to do something tricky to solve them. So what we'll do next week is we'll call these hard problems which we don't know how to solve efficiently. So this kind of hard problems, if you come across it, how do we classify them, how do we identify them, and if they are hard, then what can we do to if we come across them. So do we just leave it, or do we come up with something else creative? So these kinds of this intractable problems, and how do we deal with them. So this is the lecture content for the week 8, and we will also look into some nice problems on this for in the next week. So next week again we are meeting on Friday, same time 6 p.m. to 8 p.m. and after that I think the final class would be on the summary class would be on the Monday, the upcoming Monday, which is I think 17th March, I think. Okay, so I think, yeah, we'll meet on 7 p.m., 7 to 9 p.m. There will be announcements that will be made, but yeah, I just want to announce it one more time. So if there are any questions regarding what we saw today, I'll wait for some time. Otherwise, yeah, feel free to leave, and thank you for joining. Okay, so yeah, I have started the recording. Okay. So what we'll do today is, yeah, like we said last time, there are several strategies that you saw throughout this course. One of these is greedy strategy, and the other was dynamic programming, and there are several things that we learned. We saw data structures and so on. But then the question that arises is, is whether it's always possible to find polynomial time solutions. So initially we discussed, um, when we saw this order notation and so on, asymptotics, which was the weak one. So we saw what do we mean by polynomial time. Polynomial time basically means it's order of n to the c, where c is some constant. And then we also saw something called exponential time, where where you have something like order 2 to the n, or some constant c to the n, something like that. Okay, and we said that this polynomial time is good for us because that means our algorithm is fast, and exponential time is bad for us because that means that our algorithm runs slow, which is not what we want. Okay, so the question is, whether it's always possible to find polynomial time algorithms for any problem. So you saw, for example, you saw shortest path, and what is the running time of this? Is it polynomial time or is it an exponential time algorithm? um, okay, if you recall, anybody? Okay, so this was indeed a polynomial time algorithm. It was roughly bounded by order n cube. So this is indeed a polynomial time algorithm. Then you also saw, say for example, edit distance and so on. So yeah, maybe minimum spanning tree, MST. I'll simply call it. So where does MST fit in? Does it fit in the polynomial time regime or in the exponential time regime? I'm audible, right? Can you at least confirm if I'm audible? Can someone please confirm if I'm audible, or at least, I mean, okay. So okay, so you also saw this MST algorithm, which also has polynomial time algorithm, and the question is it, yeah, so the question is it always possible to find polynomial time algorithms? Just a second, yeah. To find polynomial time algorithms for any problem, for any given problem. So what do you think? Okay, so um, okay, so I mean the answer is it may or may not be possible for some there are some problems which you can do in exponential time but you can't do in polynomial time. But there are also problems that are in between where we don't know if there is a solution which is efficient. So that is, we are looking at that kind of problem. So there are problems. mm, okay, so then there are problems where there is a easy solution. By easy I mean that there is a polytime solution. Okay, and then there are problems where you need exponential time. Okay, we will not worry about that. But then there are problems that are hard in the sense that we don't know whether there is a polynomial time solution. So let me just highlight this fact that what we're saying is, we are not saying that there does not exist a polynomial time solution. We are saying we don't know if it exists. So there do exist such problems, and these are the kind of hard problems that we will focus on in the content of this week. And so majorly our theme is, um, what do we do then if we don't know if there is an efficient solution? There may be, but we don't know. So then how do we deal with it? How do we classify? So can we systematically classify such hard problems? That is one thing. And second is, how do we get around it? How do we um, I mean, how do we deal with this difficulty? Okay, how do we deal with it? So these are the two things that we will look into. So yeah, so just to recall what you did in the lecture. So these kinds of problems where you actually know that it has a polynomial time solutions, we put them in the complexity class P. P denotes all the problems which have efficient solutions. So for example, sorting will be in P, or okay, maybe I'll not put it there, but let me define what P is formally. So there are two classes that we will, this is always the question of easy versus hard. So P is easy for us because we have efficient solutions, and NP is what we don't know, is whether, I mean, we don't know if it is easy. So let me define it. So whenever you define this, you define with respect to the decision problems. So what is a decision problem? A decision problem is simply a yes or no type answer. So for example, if I have to define a decision problem for shortest, or let's say let me define reachability. So I'll define a problem called reachability. I'll call it reachability. What does it mean? What does it say? It says that the input to you is a graph G, and you have two vertices S and T. S is the source and T is the target. So this is source and this is target, and the output is yes if there is a path from S to T in G, and no otherwise. Okay, so this is the problem. So when I say a decision problem, what it means is you are given some input and the answer is, the output is always yes or no. It's never non-binary. So for example, if I give you sorting, that is, I give you an array and ask you to output it in sorted form, it's not a decision problem because it's not saying any yes or no type answer. So whenever the answer is yes or no, those are your decision problems. Okay, so yeah, so for example, another example of a decision problem can be factorization. I'll give you a number. So another example would be factorization. Sorry. Yeah. Another example would be factorization, where I give you as input some number, some integer n and another integer k, and I ask you yes if k is a factor of n and no otherwise. So this is another example of a decision problem because it just gives a yes no type answer. So we'll look at all these decision problems and check if there is an easy solution for it. If there is an easy solution, then we will put it in the class P. Okay. And okay. Yeah, so for example, if I give you a number and I ask you to check whether it is even or odd, so if it's even you should say yes, if it's odd you should say no. Then does this problem is this problem in P? You can even use the chat. I mean, if you want, if you don't feel, if you don't want to unmute, you can even use chat. So I encourage you to speak up. Okay, so let me just define this problem called odd, where, so this is the first example, this is the second example, this is the third example. Input is a number n, so imagine this is an integer, and output yes if n is odd and no otherwise. Okay, so then given this problem, what is my algorithm? I'll simply I'll simply look at the number divided by 2. If the answer is 0, if the remainder is 0, then I'll say no, it is not odd. If the remainder is 1, then I'll say yes, it is odd. So this is the simple algorithm where I'm simply doing a division operation. Therefore this problem is trivially in P. So inside this class, this, if I denote this set, so if this set denotes the class P, then odd is somewhere here. Okay, and there are many other problems lying here. Okay, now we will look at this class called NP. So what happens is there are problems for which maybe I'll so this is our class P, where for example we have just now put odd, this problem odd, of testing whether number is odd. Then there are examples where it's not so easy to find a polynomial time algorithm. So for example, let me say checking for primes. Okay, so the input to you is an integer n, which is given in binary encoding, and you should output yes if it is prime and no otherwise. So does this problem belong to P? Can I have a polynomial time solution for this? Any guess? Okay, so if the trivial algorithm that you try, what is the trivial algorithm? Trivial algorithm is you look at all numbers from 1 to n minus 1, check if 1 divides n, check if 2 divides n, 3 divides n, and so on. Check if any number less than n divides n. If there is such a number, start from 2 maybe. If there is such a number which other than 1 and n which divides n, then you declare that it is not a prime. Otherwise you say that it is a prime. But the problem with this algorithm is, what is the running time of this? So let me write whatever I said. So what is the so what is the trivial algorithm for prime, checking whether a number is prime? The algorithm is so input is n. So what you do is for each I in 2, 3 up to n, check if I divides n? If yes, then return no, then that means it is not a prime. Otherwise you continue. At the end of this loop you return yes. That means if you never found a factor, then that means the number is it is prime. Okay, so what is the running time of this algorithm? I'm going through um, yeah, I'm going through all the n minus 2 many numbers and checking if it divides n. So these are some n order and many operations, and then checking division. Let's say it takes order one time, so altogether this algorithm runs in order n time. Okay, but the problem is, although it looks like it's polynomial time algorithm, actually it's not. So why is that? Because the catch is that the number n that is given to you is not given in decimal form. So for example, if I give you the number 42, the input won't be written as 42. The input is actually going to be written in the binary form. That means 101010, something like this. So what is the size of this input? The size of this input is the number of is the number of bits that you used, which is 6 in this case. So if I want to represent a number 2 to the n, how many bits do I need? I need n bits to represent, because if I do n all ones in the n bits, then I can produce a value of 2 to the n minus 1. So okay, so that means when the input is given to you in binary, so the catch is okay, so don't get yeah I mean confused because of this order n. So so what we said is that the input is given to us. So the catch is that the input is given in binary. So that means if I want to represent a number, an integer n, I only need log n many bits to represent. Okay, so this is what it meant, and that's why when the size of the input that I have is log n, when the input size is log n, the running time, if I call this capital N, the running time in terms of the input size, which is capital N, is order n, which is same as order 2 to the capital N. Is this fine? So in terms of the input size, which is n, the running time is actually exponential. So I'll just let you see this again, and please ask me if there are any questions at this point. Okay, so what we did is we saw a trivial algorithm for checking if a number is prime, which is go through all the numbers less than n, check if it divides. If you find such a divisor, say no, it's not a prime, otherwise you say yes. And we saw that this takes order n time, where n is the value, is the integer that you have. But we said this is not polynomial time algorithm because the input that is given to you is in binary format. So if I want to represent a number like 42, I don't need a 42 length string. I only need a 6-bit string, which is 101010. That's how I will write 42. So the catch is that the input size is actually logarithmic instead of being n. It is log n. So in terms of that, the time that is being taken is order small n, but small n is actually so from this you know since log n is n, this means that n is 2 to the capital N, and we just substituted that. Therefore the algorithm, the trivial algorithm that you have for prime, actually runs in exponential time instead of polynomial time. So this algorithm is an exponential time algorithm. Okay, so is everybody convinced why this is an exponential time algorithm? If there is any part that you want me to repeat, please feel free to interrupt. Okay, so if this is clear.
Hello,
Yes.
ma'am. Like for the upcoming DA exam, if we study the quizzes, will it be enough?
So I can't exactly say it would be enough, but it should it should be like a good enough practice, but it won't cover all the portions. The quizzes, the questions in quizzes are only taking some selected topics. There are some topics that are in the lectures but not there, which may come up in the exam. So
Yes, but if we is to go through the previous year quizzes and previous year question paper, is it okay?
is it okay in the sense? Are you saying? I mean, are you saying that would be the syllabus, or I mean, just contain to it?
Ma'am, means for the exam, will it be enough?
Yeah, yeah, I can't guarantee that would be enough for the exam. So first of all, I don't even know who is setting the exam, so I don't know what kind of questions there would be. But my suggestion would be, go through the quizzes. So those are the important topics, but there can also be questions outside the quiz topic. So
Yeah, yeah, yeah. Ma'am, and one more thing is that, like, will they ask programming type questions? Will we should write a program, anything like that?
um, I'm not aware of this, but I think it should not be, because the assignments, the coding assignments that you were submitting the code, right? I mean,
Yes.
so that is something that probably you can't do in a written exam. So
Okay, okay.
um,
Ma'am, and can you tell anything about the question pattern? Like how many questions and negative marking will be there or not anything?
yeah, actually I have no clue about the exam. I don't know who sets it and so on. So I yeah I yeah, I wouldn't be of any use here. So but yeah, you can actually use the portal, right? There are people who manage the course. So if you ask it there, maybe they'll reply to you. So do it
Like in the discussion forum, I
in the
should ask.
discussion forum. Yeah, yeah. Do
Okay,
it.
okay,
Yeah.
okay.
Okay.
Okay, okay, fine. Thank you.
Okay. Sure. So okay. So yeah, I hope everybody is with me when I say that this running time is actually exponential. So yeah. So the question is, we don't know whether, I mean, as of now we didn't do anything better. We just did a trivial algorithm. Maybe there is a clever way of solving it. Okay, so as of now I'm not putting primes anywhere, so I'll keep modifying this, but as of now I don't know where to put primes. So primes is somewhere outside for me right now. Okay, but what is this class NP? So let's define that. Okay, so there are some problems for which there are some problems for which maybe solving it may be hard, but if I give you the solution, it's easy to verify. So so let me just take the same example. So instead of prime, let me write composite. And if I write composite, what do you think I should change in the algorithm? There are only two changes. Can you quickly tell? Okay, I'll just hint you. So what should I write here? If there is a number that divides n, then what should I write here? Is the question clear? So are the two problems clear? Prime says yes if the number is prime and no otherwise, and composite says yes if n is composite and no otherwise. So if you see, okay, so just given the definitions, do you see what we should do here?
And then you should return yes. If yes, then return yes.
Exactly, good. So instead of no, you say yes, and instead of yes, you say no. Good. Okay. So it's the same algorithm right now, and it's still an exponential time algorithm. Okay. So now, what we'll do is, I'll say that okay, maybe I don't know how to solve composites efficiently right now, but if you tell me the solution, I can verify it quickly. So for example, I can verify the solution quickly. What do I mean by that? If you tell me the number n, which is the input to the problem, which you want to check whether it's composite or not, and you tell me the solution. So let's say k is your solution. You're claiming that k is the solution, which may or may not be correct. Okay, so for example, the number is 42, and yeah, and the k that you give me is 2. You are saying that 2 is the correct solution. Then what I'll do is, if I want to check whether it is true, I'll simply check if 2 divides 42. If 2 does, then I'm convinced that yes, 2 is the correct answer. Okay, but you can also fool me. You can instead say that, oh, k is the 5 is the solution. Then what I'll do is, I'll do the same thing. I'll check if 5 divides 42 and 5 does not divide 42. So I'm convinced that your solution is not correct. So I'm basically just verifying whether what you're telling me is correct or not. And this I can do efficiently, right? So why is this efficient? I'm just performing one division operation. So if you give me a solution, I can actually check whether it is correct or not efficiently. So this is what we mean by verifying the solution quickly, and by quickly we mean polynomial time. Okay, so that's why I'll put the composite. Okay, so maybe yeah, so you're convinced, right? So why composite is in NP? Because you can tell me a factor and I'll check whether it is actually a factor or not. Is this okay? So okay, so maybe if it's not clear right now, maybe it will get clear in upcoming examples, but please give me some feedback. Yeah, otherwise I'll end up spending more time on the same thing. So okay, so here what you gave me as your solution was a factor k. Okay, and this I call a certificate. Whatever you give me to verify, I call it a certificate. Okay, and what I want is, I want the certificate to be small. So by small I mean it should be polynomial in terms of the input length. So maybe I'll not get into all the details, but just remember that it should not be very large. So for example, if I want to check the same thing for prime and the input to you is n, then your answer cannot be cannot be all the numbers n1, n2 and so on up to nk. I mean n minus 1. Sorry. Yeah, your answer cannot be 2, 3, 4 and so on up to n minus 1, because if you give me this answer, this is actually very large. You are actually giving me n numbers which I can't store. So right now I'll not get into. So in the portal, where want to approach those details before you asked. So you're saying in the Google group, right? There's a Google group, right, for the discussion forum. Okay, I'm not sure I understand the comment, but okay, I'll get back to you. Okay, so at least are you convinced that composites is in NP, because it has a short certificate or a short certificate which you can give me and I can quickly check whether it is correct or not. So if that is clear, maybe try out this example of reachability. So what is reachability? I think we defined this before. So your input to you is a graph G, and I'm giving you two designated vertices where S is the source and T is the target. Okay, and so for example, it could be like 1, 2, 3, 4, 5. Okay, and so for example, the input to you is this graph, and let's say source is 1 and target is 5. The question is whether there is a path from S to T. So in this case, is there a path from vertex 1 to vertex 5? Yeah, so indeed there is a path, right? So from from here, from the vertex 1 you can go to vertex 2, from 2 you can go to 4, from 4 you can go to 5. So there is a path that you can traverse from starting at 1 which ends at 5. So it simply says that output yes if there is a path from S to T and no otherwise. Okay, so for example, if I give you vertices, if I give you source as 3 and target as 4, then what should be the answer? So is there a path from 3 to 4? Okay, so no, right? Good. So there's no path from 3 to 4 and hence the answer is no. So this is the decision type problem, and the question is whether it is in NP or not. So I'm not asking you whether it is in P. I'm not asking you to give an algorithm that solves it in polynomial time. The question is, can we do this in NP? That means, can you give me a short certificate which I can quickly verify, using which I can quickly verify whether your answer is correct or not. So what could be a certificate? I mean, it's very obvious if you think about it. So what can be the certificate? How will you convince me? So for example, in this case, there is a path from 1 to 5. So how will you convince me that there is a path from 1 to 5? So you actually give me the path. So you tell me go from 1 to 2 to 4 to 5. You give me this certificate. So this is the certificate that you give me. Okay. And how will I verify now? I'll simply start at this vertex. You told me to start at 1. Then you told me to take this edge to 2. I'll check if there exists such an edge. That edge should exist. Then I'll go to 2. From 2 I'll read the next vertex you gave me. So 2 4 should be an edge. Then 4 5 should be an edge. So I'm simply checking whether those edges are present. 1 2 2 4 4 5. So you give me the certificate. All I'm doing is I'm just checking whether those edges are present. This can be done quickly. This can be done in polynomial time. So I can check for existence of edges 1 2 2 4 4 5. All this can be done in polynomial time. So hence I have a polynomial time algorithm that verifies whether the answer is correct or not. So hence I'll put it in the class NP. So reachability is also in NP. Sorry, where is the yeah. So I'll put reachability also here. Okay. Indeed, it so happens that reachability actually falls into P. If you do some clever, you can have algorithms to I mean, something like DFS, BFS or something would also work. So you can actually do this in polynomial time. So it falls in this, but I'm not focusing on P here. I'm focusing on NP. That is, I want you to be able to see whether the problem is in NP at all. Okay. So for example, if you try for primes, the same thing does not work. So the solution that worked for composites was that you just give the factor. But the same thing does not work for prime. Do you see why? So why is it not enough if you just give me a fact, some k? Why am I not convinced that the number is actually prime?
Tell me once again, ma'am. We can't understand. I can't understand.
Okay, so for example, if the number you had was 42, in case of composites, the number you had, the input was 42, and the value k that you gave me is 2. Okay, then I'm convinced that um, it is actually composite, because you can give me such a number which divides 42, and I'll check whether it actually divides, and I'll be convinced that okay, in fact the answer is yes, the number is composite. Okay, but if you want to tell me that the number is prime, how will you convince me that it's prime? Because by definition of prime, any number less than that should not be able to divide it, right? So just giving a number like this is not enough to convince me that it's prime, because the number that I have here could be 16, the number you gave me could be 3, and 3 does not divide 16 does not mean that 16 is a prime. It's just that the number that you gave me is not correct. If you give me 4, then I would have been convinced that it's not a prime. So is this clear now? So I'm just trying to say that although the problems are very similar, there is an easy certificate that you can give me to verify the yes instance of the problem. So for composites, you can give me the divisor, I'll check and say that oh yes, the number is composite. But if it's a prime number, then then even if you give me one number, that's not going to be sufficient to convince that it's a prime number, because prime by definition means that all numbers less than n should not be dividing it. So giving one number which does not divide is not sufficient to say that the number is not prime. Okay, so if you find this part about prime confusing, then I mean you can forget about it. Don't worry about prime, etc. But I just want you to take away, if there's one takeaway that you should take, that from this discussion, it is, when do you say that a problem is in NP? So that's the only thing I want you to take away. So for example, if the problem is reachability, the certificate you gave me was a path, simply the path, and I can just verify whether the path is actually taking you from the given source and the given target. So if it happens, then you say that the problem is in NP. So there are problems that are outside NP as well. We'll not get into all that. So okay, so I'll just so I had several other questions that I wanted you to try, but I think in interest of time I'll skip that, because there are other things that we want to discuss. So I'll just tell you the question, you can try it out on your own. So what is this problem called cycle? Cycle says the input to you is a graph, and output is yes if G contains a cycle and no otherwise. Okay, so this is the problem, and I want you to check whether this is in NP. If it's in NP, then what is the certificate that you will give me through which I'll be convinced? So quickly, if you can think of some certificate, what can you give me so that I can quickly verify that yes, there is a cycle? It's similar to what we did for path.
We can use the Bellman-Ford algorithm to find if there are such edges.
So finding an algorithm is an entirely different thing, right? So if I want to show that it's in polynomial time, I'll have to come up with the algorithm. But the essence of this NP type problem is I don't want you to give me an algorithm. I just want you to be able to check whether my solution is correct. So if you just give me some certificate or some extra information, can I just use that to see if your answer is correct? So uh, I mean, if you do a BFS and so on, you can find it. You can explicitly find a cycle. That is there. But right now, I don't want to do all that. Let's say I just want to verify. So what can you give me? Similar to what we did for paths. So in case of path, what you did was you actually gave me the path, right? 1, 2, 3, 4. So in case of cycles, what you can do is you can give me the cycle explicitly. So if there is a cycle, then the certificate would be 2, 3, 4, 5, 2. And then similar to the paths, what I'll do is I'll check if 2, 3 is an edge, 3, 4 is an edge, 4, 5 is an edge, 5, 2 is an edge. So the difference between what you are saying and what we want is that you're actually telling me something more, right? You are giving me an algorithm to find it. But I just want to verify whether your solution is correct or not. So if indeed there is a cycle, you can actually give me the cycle and I'll check whether it's correct. So this is the essence, because there are problems for which we don't know. So in this case, for cycles, we know there is polynomial time solution. That's why you can actually use the algorithm. But there are problems for which we don't know such solutions. So that's why we want to classify whether at least verifying your answer is easy or not. And I mean, that's why we're doing this exercise. Okay. So yeah, so I'll okay, if there are any questions, then you can ask right now, or you can also ask at the end of the discussion. But yeah, I hope the definition of the class NP is clear. Okay. Okay. So yeah, so now what we saw was this class NP, where I can check whether your solution is correct or not. So if the answer is yes, there is some certificate you can give me to convince that the answer is yes. And we saw another class P, where you have polynomial time solutions for the problems. So then it so happens that among these problems that are in NP, for example, composite and so on, there are problems that that are sort of hardest in some sense. So what do I mean by hardest? Hardest in the sense, if I can solve that problem, so there is some problem X here, let's say, if I can solve X, then I can solve all the other problems outside. So solving X is sufficient to solve all the other problems. So what do I mean by that? So these kinds of notions that you have, these are called reductions. Reduction simply means that I have a problem A and I'm going to do some pre-processing on it. So given problem A, I'm going to convert it, I'm going to do some pre-processing, and I'll convert it into a problem B. Okay, and once I have my problem B, I'm just going to solve B. Once I have the solution for B, I can actually find the solution for A. So if you can do this efficiently, if you can do this whole process of doing pre-processing, solving and getting back the solution. If you can do this in polynomial time, then you say it's a polynomial time reduction. So you can okay, just to give you an example, okay, I mean the only example I can think of right now is very trivial. So okay, if I come up with a nice example, I'll tell you. But okay, maybe I'll, yeah, but I hope it's clear that what do we mean by reduction. You take your problem A, you convert it into a problem, another problem, solve for that other problem, and you'll be and somehow if you can get back the solution to the original problem, then you have you have what is called a reduction. Okay, so then within this class NP, we have a notion of something called the hardest problems in NP. So one such problem which you have seen uh, is what is called vertex cover. So what is vertex cover, if you recall? Anybody? Okay, so what is vertex cover? Vertex cover is simply that say I give you some graph. So let me take something as simple as this. Okay, and I want to choose a subset of vertices. So if I choose this vertex, then I'm covering all the edges that are adjacent to it. If I take this vertex, I'm covering all the edges. So what I want to do is I want to choose a subset of vertices such that all the edges are covered. That means if I choose 1, if I choose 5, then what are the edges that are covered? Can someone quickly tell? If I choose just 1 and 5, what are the edges that are covered? So 1 is adjacent to this edge and this edge, 5 is incident on this edge. So only 3 edges are covered, but there is some edge here that is not covered. So this is not a vertex cover. When I say vertex cover, you choose a subset of vertices that will cover all the edges. So trivial answer would be that you choose all the vertices, then all the edges will be covered. Okay, but yeah, so this is always a trivial answer. You take all the vertices and it will cover all the edges. But what I want is I want to find as small a subset as possible. So in this case, can you come up with 3? Can you choose 3 vertices such that all the edges are covered? Yeah, anybody, if you have an answer, please yeah, please either use the chat box or unmute and speak. Is the question clear? At least is the question clear? Can you please respond? Okay, so the input to us is a graph G with n vertices, and I'm given a subset of vertices and a number. Okay, and I want to find minimum. Okay, maybe I'll just not take this. I want to find minimum S, minimum K, such that size of S is equal to K, S subset of B, and for every edge in the graph, there is some vertex in B in S such that um, V is in. That means for every edge, either the one at least one of its endpoints should be in the set S. Otherwise, that edge will not be covered, because for this edge to be covered, either this endpoint or that or the other endpoint, one of them should be picked. Okay, so to answer the question I asked earlier, can I do with less than 4? So let's say, for example, I don't choose 5, I only take 1 to 3, then all the edges are covered, because 2 will cover these 3 edges, and 1 will cover this edge. So all the edges are covered even if I do 1 to 3. Then the next question is, can I do with 2? Do I really need 3? So the answer is yes. Again, actually you can do with 2. So I don't even put it here. I'm just going to choose 2 and 3. So 2 will take care of these 3 edges and 3 will take care of this edge. So all the edges are covered. But then if you ask me whether we can do with one vertex, so the answer is no. You can try and see that if you just take one vertex, you'll never be able to cover all the edges. So the question of interest is, I want to find minimum such subset. That's what we are interested in finding. So trivial way, what is a trivial algorithm for finding vertex cover? Any algorithm that you can think of to solve this problem? Okay, so the trivial algorithm for this would be that you go through all possible subsets. So you start with one, check if it covers all, start with just by taking 2, 3 and 4 and so on, and then you, once that is exhausted, you try with 1 comma 2. If just 1 and 2 are picked, is everything covered, and so on. So basically you go through all possible subsets and find the minimum which covers all the edges. So how much time will this take? Okay, so this is the trivial algorithm that we said, and how much time will this take? Well, let's see how much time each of the step takes. So in the first one, we are saying it's a for loop where we are going through all possible uh, subsets of vertices. So if size of V is n, then what is the total number of subsets you can have? You can have exponential many subsets. So this is 2 to the n many subsets. And if I want to check whether it forms a vertex cover, I can do this in polynomial time. This is where you are using the property of NP. So this is where you are actually using the property of NP, because remember what we said about NP. We said if I give you a solution, you can verify whether it is correct or not, whether it is uh, yeah, whether it is a yes solution for your yes instance. So that means if I give you the vertex cover explicitly that take this subset of vertices, I can actually check if all the edges are covered in polynomial time. Hence, I can verify the answer correctly. So, this is just to complement the remark that we had earlier, right? So, we looked at cycles and so on, where it's already easy to solve the problem. But here is where we actually start appreciating the concept of NP, because we don't know whether we can find a polynomial time solution, but we do know that at least if you give me a solution, I can verify. So, this is where you are using the property. And this is just, if you do it carefully, you'll actually, within the first two steps, I mean within this itself, you can modify it so that you find the smallest such as and output it. So overall, although these steps only take polynomial time, but you're actually running the for loop for 2 to the n time. So overall this algorithm is really bad. So this takes like order 2 to the n time, which is exponential, which is bad. Okay, so yeah, so then what you actually end up showing is that vertex cover is in fact one of the hardest problems in NP. That means if you look at this as your NP, this as your P, then every problem that is there in NP, so for all problems, by problems I mean decision problems, for all decision problems X, or let me say A, which are in the class NP, you can give a reduction, you can actually give a reduction from A to vertex cover in polynomial time. Okay, so what do I mean by that? If you give me any problem here, I can take that problem A, I'll convert it, I'll do some pre-processing, I'll convert it into a graph and some parameters, such that my job is now only to find vertex cover for this minimum vertex cover for this graph. And if I have a solution for that, I'll be able to get a solution for the original problem A. So this is called the notion of reduction. And since all the problems reduce to vertex cover, that means if I can solve vertex cover in polynomial time, I can solve problem A also in polynomial time. So this vertex cover is like one of the hardest problems sitting there. There you might have seen 3 sat in the class. This is the first problem for which you establish hardness. Okay, so you say that vertex cover is NP hard. Why do we say that? Because what does it mean? It means it is one of the hardest problems in NP, meaning if you can solve it you in polynomial time, you can solve all the other problems in polynomial time. So that is the notion of NP hardness. And what is NP completeness? NP completeness means that the problem is in NP, and second thing is it is NP hard. So if it is both, it is if it is in NP, which is here, as well as it is hard as in there are other problems also that can be hard for NP outside, but it's an intersection. So you can imagine this is some NP hard set, which I'll just draw in red lines. So let's say this is some hard set, these are NP hard problems. Then this area that you get here, this is the intersection of these hard problems and the problems in NP. So this is the shaded area, and this is what we call the NP complete problems, and this is precisely what we wrote here. Sorry. Yeah, this is precisely what we wrote here. These are the problems that are in NP as well as in NP hard. So this is basically NP intersection NP hard. So this is your set of NP complete problems, and you now know two problems that are NP complete. Complete. One is the 3 sat problem, the other is 3 satisfiability, which I think is done in the lectures, and the other is vertex cover. So now let's say I want to show that yeah, I think you must have also done independent set problem. This is also something I think you did in the class. So okay, so maybe yeah, I'll just quickly recall the definition of independent set, then I want you to see how to come up with reductions. So I'll just do one such example. So what is independent set, or I'll just call it IS. So what is this problem? The input to U is again a graph G and some integer K, and output yes if there is an independent set of size K in G and no otherwise. And what do I mean by independent set? So it's basically the set of vertices. So what is an independent set? It's a subset of vertices such that for any two vertices in S, UV cannot be an edge. So what does that mean? So let me just take the previous example. Let me just take the simple example. So is 2 3 is 2 comma 3 an independent set? No, because if I take 2 and 3, there is actually an edge connecting 2 and 3. But for example, 1 and 5 is an independent set because there is no edge that connects 1 with 5. Okay, so trivial answer to independent set would be that you don't take anything. It's an empty set. Okay, or you just take one vertex. It will always form an independent set because there are no two vertices that form an edge. Okay, but like vertex cover, you had a trivial solution where you took all the vertices. But I'm not interested in that. I'm interested in the minimum size of vertex cover. Similarly, for independent set, trivial answer is that you just take one vertex. But I'm not interested in that. I'm interested in finding as large an independent set as possible. So there is some kind of maximization that I want. So whenever we say independent set, we want to find the maximum sized independent set, which in this case is, in this particular example, the answer is 2. Sorry, in this particular example, the answer is 2. You can't get an independent set of size more than 2 in this particular example, and this is also something that you did in the lecture. So you also saw that in fact you can actually show that the vertex cover problem reduces to independent set problem in polynomial time, and hence you know that independent set is NP hard. In fact, you can also show that it's in NP. It's also easy, hence it's NP complete. So the problem that I want you to try now is that you know that independent set is NP complete. So I'll not get into how we proved that. That is something we did in the class, but for now you don't need that. You just assume that I know that independent set is NP hard, and I want to comment about click. I want to show that click is also NP complete. So what is click? Click is that input to U is a graph G and a number K, and output yes if there is a click of size K in G and no otherwise. And how do I check? So I'll just give you an example of a click. So okay, so in this example, if I take these 4 vertices, then all of them have an edge to each other. So if I within these 4 vertices, they are all fully connected. Similarly, if I look at these 3 vertices, they are all connected to each other. Okay, so this is a click. Click is basically a set of vertices such that you have all edges connecting them. So maybe I'm missing some while drawing, but yeah, it's basically a set of vertices where all the edges are present. Okay, so the question is whether there is a click of size K. So what is the size of the click? It's the number of vertices there. So for example, this is a click of size 3. This is a click of size 4. Okay, so am I interested in the maximum size click, or am I interested in the minimum size click? What is non-trivial? Or do I want to maximize or do I want to minimize? Okay, so if I just take one vertex, It is a click because it has a, I mean, it's connected to itself. Okay, so finding one click is not difficult. You just take one vertex that is already forms a click. But I want to find as large a click as possible. Is there a click of size, I mean, n minus 1 and something like that? So finding large maximum click is so for vertex cover you saw that it has, we want to minimize. So for vertex cover we want to minimize, we want minimum number, minimum size vertex cover. For independent set I wanted maximum sized independent set. For click I want maximum sized click because that is non-trivial. Okay, so um, yeah, so given this problem, given independent set, given click, you know that independent set is hard. Use this fact and show that click is also hard. So I don't want you to explicit, I mean, just come up with a reduction from independent set to click. So that means I have a graph G and some number K. I'm going to transform it into some G prime and some other K prime, such that if I solve click, I'll be able to solve independent set. So I'll just let you think about it for a minute or two. Okay. Okay, anybody, any ideas? Okay, so maybe maybe let me show you one such reduction and let me know if there are any questions. So what we'll do is we will convert, so I have independent set, I want to convert it into an instance of click in polynomial time. So input to me is a graph G and a number K. Okay, and I say yes if G has a K sized independent set. Here you say G prime K prime if G prime has K prime sized click. So what you will do is maybe just take an example. Okay, I'll take the same example that we had here. So 1 2 3 and 5. Okay, so this is 1 2 3 and 4. Okay, and what I'm saying is let me take some independent set here. So I'll just take 1 and 4, and from this G I'm going to come up with another graph G prime. How do we form G prime? Write the same vertices. So vertices is 1 2 4 3. Okay, the vertices are same but edges are such that if in the original graph there is an edge between 1 and 2, then you will not have an edge here. Okay, but if you, let's say, look at 3 and 4, there is no edge between 3 and 4. So in this graph now you will add an edge. So whenever there is an edge in the original graph, you will not take it in the new graph. When there is no edge, you will add that edge. So you are kind of taking complement of the graph. So what will you do now? So 1 2 is an edge, so I won't draw. 2 4 I won't draw. 2 3 also I won't draw. So only edges that I'm going to draw are these two. Okay, and notice that the two vertices that you colored earlier. So let me just highlight it again. The two vertices that we colored earlier are 1 and 4, and they form a clique. Why do they form a clique? Because between any two vertices in that set you have an edge. So recall that here between 1 and 4 there is no edge, because that's what the definition of independent set is. But here between 1 and 4 there is an edge, because that is the definition of clique. So this was a smaller example, that's why maybe you won't maybe generalize, but let me take a bigger example. Okay, so let me take this example. Here one independent set that you can come up with is 1, 2 and 3, because there is no edge between 1 and 2, there's no edge between 1 and 3, there's no edge between 2 and 3. So you look at all these vertices, they do not 1, 2, 3, there does not exist UV in the set S such that UV is an edge. This is by the definition of independent set. What will happen when you complement this graph? 1, 2, 5, 4, 3. What will happen now? Because there is no edge between 1 and 2, you have an edge here. Because there is no edge between 1 and 3, you have an edge here. You have an edge here. So they already form a clique of size 3, because so if you see just by definition, it's actually the opposite. Both are opposite definitions of each other. When I say a set forms independent set, that means if you look at any pair of vertices in that set, they do not have an edge. So what will happen in the complement graph? Because they do not have an edge in the original graph, they will all have an edge in the complement graph. So if S is a independent set in G, then for all pair of vertices UV in G, UV in G, UV is not an edge. Okay, but that means for every pair of vertices UV in S, edge in G, UV is an edge in G bar. Because, so what we did here, this is simply the definition of independent set, because when S is an independent set, it must satisfy that for any two vertices in that set there should not be an edge between them. And when I write this, we are simply using the property of complementation. That means if there is no edge in G, then if UV is not an edge in G, then UV is an edge in G bar, because that is how we define complement. If there is no edge, add that edge. If there is an edge, remove it. And what does this mean? That means you have some set of vertices in S where every pair of them have an edge. That means it's a clique. This is by definition a clique. That means S is a clique. And what is the size? If S is of size K, there is a K-sized independent set, and therefore you have a K-sized clique in G bar. So what is the pre-processing that we did? We simply converted G into its complement graph. So from G, we told how to get G bar, which is simply by complementation. And what is K prime? K prime is simply K. Okay. So so in this case, it's also obvious how you can use the solution for clique to get a solution for independent set. So for example, if you solve clique and you say that 1, 4 is the clique here, then the same set of vertices actually form independent set there. So in case of the reduction from vertex cover to independent set, you have to do some n minus k. If you have k parameter here, you have to give n minus k parameter there. If you remember, the graph is same, but it's just that the integers change from k to n minus k. But here what happened is k remained the same, but we changed the graph. So, and also note that all this pre-processing can be done in polynomial time, because I'll just look at the adjacency matrix, and instead of 1 I'll write a 0, instead of 0 I'll write a 1. So all this can be done in polynomial time. So therefore this P. Yeah, therefore this P. And you can also show that in fact click is in NP. So what will be the certificate? The certificate is just give the subset of vertices. I'll check if they have edges between all of them. So this is for the hardness. This is how you conclude that click is NP hard. And you can independently try to see that it's also in NP, and therefore you conclude that it's NP complete. So you show that click is in NP, and therefore now you proved it's NP hard. If you can also show it's NP, therefore it becomes NP complete. Okay, so I don't know if I went fast here or slow here, but if there are any questions about whatever we discussed so far, this is a good time to ask. Is the reduction clear? Is the idea of reduction clear? NP completeness, NP hardness, any of that?
Ma'am, you can tell again NP hardness and NP.
And NP, NP hardness and NP.
Yes, sir.
Okay, so yeah, so what do I mean by NP? First of all, by NP I mean that if you want to convince me that the answer is yes, so this is a decision problem first of all, right? So that means the answer is either yes or no. So if you want to tell me that the answer is if you want to tell me that the answer is yes, there is some small certificate you can give me which I can verify, using which I can verify that it's correct or not. So for example, for the case of composite numbers, I want to check whether the number is composite. So if the answer is yes, the number is composite, you can give me one factor. Just give me one factor of that number. And what I'll do is I'll just check if that factor divides my number. If yes, then I'll be convinced, oh yes, it actually is a certificate. So another example is just this vertex cover, maybe. Or let me just take click because that's something we freshly did. If I want to show that click is an NP, so your input is a graph G, an integer k, you want to check whether it has a click of size k. What does click mean? That between all those subset of vertices, k many vertices, every two vertices will have edge. Okay, so if you want to convince me, maybe I can't finding that may be hard because I'll have to go through all the graph and entire graph and see if you have such a structure there. Finding that may be very hard because you have to go through exponentially many possibilities. But if the answer is yes, that is indeed there is a click in the graph, then what you can do is you can give me as a certificate, you give me those set of vertices, maybe 3 4 5 6 7, these are the vertices in your graph. Just tell me the names of those vertices. If you give me this certificate, I can actually check if the answer is correct. So how will I check that? I'll just go through the vertices that you gave me. So 2 3 4 5 6, I'll see if 2 3 is an edge, 2 4 is an edge, 2 5 is an edge. For every pair, check if there is an edge, and if there is, then indeed I'll be convinced that oh yes, the answer is correct. So finding that click may be hard. I don't know how to find other than going through all possibilities, but if you give me the click, I can actually verify that it's correct. So this is what NP is NP clear now?
Yes, ma'am.
Okay, good. And what do I mean by hard? So by hard we mean that within this set of, so we collected so many problems in NP here. Within these problems, there are some problems that we believe are hard. Hard in the sense, if you can solve that problem, you can actually solve every other problem. So this is something they did in class. We started with a problem called 3SAT. It's called satisfiability. The input is a formula, Boolean formula. You want to check whether there is a 0-1 assignment that will make the formula evaluate to 1. So this is the first problem that they showed is hard. Hard in the sense, if you solve this problem, you will be able to solve every other problem. Okay. So then by reductions, you can actually start showing that other problems are also hard. So that means if 3SAT reduces to vertex cover. That means if I solve vertex cover, I can actually solve 3 sides. So this is the notion of reduction. When I say A reduces to B, that means if you solve B, you will be able to solve A. Okay, so this is how you will start putting more and more problems to this set. So what does this mean? This means if I solve vertex cover, I'll be able to solve 3 sat, therefore I'll be able to solve every other problem. So then vertex cover also becomes a hard problem here. Okay, so then you start putting these other problems. Then they also, you did in class how independent set comes into this and so on. Yeah, so by hardness we just mean if you solve it, you'll be able to solve all the other problems. So how do we show that? You actually take some problem that is known to be hard. So for example, if I want to show click is hard, what I did is I took one problem which I know is hard, which is independent set here, and I showed that that problem reduces to this problem that you want to solve. That means if I can solve this, I'll be able to solve this, hence I'll be able to solve everything.
Okay, ma'am. I understand.
Okay, good. So yeah, so that is the discussion about PNP and NP completeness, and there is a huge hierarchy out there. There are so many classes in between them. There are classes outside them, PNP, EXP, and so on. It's a whole area of research, but for the scope of this course, we'll not get into it. But if you are interested, you can check out. You can check out by the name of complexity classes. Okay, if you are interested, you can see there are many classes out there. Okay, but yeah, so now we'll move on to the next topic, which is called linear programming. So linear programming, and yeah, I think by name itself you can guess what it is. You might have also seen it previously, but what we want to see in this is a perspective of how we can use linear program to solve these problems. For example, vertex cover, independent set, all these problems that you saw just now. Okay, so just to recall what is a linear programming, it's an optimization problem. So when I say an optimization problem, it means either there is something that you want to minimize, there's some quantity that you either want to minimize or maximize. You might have seen these kinds of examples in school where you have some budget, and there are different costs for different items. Yeah, some cost for chocolate and books and pens and so on. What you want to do is you want to take as many objects as possible, but you still want to respect your constraint, your budget. So within that budget, what is the maximum number of items you can buy, and so on. Or you can even have constraints like I want at least 2 books, at least 1 chocolate, and so on. So you might have seen these kinds of examples. It's the same LP, but only that we are now looking at objects that are different, graph and so on. Okay, so I'll just write what does an LP look like. Typically you have an objective function, and the objective, so let's say x1, x2, these are the variables, and there is some objective function. That means you want to maximize or minimize some constraint, and the constraint is always going to be linear. That means it will be some x1 plus x2 plus x4 or something, but it cannot be x1 square, x1, x2, because it's not linear. The degree of each term here should be 1. And then you have some constraints. What do I mean by constraints? So maybe x1 plus x3 is less than equal to 3. So this could correspond to that the total number of books, which is represented by x1, and the total number of chocolates, the sum of this should not be more than 3. So this is how you used to do. I mean, it's the same thing. You can have multiple constraints, or you can say I want at least 1 pen if x2 denotes the number of pens. So you can have such constraints, and typically these xi's are integers. So we are looking at integer linear programming. What do we mean by that? By integer we mean that all the variables are going to take integer values. There is also something called fractional linear program where xi's are allowed to be fractionals, but we are not interested in that for as of now, so we'll focus on integer linear program. Okay, so is this recall enough what a linear program is? Okay, so if that is clear, then what we'll do is we'll start by a simple recall of vertex cover problem. And what we are saying is, what is the vertex cover problem? I have graph G, I have integer k, and check if G has a vertex cover of size k. And how do I write integer linear program for this? um, what are the variables? So variables would be, so these are, so let's say v1 sorry, yeah, just let I'll just let the pencil charge for a moment. If you have seen in the class already, or if you have any ideas, or even if you have not seen, can you identify what should be the variables? So let's say G has n vertices, v1 v2 up to vn, and it has m many edges, e1, I'll call those edges e1, e2, and so on up to em. Then okay, so I'll define my variables. So let me start by defining variables. Okay, so so what do I mean by that? So I'll say xi, maybe x1 is 1, then that means the vertex 1 is taken in the subset. So remember, what is vertex cover? I want to choose some subset of vertices S such that for every edge there is some vertex in S. So that means v1 is chosen, v1 is taken in S, and if it's 0, that means v1 is not taken in the set S, where S is the vertex cover that we would want. So these are the variables. So are the variables clear? For every vertex there is a variable. For v1 vertex there is variable x1, which is 1 if it is in the vertex cover, otherwise it's 0. So you can similarly define x2, x3, and so on up to xn. So there are n variables, x1, x2 up to xn, one variable per vertex. Okay, so what do I want to maximize? Now the objective is to minimize, right? So in the vertex cover, the objective is I want to minimize the size of the vertex cover. So what is the size of the vertex cover here in terms of x1, x2, x3, x4? I mean up to xn. So does everyone agree that this is exactly the size of the vertex cover? Why is that? Why is that? Because whenever this variable is 1, that means it's in the set, it's in the vertex cover. Whenever the variable is 0, it means it's not in the set. So if it's in the set, it will give 1. So for every element in the vertex cover, it will give 1. Hence this sum corresponds to the size of the vertex cover. Is this okay with everyone? So why does this sum correspond to the size of the vertex? So is that okay? Okay, if not, then let me know. I'll move on with the constraints. And what do I want to do? I want to minimize the size of this vertex cover. Hence the objective is to minimize. In case of independent set, it would be to maximize. Now I'll write the constraints. What are the constraints? The constraint is that for every edge, at least one of its endpoints should be in the set. So for example, if this is an edge, either u or v should be in the set S. Otherwise, if u is also not there, v is also not there, I won't be able to cover this edge. So how do we capture this in terms of constraints? So maybe just take this example. Okay, uv is an edge. I want to make sure that either u or v must be in the set S. Okay, so we'll say that for every edge uv, xu is the variable that is 1 if u is taken, and xv is the variable that is 1 if v is taken. What we are saying is at least one of them should be taken. That means xu plus xv should be at least 1. Okay, it can be 2. You may have to choose both, but at least one of these should be taken. Hence the sum of xu and xv should be at least 1. This constraint you will write for every edge uv in the graph, and this will be the set of constraint. This is precisely the set of constraint. So this is how we captured the vertex cover problem. We are saying I want to minimize the size of vertex cover, which is basically sum of these variables, and the constraints are that for every edge at least one of its endpoints should be in the set. So that's why the sum of xu and xv, which are the two variables, the variables participating in that edge, the sum should be at least 1. So why are we doing this is because if I can actually you'll see so many problems where you can translate the problem in terms of a linear program, as we will see now. We will see some other examples also. So it's like a one shot solution to all these problems. So recall that we said this problem is hard, meaning we don't have a polynomial time solution as of now. Maybe someday someone can find a polynomial time solution. As of now we don't have. So there are so many such hard problems, and if I could just solve this integer linear program, let's say my task is now just to solve integer linear program. If I can solve it in polynomial time integral with integral solutions, then I have actually solved vertex cover, because the answer for this is actually the solution for my vertex cover problem. We are simply casting it as a linear programming instance. Okay, so this is why it's a tool. It's a one shot tool, not just vertex cover, independent set, click, and so on. And a lot of problems can actually be translated in terms of linear program, and if you can solve linear program, then well, you have solution to all these problems. So yeah, so that's why we are that's why it's a very useful tool. But right now we will not get into how do we solve this, but rather we'll see how do you convert a given problem into an instance of linear program. So we did vertex cover just now, so maybe you can try independent set problem. So just to recall, when is so this is you want to find a subset of vertices such that for every set of vertices in the set S, uv should not be an edge in the graph G. If you look at any two vertices in that set, there should not be an edge between any two of them. This is the independent set problem. So can you convert it in terms of linear program? What are the variables first of all? So can I work with the same variables? Maybe I'll use the same variables, let's say. So xi, x1 to xn are the variables where xi is 1 if the vertex is in the set S, and 0 otherwise. If that vertex is in the set S, I'll make the variable 1. If it's not, I'll make the variable 0. So what is the objective function? I want to maximize the size of this independent set. So what should I write? Anybody? I know, this is something we did just now, but yeah, please speak up. Okay, so will in fact it's the same thing. You do x1, x2, and so on up to xn. So whenever that variable is in the set S, it will take a value of 1, otherwise it will take a value of 0. So hence this sum exactly corresponds to the size of S, which is the independent set, and I want to maximize that. Remember, in the case of vertex cover, we want to find minimum vertex cover. Therefore we had a minimization in the objective function. Here we want to maximize, therefore you have a max. Okay, and what are the constraints? So we just now said that the constraint is that for every two vertices in the set S, they should not form an edge in the original graph. So how do I capture that in terms of these variables? Yeah, you can attempt. I mean, it's okay if the answer is incorrect or partly correct or even correct. I mean, it doesn't matter, but yeah, please at least try it for yourself. Okay, so okay, yeah, so what that means is for every edge UV, yeah, for every edge UV in the graph, you cannot take both the endpoints. You can either take one, or you can take none, but you can't take both of them. So that means xu, which is 1 if that vertex u is taken, and xv, which is 1 if vertex v is taken, the sum can be at most 1. You cannot end up taking both the vertices. If you do, then you have actually taken the edge. So that's the only constraint. You can even take 0, that is okay. And the values of x size are in 0, 1. So x1 can be 0 or 1, and so these are the integral constraints. So these are the constraints from the independent set problem. These are the integral constraints, and that altogether is a linear program for independent set problem. So is that clear? If there are any questions, then do let me know. Okay, so now what I'll do is I'll just give you one more problem to solve for yourself. We'll not discuss the solution right now, but try it for yourself. Yeah, if there are any doubts about it, then let me know. So I'll just define the problem. It's called maximum matching problem. What Okay, let me charge the pencil. So by the time if there are any questions about anything we discussed, you can feel free to ask. Okay, so let me just define what is the maximum matching problem. So so the input to you is a graph G. So and okay, so maybe I'll just show you an example first. So you have 1 2 3 4 5, let's say. Okay, so what I want to do is I want to choose subset of edges. So what are the edges here? These are the 5 edges. I want to choose some edges out of these such that no two of them are adjacent. So for example, if I choose this one, I cannot choose this one because they are adjacent, meaning they intersect at some vertex, but I can choose this as well as this. This is completely okay, because between this edge and this edge there's no common vertex. I mean, there's no common vertex that they intersect in, so this is okay. Even 1 4 and 2 3 is okay. Okay, so this is a matching. So matching is basically a subset of edges, some m which is subset of edges, such that for every two e edges e and f in the matching, e intersection f is equal to empty. That means for any two edges that you look at in the set M, they shouldn't intersect at a common vertex. So yeah, so that is what we mean by matching. So a trivial matching would be that you just take one edge, and it will not intersect with anything else because there's no other edge at all. So finding some matching is easy, you just take one edge, but I'm interested in finding maximum matching. In this case, this and this, if you take, it forms a matching, and this I claim is the maximum matching. You cannot find a matching of size 3 in this graph. If you take any three edges, you will end up finding some intersection. So I want to find maximum matching in this graph. So output is maximum matching in G. So I want to convert this into a into integer linear program. So I want to formulate this as an LP. So first question, what are the variables? So given that you already saw two examples, now can you define some variables that are suitable for this, capturing this example? Okay, so maybe I'll just give you a hint. So I want to maximize the size of matching M. What is M? M is a subset of edges. Okay, so what I'll do is, initially we did variables with respect to vertices. Now we will define variables with respect to edges. So I have my variable xi, which is 1 if the edge ei, so I can call this e1, e2, e3, e4 and so on. So there is a labeling of the edges if the edge ei is taken in the matching and 0 otherwise. Okay, so if that edge is in the matching, the variable will take a value of 1. If that edge is not there in the matching, the variable will take a value of 0. So then what is the objective? The objective function is that I want to maximize the total number of edges I can take, right? So hence it's a maximization function, and if I do x1 plus x2 plus x3 plus so on up to xn, then the sum is exactly equal to the size of the matching. This is something that we said earlier 2 times. Because it takes a value of 1 when the edge is in the matching, otherwise it takes a value of 0. So if you sum those up, that is exactly equal to the size of matching. And what are the constraints? So what are the constraints in terms of the problems? We said if you look at any two edges, they should not intersect. That means you should not take any two adjacent. Okay, so then what you will do is you will look at all pairs of vertices that are adjacent, edges that are adjacent. For example, here e1 e4, e1 e2, e2 e3, you have e3 e4 and e3 e5 as well as e5, e4, e5. So you look at all pairs of edges that are adjacent. For each such pair, for every pair ei ej, you actually, you don't want both of them to be there, such that ei intersection ej is equal to 1. You want exactly one of them there. So either um, yeah either you are taking ei or you are taking ej, or maybe you are not taking both. I mean, you're not taking either, but you can't take both. The moment you take two adjacent edges, you are violating the definition of matching. If I take e1, e4 which are adjacent, it's not a matching because you're taking two adjacent vertices. So the sum of these should be at most 1. That's, I mean, as simple as that. So you don't want to take two adjacent vertices both at a time. Either take one or take none of. So this is again, you have integral constraints, which is that x1 is, each xi takes a value of either 0 or 1. These are the integral constraints, and this captures the problem of maximum matching exactly. So you can try out other examples also in the course. You might have come across other problems also. You can try to convert them into a linear program. And like we said, the advantage is that if I can solve LP efficiently, if I can solve the linear program, then I have solution to all these problems. So this is in fact a tool that is used many times. If you want to solve a problem, you actually convert it into this, use the solution for LP and lift it to get your solution. So it's a very important tool. Yeah. So I think the other topic, so what we did today is the whole theory of what is NP, what is NP completeness, P, and so on. But and then we looked at this LP and how you can formulate all these problems in as a linear program instance. You can also solve. There are simplex methods and so on that you have seen in the class. You can also solve them using those standard algorithms, but solving them is not the major focus of the course. The major focus is that you should be able to convert a problem into this. We also saw the notion of reductions today. The other topic that was there is the is something called network flows, and one algorithm for that is this Ford-Fulkerson algorithm. But I think we've already we're already on time, so I think I won't be able to discuss this today. But there's anyway a session on you. So I think the exam is on Tuesday, and we have one more session before that, which is on Monday. So we'll try to do like a recap or summary of the whole course. So the important topics that you've seen, we'll try to do like a revision of that. If there's time, maybe we can solve one of these network flow examples. But I think that's all for today. If there are any questions about anything that we discussed today, feel free to ask. I'll stay back.
Next Saturday is the exam, is Mom.
Saturday, the upcoming Saturday.
Upcoming, no. After upcoming Saturday, 22.
Okay. Then we have some time. Okay, good. Okay, thanks for the clarification. But the session is still on Monday. It's on 17th. Okay, so you'll get the invite and link for joining the meet. So next we'll meet on Monday. But if there are any questions about whatever we discussed today, then stay back. I mean, I'll stay back. Sorry.
Ma'am, I missed before the class, before the sessions, problem solving sections that are available in YouTube.
Yeah, I'll maybe share the link with you. Okay, so okay, just give me a minute. Okay. Okay, so this I'm sharing in the chat. So this is the spreadsheet where all the links for the YouTube videos are there. But I'll also share um, I'll also share one link, one direct link to the YouTube with you. So yeah, either of these you can access. Um,
Ma'am, like for the paper, the final exam that we are going to have, it is just going to have the MCQ and fill up something like that, or it is also going to have the coding problem.
Yeah, so actually, I'm not sure what the exam will look like, but I think it's very unlikely that you'll be asked to write programs, or I mean coding type programs. Um, yeah, I think it will mostly be about solving problems. I don't know if all of them will be MCQ, or there can be some descriptive, that I'm not sure. um, but yeah, like I said, you can use the discussion forum, and there are people who manage all I mean these exams and everything, so they'll be able to answer it better. So you can use the Google groups, and yeah, do it as soon as possible so that you are aware of I mean what it will look like. Anything else? Okay, so thank you all for attending. I'll stop the recording, but I'll wait for a couple of minutes if. Okay. Okay, so yeah, hello everyone. Welcome to the final session for the tutorials on design and analysis of algorithms. And so what we'll do today is a quick review of whatever we saw throughout the course, and we may not be able to. So we'll do this through problems because I mean that's the best way I think to do it. So we may not be able to cover each and every topic that was covered in the entire course, but the major ones um, we'll try to do as much as possible. So there's some question in the group. So okay, so the content in the presentations. Okay, so in the exam, I don't know what kind of, I don't know if it's going to be just MCQ or if there will be descriptive questions. But yeah, like I said in the last time, you can use the portal, the group discussion portal on Google Groups, because this is completely out of my domain. So the people who are, so these are, I mean, different people doing different jobs. So I think if you write your query on that group, I think yeah, maybe you'll have an answer to your questions. And regarding the tutorials, the yeah, so I mean, I'm just trying to yeah, I mean, I'm just trying to explain the concepts through examples. So which will just help you to solve the assignments, because of course both are at different levels. The questions in assignments would be slightly easier than what we cover in the tutorials, but I'm just yeah, so I don't know though what the questions will look like and what the difficulty will be. So is that fine? So you can just use the Google groups on the spam portal. I mean, the discussion forum on the spam portal. Okay. So yeah, if you're speaking, I don't know. The mic is on, but I can't hear you. Okay. So yeah, are there any other questions before we get started? Okay. Okay, so if not, let's get started. So, um, I'll just, um, yeah, I'll just try to cover um, as many topics as possible, but we'll do it through examples. Okay. So, okay. So let's start with um, yeah. So let's start with the Tower of Hanoi problem. I don't know if you have already seen it, but it's a nice example to recall the concepts. So it's the Tower of Hanoi um, problem, and what it says is that you have three pillars. You have three pillars like this, and you can insert discs in it. So there are different discs. There are n many discs, and they're all of different sizes, all of distinct sizes. So let me say 1, 2, 3, 4, 5, and they're in the sorted order. Now, what you want to do is, yes.
In that example point of view, you telling like what we know like that, no, ma'am. In that you in tutorials, some of the problems we explain. You explain, ma'am. In that there is no options at all like a quiz type. In that type of questions may be asked in exam. What we can do, ma'am? We can all. I mean, you solved where it is like that. We want to solve or how we can write, ma'am.
Okay, so yeah. So if there are descriptive type questions, then yeah, if they're asking you specifically to design the algorithm, then um, I don't know, I can't hear you if Sai Pritam, if you're speaking. But yeah, to answer the question, yeah, so if say there are questions of the following kind, that you design an algorithm for a specific problem, then then you can write a pseudocode, unless they're asking you to code. That I don't think will happen, but I don't know. But then you can write the kind of algorithms that we saw in the tutorials. And yeah, so majorly, if there are descriptive type questions, then you'll do as we did in the tutorials. And yeah,
It is also in online, no, ma'am. Like that. In that case, I am asking.
it's also online in the sense I didn't understand.
Online in the sense you what you explained that particular algorithm that is we want to write.
So are you saying, if such a question gets asked, you would uh, sorry, can you ask again? I think I didn't understand properly.
In online mode means you tell me, no, ma'am, within a pen. I mean pen that we want to type as an answer in the exam session.
Okay, so okay, I just want to clarify one thing. So is it an exam on paper or is it an exam on computer?
Computer, ma'am.
Oh,
Online.
oh, okay. And what is the duration of the exam?
2.5 hours, ma'am, mostly 2.5 to 3 hours they are telling.
3 hours.
Okay, okay. So okay, so if it's a typing exam, then yeah, then I'm not sure if they'll ask algorithms and so on. But yeah, if they do, then yes, you'll have to type it. Mm, okay, but I think you were asking for this last time, no? Whether there are MCQs or descriptive. So did you post it
Yeah.
already on the forum?
They're having a descriptive and quiz type, ma'am.
Ah, okay,
Both is
okay. Oh, okay, okay, okay. So okay, thanks for yeah, letting us know. So then yeah, then you will have to type it. Yeah.
okay, ma'am. Thank you, ma'am.
Okay. Yeah. So that means you may not be able to draw diagrams and so on if you need to, but maybe they won't ask you questions like that. Okay.
That's why I'm also asking, ma'am. Why
Mm,
means we want to draw the diagrams and we want to
mm,
explain moreover like that. That's why I'm
yeah,
asking.
yeah.
This problem session recorded sheet also available, ma'am.
Yeah, we'll record and upload it.
Okay. Thank you.
Okay, good. So yeah, we'll start with simple example that you might have already seen. Okay, so okay, Sai Preetham, if you can hear me and if you are not speaking, can you please unmute? Can you please mute? Um, okay, so yeah, okay, thank you. So yeah, so let's recall the problem. So you have some disks that are piled up in increasing order. All of them are distinct, and what you want to do is you want to transfer this whole thing. So I'll call this ABC. You want to transfer this whole thing to C. Okay, and this is what we want at the end. This is what we want to achieve, but the problem is that I can't just lift everything from the bottom and transfer it there. I have some limitations. So what are the constraints? The constraint is that you can only pick one at a time, so you can only oh, sorry. I'm really sorry. So the constraint is that you can't put a disk of large length on top of the small length. So you're not allowed to place a disk of large size on top of a disk of um, small size. So at any point of time, you can only you have to maintain it in the sorted order. So what is the algorithm for this? If you remember, please please tell me. That will help us speed up. Or have you not seen this? I'm not sure.
Using tower of NI.
um Sorry, I couldn't hear you. Yeah, can you please? Okay, so
Using the concept of tower of NI, destination, source, and abstract.
okay. Okay, so and yeah, someone says recursion. So yeah, so we'll just quickly.
Not recursion. So tower of NI using source, destination, and abstract attribute. Three steps we have to get into the steps. Tower of NI, n minus one, source and destination.
Yeah,
The
so the
form.
okay, but the algorithm that you end up writing. You can write it iteratively, you can write it recursively. So you can think of these as smaller subproblems. So you can also do it using recursion, but the idea you're saying is fine, I think. So um, you're saying that at any point of time we're going to do three steps. One is that um, yeah, so one is that I definitely want this disk 5 to come here at C. So the only way that I can do that is I'll have to somehow bring this four disks. I'll use the B as a temporary place, and what I'll do is I'll somehow get the four disks on top of each other, and then in the next step, so this will take some x many steps, k steps to achieve this. Then what we will do is we'll simply take this disk of largest size, and we will we will keep it here. So then what you need to do is you again need to get these four disks and uh, get those from B to C. So you have A, B, C and ABC. So we divided this task into three steps. One is that first get the n minus 1 disks from A to B, and then you take the nth disk from A to C, and then the remaining n minus 1 disks from B to C. So yeah, so that means we divide. So then what we do is, in order to solve this problem, in order to solve this subproblem, what we'll do is you'll again use the same idea. So in order to get this here, first you will have to get 4 here. To get 4 here, you will have to take the remaining 3, put it in the temporary, and get 4, and keep on doing this. So I mean, it's the same idea that you're applying again and again, only that the size of the subproblem reduces, and you have to use this the empty peg as your temporary. So that may be A, B, C, depending on where you are, where you want to put the next disks. But yeah, I hope everybody remembers this. If that is clear, can you tell me the recurrence relation? So if T of n is the number of steps needed to solve the tower of Hanoi on n disks, okay. So yeah, I think there's one answer. There's one answer in the chat which is correct. So the answer is that to solve the problem on n disks, what I'm doing is I'm first solving the problem on n minus 1 disks here, which is by taking everything on the top and pushing it on the other page. So what I'm doing is I'm spending T of n minus 1 time for that. Then once the disk that I wanted to move to the correct position is free, we're going to take one step and push it there. So that will take, let's say, order 1 time. And finally we are solving the same problem again, but from different place to different place. Now I want to move from B to C. So this is again a subproblem of size n minus 1. So finally you get 2 times T of n minus 1 plus 1. And how do we solve this recurrence? So what are the methods that you know to solve the recurrence relations? So one method that you know is the substitution method. So substitution method is very simple. It may not work all the time, but in this case it does. So this is solving recurrence. Yeah, you can use Master's theorem also. That was something that we did not do in the course material, but yeah, sure, you can use that. So yeah, so then how do we write this? This is same as 2 times T of n minus 2 plus 1 plus 1. So this will be 2 square T of n minus 2 plus 2 plus 1. And if you expand this further, this will be so I can just write 2 as 2 to the 1 and 1 as 2 to the 0. So finally what happens after k steps is, what do we get after k steps? Okay, so after k steps you'll have here 2 to the k times T of n minus k plus 2 to the k minus 1. If you keep expanding, you can see this pattern, and 2 to the k minus 2 and so on up to 2 plus 1. Okay, and when does this problem become trivial? So after how many steps will this become constant sized? Let's say size 1. Okay, so if you take k to be n minus 1, so after n minus 1 steps, what will happen is T of n is 2 to the n minus 1 times T of 1 plus 2 to the n minus 2 and so on up to 2 plus 1. And what is the value of T of 1? T of 1 just means that you have this peg where there's only one disk, and I just want to get it from A to C, so I can simply do it in one step. Simply take the disk and keep it on C. So this is simply, this just take one unit of time. So this will be 2 to the n minus 1 plus 2 to the n minus 2, so on up to 1. And this is nothing but your geometric series. And yeah, so you can if you solve this, you get this answer. So okay, so yeah, so can someone tell me whether the answer that we said that u of n is 2 to the n minus 1. So okay, so can someone tell me whether this is an upper bound or a lower bound? So for solving the Tower of Hanoi problem, should I say that the running time of this problem is always order 2 to the n minus 1, or is it omega 2 to the n minus 1? Is the meaning clear? So this is an upper bound and this is a lower bound for this. So if you read it, this would mean that to solve the Tower of Hanoi problem, you need at most some constant c times 2 to the n. So I'll just skip the 2 to the n part, I mean the minus 1 part. So is it this, or what did we prove just now? Did we prove the ordered part, or did we prove the omega part? Any guess is also okay, or if the question is not clear, then yeah, please ask. Okay, so yeah, okay, maybe let me just answer that. If there are questions, then let me know. So what we're saying is that you want to solve this problem, and there could be many ways to do that. So that there could be different algorithms. The one that we saw is just one approach of doing it. So if you're saying that, okay, look, here is an algorithm to solve Tower of Hanoi problem which takes this much amount of time, then you're just saying that the optimal solution for Tower of Hanoi will run in time at most order 2 to the n. Because why are we saying at most? Because you have one algorithm which takes this much time, but there could be some other algorithm which can do better. So you are just demonstrating one way of doing it, which is this particular algorithm that we said, solving for sub problems, combining them to find the solution to the whole problem. So yeah, so therefore what you are showing is actually an upper bound. You're just saying that it's at most 2 to the n time, because you already have demonstrated one algorithm. But if you want to say that you can't do better, that means claiming that it's lower bound, it is a lower bound, would mean that there cannot exist an algorithm which does better than this. So so yeah, so what do you think, is this true? So first of all, does everybody agree that it's at most um, does everybody agree that it's order 2 to the n and at the moment not omega? Is that part clear? Okay, so so yeah, I yeah, so are you so do you think it's also tight in the sense that there does not exist an algorithm which can do better than 2 to the n minus 1? So how many think you can do better? Okay, does anyone think you that this is the best time that you can get? Okay. Okay, so let's see. So the answer in this case is actually yes. It is actually it's the best that you can do, but that's not the case every time. So for example, you have seen algorithms for the minimum spanning tree and Kruskal's and so on, and when you demonstrate one algorithm, it takes some amount of time. You are not saying that you can't do better than that. You are just demonstrating one such algorithm. Hence, you are always giving an upper bound. Whenever you give an algorithm and you analyze the running time, it's always an upper bound. If you have to show lower bound, then there are it's difficult to prove that something is, I mean, is omega of something. So in this case, we can show that with not, which is not very difficult. So we'll try to maybe you can try to come up with an argument right now. So why do you think you cannot do better than this 2 to the n exponential time? Any thoughts? I hope the question is clear. So what I'm asking is that if you want to show that there is an order 2 to the n time algorithm, then here is one algorithm which you have already demonstrated. That part is fine. But if you want to say that it's a lower bound, you want to show a lower bound of 2 to the n minus 1, then how will you prove that for this particular question only? So you want to say that you cannot do better than this time. Okay, so I'll just give you a proof sketch which looks very similar to I mean very similar to the argument we saw, but it doesn't always work for every algorithm. So in this case it does. So the proof sketch is that if I want to solve this problem, then I'm going to have to first take the largest size disk and place it here. That is the first thing I want to do, because placing 4 or 3 or anything else there is not going to help me. I'm going to have to bring this anyway. So in order to do that, I'll have to move the whole block above it somewhere else, so that this becomes free and I can freely keep it here. So we're saying that in order to find the minimum number of to find the okay to minimum number of steps needed to push nth disk to its destination, which could be, in this case it's C, but it's, I mean, yeah, it depends. So is that you first solve it for the remaining n minus 1 optimally. So this you solve optimally, and then the next optimal step is you push the largest size disk to the push the largest disk to its correct position, and next thing you do is you again have to bring back the whole thing on top of the largest disk. So then you have to solve the n minus 1 part optimally. So yeah, so then if you do the analysis, you'll end up getting the same number, but only with this inequality. You'll end up showing that p of n is at least 2 times p of n minus 1 plus 1. You solve it, you get the same thing. The only thing that was different here was the fact that in order to take the first step, you have to solve this part optimally with minimum steps, you have to solve this part optimally with minimum steps, and finally this part. So this is something that is obvious in this example, but as you can see, if you take any other algorithm that you have seen, say shortest path or anything, arguing this optimally is not easy at all. And yeah, so if this does not make sense, then don't worry about it. It's just a philosophical sort of argument. But yeah, if it does not make sense, then don't worry about it too much. So the only takeaway, I mean, I just want to quickly recall the idea of recursion that you saw, and how to form the recurrence relation. And one way of solving it is through substitution method. And yeah, like some of you pointed out, you can use different methods such as Master's theorem and so on. So yeah, if that is clear, yeah, what we'll do is, yeah, maybe I'll try to get some greedy. Yeah, so just yeah, so you saw some sorting algorithms, and yeah, so yeah, so which one of them are yeah, maybe I'll yeah, so there are different algorithms you saw. So you saw this bubble sort, you saw quick sort, there was merge sort, and then you had selection sort and insertion sort. And you saw that these algorithms take order and square time. This is something we'll not get into. And these take order and log n time. So the analysis of the merge sort was deterministic. It's a deterministic algorithm, but for quick sort you use the randomized analysis for it. And there's one more sorting algorithm that you saw, which was heap sort, and this also runs in order and log n time. Okay, and one thing that you might have noticed here is that these kinds of problems have a different flavor, in the sense that given an input, there is one fixed output that is there. So it's just one-on-one sort of a relation. But so there's no optimization that is happening. There is a problem given to you, and there's a fixed answer that is correct. I mean, that's what you are expected to output. But there are also problems where you want to maximize something or you want to minimize something. So for example, you can think of the shortest distance, shortest path problem. And yeah, so here you had some source and some target given to you in the graph, and you were supposed, there are costs on the edges. So we saw this weighted version of graphs, and there could be multiple paths from S to T, and you want to find the one which is the shortest, in the sense that if you sum up the costs, it should be the minimum. So there's some kind of an optimization here. So either you are interested in finding minimum cost or maximum of some quantity. So these kinds of problems are what are called optimization problems. And there are two techniques that you saw for solving such problems. One is the greedy, and the other is the dynamic programming. So both of them typically give you polynomial time algorithms, not necessarily always, but yeah, but both of them are nice strategies which do not work all the time. So it's not necessary that for every problem you have a greedy or you have a dynamic programming solution, but there are several certain problems for which these are suitable. So what we'll do now is we'll just quickly maybe take few examples of greedy. We'll do some examples of dynamic programming. So okay, so let me just start with the simple example. So the question is that you have a car, and let's say you want to travel you want to travel some distance, so there's this there are several cities that you want to visit. Along the way there are several petrol pumps. So this is the petrol pump P1. There's some petrol pump, so sorry, I'll just, yeah, so there's a petrol pump P1, there's a petrol pump P2, and so on. There's a petrol pump PK. So there are and in between, so basically the towns may switch somewhere in between, so it's not necessary that in every town there's a petrol pump, so we'll not worry about that, but you just know where they are located. So maybe this is at a distance of 3 kilometers from the beginning, this is maybe at a distance of 10 kilometers from the beginning, and so on. So you know how far they are. And the problem is that your car cannot hold an infinite amount of petrol, so you have a limit, you have some limit on it. So if you fill it, let's say you fill your I mean the full capacity of your tank in the tank, then you can travel, let's say 10 kilometers. So if you assume that this car is capable of traveling maximum of um, say 10 kilometers. Okay, so so then notice that if you yeah, if you, let's say you keep traveling at some point, and let's say then you decided you would have exhausted some petrol, then at some point you decide to fill it. Okay, and then you move some distance. Okay, and you keep on doing like this. So the question is, one thing that you can do is maybe, okay, at every point, so let's say I travel some distance, I reach the first petrol pump, I'm going to refill my tank. Then I travel how much distance I can before I reach P2. Then in the second petrol pump also, let's say you decide to fill it again, and you do it every time. Every time you come across a petrol pump, maybe you fill it. Okay, so then you'll definitely reach the destination. But yeah, then you'll definitely reach the destination. But what I want to do is I want to minimize the number of petrol pumps that I visit throughout my journey. So this is exactly what I was saying earlier. So there's a contrast between the sorts of algorithms you saw earlier, I mean in the first part of the course, and what you saw in the second part of the course, where there's always some kind of optimization. There's something you would like to minimize or maximize. That's the kind of nature these problems are. So whenever you see some quantity being minimized, maximized, uh, typically you can try using the greedy or DP algorithms. So in this case, I want to minimize the total number of petrol pumps that are visited before, yeah, I mean, yeah. So then what would you do? Any you can think of any algorithm, but right now if you come up with a greedy strategy, that would be nice. So yeah, if you have any thoughts or ideas, I'll wait for a couple of minutes. You can, yeah, you can share with me. They need not be correct. Any idea is welcome. So any thoughts? Okay, I'll just wait for some more time, then we'll start with the answer.
At each and
Yeah, Ishwar, Krishna. Um,
yeah, ma'am. Actually, what I was telling is, at each and every petrol pump, we can fill the maximum petrol that a car can hold. Maybe this approach can give the best result.
um, okay, okay, okay. Yeah. So I'll get to I'll get back to you. So yeah. So regarding the comment that you have in the chat, so yeah, I myself don't have any um, yeah, any way of providing feedback, but as a student you have this Google form that's provided to you, right? So you get a Google form each week after the content of every week is released. So yeah, so um, you can give your feedback there, and they'll definitely take a look into it. Okay. Okay, so yeah, getting back to your approach. Okay, so what we'll do is, yeah. So you're saying that, let's say if you assume that the tank is full, you can cover a distance of 10 kilometers. So what you'll do is you'll go as far as possible within the 10 kilometers. So let's say within the first 10 kilometers, the final petrol pump, the last petrol pump that occurs is at P2. So at this point you'll refill your tank. Then let's say the next petrol pump occurs only at 17 kilometers. So that means if you look at the next 10 kilometers, maybe there are some in between, but within the next 20 kilometers, this is the last petrol pump that you have. So then you'll go as far as possible from there. At this point, if you don't fill it, okay, you can only go 3 kilometers further, but there's no petrol pump at 20, so you won't be able to move further. So you're forced to refill your petrol at 17 kilometers. Similarly, if you keep moving ahead, okay, then you look at the next okay, so maybe I'll just draw this again. So I'll just start with an example. So let's say you have at 3, you have at 7, you have at 10, then you have at 17, 12, okay, and then maybe let's say 30, 38. Okay, so this is the example. So when I write this 3, 8 and so on, what I'm saying is there are petrol pumps at those distances. So like you said, we are starting here, and the maximum distance I can go before my petrol is exhausted, which is 10 kilometers. I can walk 10 kilometers. At this point I will refill my petrol. Okay, and from here I again have a capacity of going 10 kilometers further. So I look at 10 kilometers further and I find the final petrol pump here. I'll fill it again. Okay, but now you're not going to look from 20 to 30. Why is that? Because right now you are at 17. From here you can only go 10 kilometers ahead. So from 17 you're going to look 10 kilometers ahead, that is up to 27. The last petrol pump that occurs before that is 23. You'll fill it again at this point. From 23 you're going to again look at 10 kilometers ahead. So where do you fill next? Okay, so is this making sense to everyone? Okay, so if it is making sense, then please answer. Even though it's simple, please answer. Otherwise, I wouldn't be sure whether, yeah, I mean, whether you've been convinced or not. Okay, so then I look 10 kilometers ahead, which is up to distance of 33, and the last petrol pump that I see is at 32, so I fill it again there, and finally I look 10 kilometers ahead, which is up to 42, and at this point I can even reach 42 without even having to fill the petrol at 38. So how many times did we fill the tank? One was at 10, the other was at 17, then we had to then at 23, finally at 32. So there are 4 points only throughout this journey of 42 kilometers where we ended up filling the petrol. So I'll just write the algorithm and then you can try to come up with an explanation for. So there are two things whenever you write an algorithm. First thing is it should be correct, second is you should analyze the running time. These are the two things. So I'll just write the algorithm. The algorithm is that, say you are right now standing at point x or distance x, then you look 10 kilometers ahead, so x plus 10, and find the last petrol pump ahead within that distance. And you're going to fill it there. So let's say that happened at y. So let's say this happened at y. Then you're going to look from y to y plus 10 and repeat the same process. So basically you're looking 10 kilometers ahead, finding the last one and filling it and keeping on moving ahead. So this is the algorithm. And how much time does this take? So the input to you can think of the input to you as an array where you've been given these distances 3, 8, 10 and so on. So what is the running time of this algorithm? Is the algorithm clear? Yeah, please. Sorry. Is the algorithm clear? If not, please let me know. I can explain it again. Okay, thank you for yeah. So if that is clear, can you tell me what is the running time of the algorithm? Uh, I mean, any guess is okay. Okay, so yeah, so let's see how will this happen. So you're let's say you are given this array where you have these distances 3, 8, 10, 12, 17, 23, 25 and so on. So let me not write everything, but sorry, 30, 38. Okay, then what you'll do is you're just going to look till um, look till 10, because initially you're looking from 1 to 10, so you're going to increment your counter at 10, then you will look from 10 to I mean just scan through the numbers, check the next entry, keep checking until you find a number which is larger than 20. So at this point you know that this is the previous one was the last petrol pump, so you should end up taking this. Then from this number you're going to keep scanning until you get a number which is more than 17 plus 10, which is 27. So that means the previous one you should increment the counter and look for 10 I mean the next entry in the array which is larger than 10 plus that value. So this is just the linear scan of the array, right? You are not doing anything much, you're just scanning through the array. So this will take order and time. This is something you can show. So the other thing that we said is, okay, we have an algorithm where the approach is greedy in the sense that you're going as far as possible when you know that if you don't fill now you won't be able to move ahead, you're going to fill it. So it's greedy in that sense, and it runs in polynomial time. That's what we did, but I want to show the correctness. So you have to be convinced for your, okay. So just to make it clear, whenever you write an algorithm there's a correctness associated with it, which I am not saying will be asked in the exam, but you should be convinced it's correct, otherwise you'll end up writing an algorithm which is not correct. So this is the only reason I'm asking. So I'm not asking you to prove it, but just an argument of why this algorithm will always give you correct answer is what you need to be convinced about. So, any ideas why should it always give you the minimum number of um, petrol pump visits? Okay, so it's okay if you want to think about it, that's also okay. I'll not I'll not get into it right now, but this is something to think about, because otherwise you can end up with algorithms which are not correct. So that's it. That's all I wanted to say. But yeah, so I hope at least the algorithm is clear, and the approach, what is the greedy approach, is clear. If not, then please ask me right now. Okay, so then we'll do one more example of greedy. Okay, so let's say that the question is that you have yeah, so let's say that you have some files. Okay, so you have different files. So this is of size maybe 2 MB. The other file f2, this is f1, f2 is of size 10 MB, and so on. So you have some files here. So let's say this is 32 MB f3, and finally you have fn, which is, let's say, um, 25 MB, and so on. So these are just any numbers. So basically you have some many files. They all have some size associated with them, and what I want to do is I want to perform merging. So I want to merge all of them all together to a single file. Okay, but the problem is I can't take all the n files, merge them all together, because I have limited resources. So what I can do is I can only merge two files at a time. So the input to you is an array where you have sizes of files. So this is, say, size of the first file was 2, 10, and so on. This is the input to you, and yeah, and what you want to do is you want to merge them. So the problem is that you can only merge two files at a time. Okay, so this is the problem. So you'll have to take two, merge them together, and keep on doing this. Okay, so one question that is there is how many times you will have to perform the merging operation. That is one question that you can try to answer. So I'll not get into it right now, but this is something that you should try out. So question is, how many mergings are needed merge operations are needed to get a single file. Okay, so this is one thing, but right now we'll not get into that. So yeah, so right now the problem that I have is, so this is completely a different problem. The problem I have is that, let's say I perform a merge of file of size 2 and merge of files with size 10, then the total cost I'm paying, so I'm paying some cost for merging, and the cost of merging is the size of A and B files, is the file size of A plus the file size of B. Okay, so for example, if I perform the merging of 32 with 10, then I'm paying the cost of 42, and then I have to combine, let's say 2 and 25. So then I'm combining the current file of 42 I have with 25. Then the total cost I'm paying at this point is 67. Then I have this file of size 2 which is not yet merged. Then I'm, let's say, merging it with this. Then I'm paying the cost of 69. Whereas if I do this in a different order, let's say I first merge 2 and 10, I get a size of 12. Then I merge, say, 12 and 25. Then I get a cost of this is what, 37. And finally if I merge 32 with 37, okay, in this case I'm okay, this is not maybe a good example, so I'll do 12 and 32 first. This gives 44. 44 and sorry, really sorry. So 12 and 25, this will give me 37. 37 and 32. Sorry, this is a really bad example that I came up with, but okay. But what I'm trying to say is that if you do it in different orders, you will end up spending different amount of different costs. So the question is, how should we merge it so that the total cost that we're paying for merging all the n files is minimized. Yeah, so yeah, Shesha Sai has sorry if I mispronounce your name. So yeah, that answer is actually correct. So you're saying that we'll do a greedy approach. The greedy approach is that you're always going to find the minimum sized files and you're going to merge them. So the algorithm is that uh, you're going to pick the two files of minimum size and we're going to merge them. So let's say these are AB, then we're going to perform merge operation AB, and then notice that now you have n minus 1 file. So if there were n files here and you merge them, then these two files have now become a single file and the remaining n minus 2 files are as it is. So now you have n minus 1 files, and the cost of this is updated. The cost of this file is the sum of the file sizes of A and B. So within this n minus 1 files, you are going to find the next two minimum and merge them and keep on doing this. So this is the greedy algorithm, and the claim is that if you do this, you will end up minimizing the cost. So the question is, what is the running time of this algorithm? So correctness we will not get into because it's something you can try out for yourself. I don't think you'll be expected to do this in the exam, so I'll not get into it right now. But the interesting question right now is, what is the running time? you can yeah so for now you can assume that it's given in an array. If it's given in an array, then how do you find the minimum elements? So one thing you can do is you can always keep sorting. So let's say you sort all the elements. So first approach would be that you sort all the elements, then take the first two and merge them, add their entries, and then now the current entry that you have can actually, so let's say you had 2 10, then you have, let's say, 8, sorry, you have 11, then 14, 20, 24, let's say, and you merge the first two minimum, then the value of this new file is now 12, but 12 is not in its correct position. So you need to sort it again, because this could be anywhere. This could potentially be anywhere in the new array. So because it's the sum of the two entries, so in this case it so happens that it falls here, so you need to sort it again. That's the worst, like a very loose thing you can do. So it takes like n log n time to sort every time. You're doing this n many times. So so if you do this, you'll get n square log n. But can you do better? Do you really need to sort it to find the minimum element? So what you can do is, since you only need the two minimum elements, instead of sorting, what we will do is you will just scan through the array. In one scan you can find the two minimum elements. So this is something you can try out. Of course, in one scan you can find one minimum element. In the next scan you can find the second minimum element. But in fact you can simply do it in one scan. So this is something you can try, but will not get into the details of it. So do one scan and find the first minimum and the second minimum. Okay, how much time will this take? This takes order and time. Now we have one new entry that is there with us. So this is, let's say, the new entry, and it's not, like we said here, it's not that the correct position for this is here. It could be anywhere here. So what you do is, instead of sorting it again, we use the idea of insertion sort, where you have an array which is a part of array which is already sorted. You want to insert a new element in the sorted array. So what you do is you scan through these from left to right, find the correct position where it should be, and add it, and then push the remaining values. So this is something, the idea that you insert the min star in its correct position. So how much time does this take? This takes order n. This is the same idea that you saw for insertion algorithm. And now you have your array sorted, and you're going to repeat. You are again going to repeat that, find take the two minimums, and keep on doing this if you are sorting in the first place. So yeah, so if you do that, instead of being n square log n, it will actually take you n log n time to sort for the first time, and inserting is only n per entry. So this will take like order n square. So instead of n square log n, you are actually doing n square, which is slightly better than earlier. So so with arrays you can say get up to quadratic. But if I want to actually truly get it to n log n, do you see how we can do this? If I want to get from n square to order n log n. Do you remember any data structure that you might have seen in the course that would help you bring the running time down? Good. Yeah. So what you do is you use min heap. So what is a min heap? It's a complete binary search tree where you have that the value at the root is lesser than the values of its children. This is the property that it satisfies. Therefore, if you want to find the minimum, it will always be in the root. And we can perform deletion operations, delete an element in the heap. This can be done in order n log n time. Order n log n time. This is something we saw. You can delete some element in the heap. Then finding the minimum can be done in order one time. This is because you know that the root is at the minimum. But if you want to restore the heap, so if you simply delete it, this will disintegrate into two different trees, which is not what we want. We want to restore the heap. So if you think of finding the minimum or deleting with restoration, then this is going to take order log n time. Similarly, insertion can be done in order log n time. There are several other operations that you have seen, but for now we only need delete and insert. So what you will do is, if you want to find the first minimum is at the root. We will delete it and heapify the whole tree. So then you get another tree, and the next minimum is going to be the root of this tree. So then now that you have the first minimum and the second minimum, we're going to add them together. So when you add them together, you get a new node with some value, and that needs to be inserted into the heap. So this insert process can be again done in order log n time. So essentially you are performing two delete operations and one insert operation. So two delete are being performed to find the two minimums, and one insert is being performed to add the newly merged file. And this we are going to do n times, because eventually you need to do n mergings to get one single file. So this is 3 operations per merge, so 3 into n. And delete and insert operation, both of them take order log n time. This is something you know from the heap data structure that you saw. So this is 3n log n, or let's say order n log n time. So if you do with arrays, you can get up to quadratic. Not saying that you can't do better, but the algorithms we saw, they do up to quadratic. But if you do heap, you can actually do in n log n time, which is asymptotically better than n square. So this is one example where you are actually using greedy approach to solve it, but if you make a good choice of data structure, you can actually improve the running time even further. Okay, so okay, so we have like 45 more minutes. What we'll do is we'll quickly so MST is an important topic in the course, so I want to cover one example of it. So we'll just quickly recall the algorithm and run it on the example. We will not do the data structure part today because we don't have much time. So but we'll just recall what the algorithms do. So just give me a minute, okay? Okay. Sorry. Okay, so you've been given this graph where the weight on the edge represents, basically it's a weighted graph that is given to you, and you want to find the minimum spanning tree. So just to recall, what is a minimum spanning tree? It's a tree where which contains all the vertices in the graph, and if you sum up the costs, there are many trees that you can find, right? So in this case, for example, this is one tree, A, B, C, D, F, E, and it's a spanning tree because it covers all the vertices in the graph. And what is the cost of the tree? The cost of the tree is simply the sum of the edge weights that that are there. So in this case, it's 10 plus 15 plus 5, which is 30. So the cost of this tree is 30, and there are many other trees that you can find. So for example, this is another tree, and you sum up the edge widths and you'll find the cost of it. So what we want to do is want to find one whose weight is minimum. That's the MST problem that we said. So we saw two algorithms, at least two algorithms for solving this. One was the Prim's algorithm, the other was the Kruskal's algorithm. Both of them run in polynomial time, and we saw how you can make a good choice of data structure to bring down the time complexity. So let's see how the algorithm, run the algorithm on this example. So what does Prim's algorithm do? It just it just takes the minimum weight edge, which is in this case 1. So what we'll do is we'll take this 1 and include it in our tree. Then we're going to take the next minimum edge. So what is that? That is CE. So we're going to take this. The next minimum edge is of weight 3, but then there are 2 of them. So which one do we choose? If you choose BE, then you are actually forming a cycle. So you're not finding a minimum spanning tree, you're actually finding a cycle. So what you'll do is you'll discard that edge and take the next one. So what is the next minimum we have? It is 4, and 4 does not form a cycle with the current tree that we have. So you take 4. The next minimum is 5, but 5 we can't take because otherwise this will form a cycle. So this is something we don't want. The next minimum that you see then is 7. So 7 we can take, it does not form a cycle. Next minimum is 8. So 8 I cannot take because this will form a cycle. So then I have to take 9, and 9 I cannot take because that would form a cycle. And we already have a tree which covers all the vertices of the graph. So this is the minimum spanning tree given by this algorithm. And what is the cost of it? The cost of the MST in this algorithm is 2 plus 1 plus 3 plus 4 plus 7, which is 17. Okay, and the minimum spanning tree is unique if all the edge weights are distinct. So if you have distinct edge weights, then the MST is unique. Okay, but the other way around is not true. It's not necessary that if the edge weights are not distinct, then there will be multiple MSTs. That is not true, and the example is this itself, because here you have two edges with different weights, but there is only one minimum spanning tree in this graph. So you cannot find any. So if you take any other spanning tree in this graph, you will find that its weight is strictly larger than 17. So okay, so now we'll run our Kruskal's algorithm on yeah. Yeah, so just to mention, I'll not get into the data structure, but just want to recall that we had done a find union We had used fine-tune data structure um, to get better running time for this. So we'll just quickly run the algorithm on Kruskal's algorithm on this same example. Okay, so what does Kruskal's algorithm do? It starts with a vertex, starts with any vertex, and it takes um, the least edge that goes through it. So let's say I am going to start at 1, and start at A. There are 2 edges that are outgoing from there. I'm going to take the one which is of minimum weight. So we're going to take 4. Okay, and now our structure looks like this. We only have AC. This is our connected component. Now we are going to look at all the edges that go outside A and C, and we're going to find the one with minimum weight, so which is in this case 1. So I'm going to take 1, and now our structure looks like this. It's ABC, and we're going to look at all the edges that go outside and find the minimum of this. So out of 5, 3 and 2, the minimum is 2, so we're going to take 2. Now our structure looks like this, and what are the outgoing edges outgoing are 5, 3, 3, and again minimum is 3, but we can't take this one. Sorry, this is not even in the yeah so this is not even in our outgoing edge, because it's an edge contained within it, which would create a cycle. So the minimum that you have is 3 here. Again, you end up taking that. Now our structure looks like this with A, C, B, E and D, and the outgoing edges from the structure are DF and EF only. So the minimum one is 7. So you'll end up taking this, and again you got the same tree. So in this case, because there is a unique MST, both the algorithms give you the same MST as an output. But if there are multiple answers that are possible, then different runs of algorithms may give you different MSTs, but all of them are valid. So there was also this data structure choice that we made for Kruskal's algorithm to get better running time, but again which was a priority queue, and we did a heap based implementation of this. This is the context in which we saw the priority queue. We saw the heap sort, but we'll not again get into it for the so maybe I'll skip this question also. This is the Huffman encoding part, but I think we've done enough questions on it earlier, and last time we did not get to do this Ford Fulkerson. So I want to do it for now. So hopefully we'll have more time to do other questions, but let's see. So okay. So maybe I'll just quickly recall what the problem is, what the flow is. Okay, so the problem is that you have this you have a graph, a directed graph that is given to you, and there is some target node. So, and there are some weights that are associated with them. So maybe I'm just writing random numbers. So basically you have a source node S, you have a target node T, and this is a weighted directed graph. And what I want to do is I want to I want to pass as much flow as possible. So this, what this 2 says is that the capacity of this edge is 2. That means I can direct a flow of at most 2, weight 2 through this edge. From this edge I can pass a flow of size of at most 7. I can't pass 8, a flow of 8 through this, and so on. That is what it denotes. Okay. And so these are the capacity constraints. So there are two types of constraints. One is the capacity constraint, which means that the amount of flow that we are passing through an edge E, this is the flow that is passed through edge E, is at most the capacity of E, which is the weight that is written on it. Okay, and we'll assume that all the weights are positive. Let's not go into the case where it's negative and so on, which you can handle in some cases. So for now, let's assume that these are positive. Okay, so this is the first constraint. That means if the capacity of this particular edge is C, I cannot pass a flow more than C. The second constraint that you have is what is called the conservation constraint, which means that if there is a flow through this node, outgoing flow through this node, we are passing a flow of maybe if the incoming flow on this node is of say 2, then the outgoing has to be 2. You cannot pass a flow of more than of less than 2 or more than 2 through it. If the total incoming flow is x, you have to push it back. It cannot preserve it cannot contain some flow with itself. So what that means is total inflow on any vertex is equal to total outgoing flow. So for now, let's say it has only at this moment it can this node B can only take a 2, but let's say I pass something more. Let's say I pass 3 through this, and and 1 through this. So what is the total flow that is incoming? 1 through this node and 3 through this path. So totally there is a flow of 1 plus 3, which is 4. But this we cannot do because it can only the outgoing flow is bounded by 3. I cannot pass a flow of more than 3 through this. So that is what this conservation constraint is. So first is I can't pass a flow more than the capacity. Second is total flow that is coming in should be equal to the total flow that is going out. So these are the two constraints, and given that I want to pass as much as flow as possible from S to T, that is the question. So again, you can notice there is some kind of a maximization flavor to it. So so it's an optimization problem. So the question that we are asking is, given these constraints, find the maximum flow from S to T. Okay, so so there are several algorithms for this, but the one that we are going to discuss, which is the Ford-Fulkerson algorithm. So what does the Ford-Fulkerson algorithm say? Okay, so if you know the algorithm, can you maybe try this out? I'll just take a small I'll just come back in 5 minutes. Okay, sorry about the sorry about the delay, but please take this time to solve it out, or if you have any questions, think about it. I'll be back in a minute. Okay, hi. Sorry. So, yeah, so if I'll just, yeah, if you have solved it already, then can you tell me the maximum flow that you were able to push through this network? Okay, so what we'll do is 4. Okay, so how did you pass 4? So what are the paths that you chose? So 7, 4, 5. So from this you could pass 4. Okay, but then you can also additionally, okay, sorry, just let me charge the pencil once. So from yeah, so from here you were able to pass 7, 4, 5. I mean, this is the so the maximum you can push through this is 4, because 4 is the bottleneck. Even if you pass 7 through this, you won't be able to push it out. That's why you need to push 4 through all of them, so that finally T gets 4. But then you can also push 2 through this S to B, push 2 through this, and 2 through this, so that it looks like this. So I'll just erase this. So you can push 2 through this. The red one indicates the flow that I'm passing forward. So 2 through this again, because this is incoming, so 2 should also go. And similarly, if 2 is incoming here for this node, then 2 should also go out. So I'm passing it like this. Then I'm passing 4, 4, 4. So this is 4, 4, 4. So what is the total flow that reaches um yeah, reaches this right now it's 6. I claim that you can actually do even more. You can actually make it 7. So how can we do that? Can you see one more path here? One more path through which maybe I can push a flow of 1. I'll just write label to the node so that you can tell me the name of the path. So this is A, B, C, D. So okay, I'll just write it this way. This is not 3 of 3. Right now I'm using 0 of 3, 0 of 6, because I'm not passing anything to this and this right now. Can you identify one more path? S, A, B, C. Good, exactly. So you're saying that, look here, there is a total capacity of 7. I'm only passing 4. Maybe I'll pass one more through this. So I'll pass 3, I'll pass 5, out of which 4 is, yeah, out of this 4, out of this 5, 4 is already going from A to D. So I'll pass a flow of 1 through this. So we'll pass 1 through this. Now the total incoming here is 2 plus 1, 3. So total outgoing should also be 3 by the conservation property. So 3 is outgoing. Similarly, for the C, the total incoming flow is 3. So we'll pass 3 outside through it. So you're going to get a total flow of 3 plus 4, which is 7. And yeah, you can't do better than this, because there is a bottleneck of 3 which is totally used here. There's a bottleneck of 4 which is totally used here, and you cannot find any other path from S to T where there is some edge whose capacity is not fully exhausted. Any path will give you some edge which is fully exhausted, so that the maximum flow that you could pass here is 7. Okay, so if so using the same idea, so what we're doing is we're finding a path where we can push flow. If it's possible to push, we're keeping on pushing. Find a path and keep on pushing. So this is the idea that we have. So using that idea, can you I've not defined what the Ford-Fulkerson algorithm is as of now, but using the same idea, can you just take a couple of minutes